Hello, hello. Welcome everybody. Day 3 of Devcon. We're gonna be starting in 10 minutes. Get excited, get ready. 10-minute countdown. Okay, folks, 5 minutes. 5 minutes. We'll be getting started. Get excited. Wow. All right, let's get going. Welcome to DevCon Day 3. Who's excited for some applied cryptography? Excellent. Hope you enjoyed that nice flute music while we got started. My name's Sam. I'll be your MC today. We got some really exciting talks, a lot of good stuff. First off, we got Gubsheep is going to be telling us how to hallucinate a server. I guess quick housekeeping. With these talks, we'll try to do 5 minutes for Q&A at the end of each. You're going to see a QR code that'll link you to a Meerkat poll to allow you to submit Q&A and upvote questions as well. So take advantage of that. Let's learn, let's listen, let's have fun. And first up, Gubsheep, welcome.
Thank you, Sam. Awesome. Thank you, Sam, for introducing the morning sessions. Hello, DevCon. I am Gubsheep, and I'm here to talk to you about hallucinated servers. Thank you for joining us on this morning. I know it's not easy to make the first morning talk of the day, so I appreciate everybody for making it out here. By way of introduction, I'm Gubsheep. I'm one of the co-founders of ZeroXPark. In particular, I work on a lot of applied cryptography projects from research to production. And today, I'm going to be talking to you about Frog Zone, which is a game that you might have seen downstairs if you swung by the Frog Crypto Community Hub. So downstairs at the Frog Community Hub, we have 2 tables of 4 machines each. You can log into one of these machines using your Zupass by scanning a QR code, and you'll be dropped into this very simple frog game that I'm going to describe now. So this is a screenshot from the game. Essentially, Frog Zone is a 4-player game where you control one of 4 frogs on a 32 by 32 grid. So there's a 32 by 32 grid. There's a map. There's some items. There's some monsters. You can attack the monsters. You can pick up the items. You're trying to explore the map. You can only see the 5 by 5 area around you. And in a time limit of 5 minutes, you're trying to make it up north to the ice biome to find and slay the dragon. And this is a cooperative game, so even though you don't know where the other players are, all of you are going to have to collectively come together to figure out the right path to get up there and then use your combined items to finish off the dragon. So as you can see, my frog's moving around. I just destroyed some enemy here. Here I can see there's a wooden sword. I can go over to the wooden sword and pick it up. And if I do that, I should see my attack stat up there increase. So you can see, frogs have lives. They have different stats. Let's just watch that happen real quick. And as you can see, the rest of the game is shrouded in this fog of war, right? So I can only see the 5 by 5 area around me. And in short, it's a pretty simple game, right? There's a very, very limited set of mechanics. In terms of, the game in numbers, the total size of the game is about a total of 150 bytes. That's the entire state of the game. The front end is built in React and Phaser. The source code for the back end is about 500 or so lines of C++, not including boilerplate. That might be something like half of that. And it took about a month for a team of devs and collaborators from Gauss Labs and ZeroXPark and PSE to build this together. So why am I showing you this? Why am I showing you this incredibly simple game that a kid could have probably built as their first programming project? Well, essentially, the interesting thing about this game is that the back end of the game is running entirely inside of fully homomorphic encryption. And to our knowledge, this is the first time a multi-user application with a backend that is running inside of FHE has actually been built. So that means that all of the state of this game is encrypted using FHE, and all player actions and everything happening inside of the game is happening inside of FHE. Oh, thank you. So one question you might ask is, why bother running this inside of FHE, right? FHE is super expensive. Well, one thread that we've been pulling at in the last year is this idea that technologies like FHE can enable us to run what we think about as hallucinated servers. So let me describe what I mean by that. Today, if a group of us wanted to come together and to build some sort of application that all of us might use, like, let's say, a social network for Devcon attendees. The way we would do that today is that we would have someone rent out an AWS server, write some sort of back-end code, and then deploy that back-end code to the web server, and then each of us would, using our computer or using our browser or client or whatever else, talk to this back-end server, making API requests to update and retrieve the state of the application. Now, using technologies like programmable cryptography, another way we can imagine doing this sort of thing opens up. So we can imagine in a world with programmable cryptography that rather than there existing a specific physical server with a physical footprint that's running all of the computations of the application, instead, every participant of the application might store something like a cryptographic shard of the overall state. And using technologies like multi-party computation or fully homomorphic encryption, we could cryptographically simulate the execution of this virtual machine using things like ZK proofs or FHE to advance the state of this arbitrary computation one step at a time, ensuring its consistency, ensuring that everybody is only having access to the data that they're supposed to be able to, while doing so in a decentralized multi-party way without needing to rely on a physical server anywhere that actually is the source of truth for the system. So this sort of opens up a lot of interesting questions. What if our digital services ran as these distributed hallucinated computations between just the relevant parties? We could imagine having this abstraction for a server where instead of servers run by Zuck, we have a server made of math that's perfectly secure, privacy preserving, verifiable, interoperable with every other service built in this way, etc. Of course, right now we're very early on our journey. So in terms of the game in numbers, in order to run this extraordinarily simple game, 150 bytes of state with 4 frogs on a 32 by 32 grid, we are using 9 machines to coordinate a variety of different MPCs together. So we have 4 MacBooks downstairs, and then we also have 5 192-core AWS machines in the cloud, costing us about $200 an hour to run this game. Every binary gate involved in the execution of any operation takes about 10 milliseconds to evaluate, which is about a 1 billion times overhead on top of ordinary computation. And for every bit of plain text state in this game, this bit will blow up to about 3,000 bits. Actually, I think this might be 3,000 bytes of ciphertext. I need to check on that, but it's a huge overhead. So the way that I think about what's going on is it's sort of like, we've built almost this particle accelerator and spent enormous amount of resources just so that we can suspend in the middle of the cryptographic ether for a brief instant something that looks like the Higgs boson, and we can sort of hold that stably. And in short, we have built what I believe is the slowest and worst performing game in the history of computing. Okay, so how does it work? Let's dig in a little bit to what's going on under the hood. So like I mentioned, there's about 9 machines that are concurrently performing various things together in order to hallucinate the state of Frog Zone. 5 of those machines are C6A 48X large AWS machines. They have 192 cores each, 384 gigabytes of memory. And then we've got our 4 MacBooks, which are our local clients that are involved in the decryption MPC. So whenever a player wants to make a move, move their frog up, down, left, or right, or attack a monster or pick up an item, they're going to send the encryption of that intent, of that request, to one of these 5 servers. That server is then going to share that encrypted request with all the other servers, and each of them is basically going to keep a replica of the fully encrypted state of the game. So that move is then going to be shared between all of these massive servers and then executed inside of FHE to update the state. Now, in order to retrieve the latest state of the game, and in particular that 5x5 area around you, each of the client machines is going to be talking to a dedicated server that will handle the request of executing a view function on the overall state and then returning the result of that view function in encryption to the players. So we need 5 servers here because all of these operations are enormously expensive. We're using these machines to distribute the load of both executing in FHE all of the player actions, as well as executing the view functions over the state to return back to the players. Finally, because the state is returned back to the players in encryption, no single player has the decryption key for the whole game. In fact, no single party in this whole system has the blanket ability to decrypt and read state. So the 4 clients each contain a decryption key shard, and they have to coordinate using a simple multi-party computation in order to decrypt any individual piece of state. So I'm going to send out requests. That's kind of that big box, that switch in the middle of the 4 clients for those who have seen the machines downstairs. That is helping to coordinate the peer-to-peer networking that needs to happen for these machines to talk to each other. Okay, so what's going on with the servers here? I've described the idea that a hallucinated server would not need a physical machine that's actually the source of truth for the application state, and yet I just showed you a diagram where there's a fleet of 5 machines. Well, it turns out that in this case, the servers aren't theoretically necessary. What they're doing is they're performing a deterministic operation that involves no secret data. So they're basically just these cattle which you can delegate computation to. They're performing these operations on top of encrypted data using a deterministic FHE scheme. Theoretically, we could run all these computations on the local machines and just have them cross-check each other, but for performance reasons, based off of where FHE is today, with the libraries we're using, Fantom Zone, we need to sort of add some additional computation power in addition to the 4 client machines that we have. So that's all that those servers are doing. I want to talk now about some tricks that we use to get a game working in such a constrained environment. So building out this game with the other collaborators has been a really interesting exercise. It kind of reminds me of what I've read about game development really, really early on, with the first personal computer games in the 90s, or even earlier than that, arcade machines. In a lot of these settings, game developers were working with very limited constraint sets. And for me also, this kind of reminds me of the early days of building blockchain-based games. So about 5 years ago, I worked on a game called Dark Forest, and this was before L2s. This was before there was widespread kind of toolchain support for ZK snarks. And you end up having to do a lot of interesting little hacks to even get something so simple working. So going back to our constraints, we have about the ability to work with maybe 200 bytes of plain text state. We have a 1 billionx computation overhead. We have an overhead that's somewhere in the thousands in terms of how big ciphertexts are, which have implications about how much state you can be transmitting over the network, especially here at a conference where tons of people are using bandwidth to find frogs or access their ticket, things like that. And one thing that we wanted to hold ourselves to was we wanted to keep each player action operating under 1 second. So every action that a player can take should execute in about 1 second, and that means that if all 4 players are constantly making actions, then players can be rate limited to performing an action once every about 4 seconds or so. We can start by even looking at how do we represent player actions. So all of those different actions that you can see in the game, whether that's picking up an item or moving to a square or attempting to move onto a square you're not allowed to move to, or attacking a monster, all of those are simply serialized as 2 encrypted bits that represent a direction. And under the hood, what the FHE circuit is going to do is it's essentially going to execute all of these possibilities for what you're moving onto or what you're attacking, etc. It's going to execute all of that simultaneously. So what that means is the FHE circuit is going to take in the approximately 200 bytes of game state, as well as 2 encrypted bits that represent your direction. And it's going to check, for example, for each of the tiles that you should not be allowed to move onto, we'll do an equality check between each of those pairs of coordinates. And if any one of those equality checks turns up true, then I'm going to return your new coordinate as equal to your current coordinate and not equal to the coordinate that would be computed by incrementing your x or y position. Similarly, with an item, we're going to simultaneously check for every item, is the coordinate you're trying to move to, that result of applying the direction on top of your original coordinate, is that coordinate equal to each coordinate of all of the items? And if any of the items turn up yes, then we're going to prevent you, or we're going to cause you to update your internal state to reflect the item upgrade that that item might give, and we're going to mark that item as consumed, and then we're going to refresh the entire state. So we basically have to figure out some strategy for factoring out the state into these different pieces and then running these checks efficiently over all of these different state coordinate pairs. Another thing that we have to be very aware of is the data constraints. So we don't want, when we're returning back something from the hallucinated server to a player for the decryption phase, we don't want to have to return a bunch of custom fields for all of the different kinds of entities that could live on a tile. In particular, because the computation that is returning what should be on each tile lives in encryption, whoever is making that return statement cannot know what's on each of those tiles. So we would have to, one naive way you could imagine implementing this, you could imagine implementing a big checklist that contains all of the items and all of the monsters and all of the, just all of the entities. And for every single one of the 25 tiles, it would return an encrypted bit for each checkbox in the checklist of whether that particular entity is at that particular tile. And because that bit is encrypted, the server or whoever's running the FHE, that could be a local client, would not know anything about what actually lives there. That's too expensive given the ciphertext blowup. So what we do is we have a 32-bit format, or it might be 40 actually, for what is actually being returned for any given entity. So we'll do some computation in the circuit. It will result in 32 bits. Depending on what those bits are after the decryption phase, that will tell you how to interpret these 32 bits. So the first byte tells you, various types of metadata, the entity type, the ID. Knowing the entity type tells you how to interpret the remaining 3 bytes. For the second byte, if it's a player or a monster, that represents the hit points. If it's an item, it represents the additional up. If it's a player, that represents score. If it's an item or a monster, that represents how many points you get for picking up the item or points for defeating the monster. And in this way, we can make sure that every tile that's being returned is simply this 32-bit thing without needing to special case for every single type of entity. Moving monsters was a fun one as well. So basically, you've got these 4 frogs that are moving around in the universe. Each of them can see a 5x5 square around them. But there's also a bunch of stuff going on in between each of the players' viewports. So monsters are actually these autonomous agents that are moving around inside of the global fog of war. There's some notion of global private state that is being executed on consistently, but which nobody in the game, neither players nor any of the delegated computation servers, know what's happening. So in order to do that, well, this is very expensive because for every monster we want to try to move, we again have to do that check of, is that monster moving to on a collision course with any of the boundary cells. So in order to make it feel like there's a bunch of monsters and they're moving in a reasonably performant way, what we have is we've just got these different kinds of monsters. One of the kinds of monsters is immobile, so we just never have to do this. Another kind of monster, we do have to do all of those collision checks. And then a final kind of monster, the bat here, it's a flying monster, so you don't have to do the collision checks, which speeds up things a lot on our end and still makes sense in the context of the game. There is a story about randomness here as well. So whether it's the initial conditions of the game or how the monsters are moving, you don't want any particular participant to know that, but you want that to be able to happen in a way that is correct and consistent with the execution of the program. So at every stage and at the beginning of the game, players are going to submit, they're going to randomly generate some randomness locally, encrypt that, and send that up to the server. The server is keeping an encryption of a global random state, and every time it receives a request, it can mix that in, and then it will use that randomness to seed various actions on NPCs or whatever. Okay, so that's the current state of things. You can try the game out downstairs. Just as a warning, it's very slow and very clunky and very brittle. I would not exactly call it a good gameplay experience. But you can play it, and you can try to slay the dragon. So another question to ask is, where do we go from here? Right now that we've demonstrated that it is in principle possible to build an application in this way, what might we want? Well, one thing that has become really clear is we might want more performance, whether that means adding a fleet of 10x more servers, or whether that means improving the underlying FHE protocols or the libraries that implement them. So with 10x more compute, we would be able to run this actually as a local computation between the 4 machines without requiring these delegated servers to help us perform these untrusted FHE operations. We could imagine procedurally generating the map itself. So imagine that rather than a fixed hard-coded map that is plugged in at the beginning of the game in encryption, all of the players submit their randomness, and we use an algorithm like Perlin noise to generate a new map every single time that truly no one, not the developers, nor the delegated servers, nor the players would know. Another thing that's going on here is that in the process of building this, we realized that FHE as a technology is limited in certain ways. So I previously described how in order to make any operation on the game, you would have to feed the entire previous game state in, plus the mutation that you want to do on top of it, and run a state transition function over the entire thing in FHE. Well, that's not really how we think about programs today. We usually think about programs in terms of memory access. I can access such and such array element, I can update it, I can read, I can write to this. And that ends up being much faster because I don't need to carry the entire state with me on every operation. There's active theoretical work being done on FHE protocols and MPC protocols that might fit more naturally with the program, the memory model. One thing that's been really annoying, especially with the conference Wi-Fi, is the decryption stage that must occur between all 4 of the parties using technologies like obfuscation and functional encryption, which we discussed earlier this week. You would be able to make it so that the view functions, so long as you're calling the correct view function, can return to you the appropriate state that you want decrypted, so without a need for this kind of group decryption. So that makes the hallucinated server behave, at that point, almost identically to a server. We want verifiability, so whatever machines are executing the computation, the FHE computation, right now they can't learn anything about the computation, but they can execute whatever function they want. They could be executing some nonsense. And then finally, you might want something like a data availability layer. You know, if you want to add in properties like censorship resistance or certain forms of consensus, perhaps you want to treat Frog Zone as something like a rollup. So that's an interesting direction as well. There's a few sort of conceptual or philosophical questions that arise as well, right? Like, is this an autonomous world? You know, somehow the bat that's flying around in encryption that nobody knows where it is, it has a kind of autonomy that is a different sort of autonomy from the kind that we get from blockchains and smart contracts, but it does feel like a new dimension. So what is the subjective experience of being a bat that lives in Frog Zone, that lives inside of encryption? You know, maybe this is how we're going to do mind upload technology in the future. I certainly wouldn't want to upload my brain into the cloud in plain text, but I might do it if it's encrypted or obfuscated. So that's all for this talk. I just want to shout out a number of contributors who have made this possible. This was a joint effort. It was built on top of Fantom Zone, which is developed by Gauss Labs. A bunch of folks from PSE helped enormously in writing the circuits. Han, Edu, and CC. Sohan and Marian helped to build out the front end, and a bunch of 0x Parkers as well helped with the deployment of this. So that's all I've got for this talk. You can scan this QR code, by the way, for a froggy surprise. For those of you who have been playing the Frog Crypto Zupass-based, ZK-based game, this will give you access to something special. But thank you all for coming to this talk, and we'll take questions now.
Woo! Thank you. Thank you, Gubsheep. We do have a few minutes for questions. I think it's going to come up on the screen. If not, I can read them. Can you elaborate more on the cryptographic primitives you used? Got into a bit. Curious if it's lattices to achieve the FHE.
Yeah, so one thing that's actually been really interesting about exploring this whole FHE world is that a lot of our old friends from ZK come up again. So, for example, one of the operations that folks might be familiar with that we have to optimize a lot during, ZK programming is fast Fourier transforms and various kinds of polynomial operations. These things also come up in various FHE schemes, and we suspect that maybe they could be accelerated even with similar methods. FHE schemes also rely on some cryptography we don't see as much in ZK, such as lattices. We might have different strategies for approaching those, but this is very much an open kind of question. I don't think that what we're using right now for necessarily Fantom Zone or Frog Zone today is going to be what we use in perpetuity. But yeah, there's a lot of kind of these early exploration directions.
Awesome. Looks like some folks are curious, what is the most powerful use case you've imagined with this tech stack?
Yeah, so I mean, one exercise you can kind of run is like, what if you take the most ridiculous technology that exists today and just mash it all together? I like to think about this idea of a cryptomata, which is what I think of as cryptography's equivalent of AGI. So imagine that you had perfect obfuscation. It was running on a blockchain that had enormous data availability guarantees and bandwidth. What you would get is basically like a truly self-sovereign program that's made out of math. That's can never be taken down. It's always executing properly. You can never open up the program to inspect its internal state, except as it is allowed to run. If you add in things like quantum one-shot signatures, that program might have things that can only be executed once. So it really feels like a physical program. And then you might think, what happens if you put an AGI, what if you run an AGI inside of that? Well, now you have this essentially autonomous being made of pure information that has first-class citizenship with reality in the same way that you or I do, or any living, thinking brain. So I don't know, the speculation here can get pretty crazy.
Love it. Looks like people are curious about code repos, about library usage.
Yeah, if you go to github.com/0xpark/frog-zone, you'll be able to see the code for this particular game. This is built on Fantom Zone, which is under the Gauss Labs organization. So if you're curious, come by the Frog Hub and we'll get you set up.
Awesome. Another round of applause for Gubsheep. Awesome, really incredible. Yeah, would highly encourage, if you guys do have more questions or are curious to check it out, go check out the Frog Zone. A lot of cool stuff happening on there. Crypto Frog Mania is in full force this week. Yeah, definitely check it out. Quite a few rabbit holes you can dig down if you want to spend the rest of your DevCon doing that. Moving on, more great talks. Next up we have Andreas, co-founder of Fileverse. Oh, okay, getting ahead of myself. We'll be back in a few minutes with some more great talks, so stay tuned. Okay, folks, Another great talk coming up at the Applied Cryptography track. Here we got Andreas, one of the co-founders of Fileverse, here to talk about how we decentralize the internet's collaboration layer. So get excited. Again, there will be a QR code. If you guys have questions during the talk, feel free to pop that in, and we'll have a few minutes at the end to chat through it. So welcome, Andreas.
Hey everyone, thanks for making it to the morning sessions. I know it's not easy, especially after yesterday's parties. So yeah, originally this was meant for the real-world Ethereum track. So I'm going to talk to you today a little bit about the legendary Pokemons of crypto, aka apps. Not much of infrastructure in here. And the main goal of the talk is actually to talk about how do we actually approach decentralizing one of the most essential activities on the internet, which is collaboration. And I'll use specifically the Devcon Collab app that we developed for Devcon with a bunch of teams right here, including the Devcon team, and that I'll describe in a bit. I'm Andreas, I'm the co-founder of Fileverse and ddocs.new, and let's go. So, super important context to get started with. There is over half of all internet users that trust one single closed-sourced and centralized app suite for their daily knowledge and collaboration, Google Workspace. And this is catastrophic because it's what you do every day. It's related to your identity. It's related to your friends, family, social graph, etc. So the premise that underlies my talk here is that internet freedom, meaning your digital rights, right to access information, right to coordinate with others, right to not be censored on the internet, cannot be guaranteed behind walled gardens. Worse even, we cannot even imagine new forms of coordination and collaboration that are independent of the cloud empires and a third party guaranteeing this type of collaboration for us. I'm going to speed through because I have only 10 minutes, so I'm going to go at 1.2 speed here. The problem speaks for itself. Mass surveillance, constant leaks, constant fumbles by companies going bankrupt, link rot, leaks, etc. And this problem is actually one that the crypto community knows very well, and yet it has a bit of difficulty moving on to something new. We should know better, but we could not necessarily do better until very recently. So, you know, we had our old aspirations and we've moved into something that is a little bit convoluted, messy, and a bunch of infrastructure that doesn't give us enough direction. Now, my point in the second section is that we should think of social technical counterpositioning to the cloud empires, to the current situation on the centralized web. And one useful concept to use here is by Ethan Buchman, which is personal computers unleashed on unimaginable levels of sovereignty and interoperability for people, and community computers, meaning public blockchains, will do the same for groups. Now, examples. Examples because we want to see apps here. This is the Devcon Collab.io app. The reason why I wanted to show you this today is because it was a community effort. It's something that started with the idea that, okay, what if we didn't depend on 15 Telegram group chats, 35 Notion pages, 63 Luma pages, and more for our conferences, and actually preserved our knowledge and ability to communicate, connect, and collaborate on something that is properly decentralized. So here on this app, this is powered by a smart contract that lives on Gnosis chain. It's powered by, the chatting is powered by XMTP. The storage happens on IPFS. It is also, the content addressing of all your content here is put on-chain. Access permissions are also done on-chain. You have people actually contributing incredible knowledge through PDFs, their own notes, comments, likes, etc. And this combines the technology that has matured over the past 10 years, including from Waku, from L2s, from Zupass for authentication, etc. And one cool part of this app that I really wanted to highlight is a real-time collaboration that you can do, and this is accessible to all Devcon attendees at the moment, which is enabled purely through peer-to-peer connections to your peers. So let me show you with a little introduction by Vitalik himself. Let's see. Yeah. Yeah.
How does Google Docs work? It's like, okay, everything goes off into a cloud and like servers like somewhere in America, I'm not even sure where, right? And the reason why it has to be this way is because people started about collaboration, right? And people started caring about things like not just like me editing a document for myself, but like people working together on documents, right? And then you have the vision is basically like, okay, you have to have a shared memory, and like maybe Ethereum can do that shared memory, right? So like that was the original Web3 vision, and of course I think the original Ethereum ended up not delivering back then, basically because there were three things.
So this was just a quick demo of the live collaboration that you can do in a peer-to-peer manner. Now, just to finish, since I have just 1 minute, I want to give you a little list of apps to give you a little bit of hope about the direction of the space at the moment. I just wanted to highlight one of the latest Just Stark blog posts, just to describe the actual properties that developers might have been looking very actively for in 2017 during the ICO era, when we were still calling Ethereum the world computer, which is that if you give Ethereum code, we can receive a very strong guarantee that it will run it anytime we call on it, and that if you give Ethereum data, and know with certainty it will still be available in the future, unaltered and uncorrupted. So there are a lot of primitives that have matured since. I have 30 seconds. These are some of them. I'm going to put them just online here so that people can see that, take screenshots, be available also on YouTube. Those primitives have matured. Today we combine also public blockchains with peer-to-peer networks in a really scalable and useful way. And this allows us to create new generation of apps that rival the UX and actually protect the data of our users at a global scale. We don't need 3 billion people anymore depending on one centralized cloud empire. We can actually have properly decentralized apps for everyone, and these are some of the amazing examples that have emerged in the past 2 years only. So I highly encourage you to actually look them up, try them. This is the future of Ethereum, and this is actually, I believe, the future of the open, free web, and not one that will be guaranteed by third parties that nobody actually wants to trust. Thank you very much.
All right, thank you, Andreas. Cool stuff. Looks like we got some questions. How does one ensure power doesn't centralize over time or fail to be maintained?
Yeah, great question. So the immediate answer is try to rely on as few third parties as possible. So we have a bit of a morbid thought experiment in our team. We like to think, okay, what happens if our whole team disappears tomorrow, turns malicious? And the answer is that our apps, our decentralized apps, can continue running because we actually do not take care necessarily of introducing new infrastructure. We actually leverage networks that already exist and that do not depend on 1, 2, 3, 4 parties actually maintaining them. So here you have communities that are maintaining these community computers, if you'd like, and building apps on top of them guarantees that, you know, the apps that you're using are passing the walk-away test. A team can walk away, you can continue accessing your data, running the software, and be independent and self-sovereign.
Love it, yeah. So we like the tech, we like the vibes. How do we bring the noobs?
So a lot of the apps that I actually showed in the last slide are noob-friendly. So Radical, for example, is for your average developer, coder. Instead of using GitHub, they can use Radical. Ddocs.new is made so that you wouldn't have even the need to create an account, which is a friction that even Google Docs has. A lot of those apps also work offline. They work in a way that do not require a wallet, that do not require you to dox yourself at Coinbase, give the name of your family, where you live, a picture of your cat, in order to get some crypto, to then send to your wallet, to then actually sign in a transaction, to actually be able to use the app. So a lot of those apps do not require all this, and account abstraction is something actually that got us past this important threshold of UX, which is something that we're taking full advantage of in the apps that I just showed you.
Right on. And we see question around how do you do the real-time tech? Is it using CRDTs, sync servers? Tell us more.
Yeah. So yes, we're using CRDTs, amazing piece of technology that came out or matured by 2019. I highly recommend an article by Martin Kleppmann at Ink and Switch that talks about CRDTs and how infra-less and peer-to-peer apps are actually possible. Also, our code is open source. If you want to learn a little bit more about it, go ahead and look at it. And yeah, we use WebRTC, we use IndexedDB to keep as much data as possible local, and do the syncing via WebRTC and some other technologies, again, that you can look up on GitHub or come talk to me afterwards for a discussion.
Right on. Give it up again for Andreas. Thank you very much. Yeah. Pretty insane to see half the internet is relying on Google Suite. Glad to see we're moving away from that. All right, we'll be back in a few minutes with another great talk. Stay tuned. We'll see you soon. Okay, welcome back. Going strong. We got a talk from Richard, one of the co-founders of ZK P2P, up next, talking to us about trust minimalized P2P marketplaces on Ethereum. Give it up for Richard.
Awesome. Hey guys, I'm Richard. Today I'll be talking about trust minimized P2P marketplaces on Ethereum. Go over the why, how, and some thoughts of looking ahead. So why are we here? If we look at Web 2 today, data currently exists in these centralized data silos, whether it's fiat currency in your bank account, your social graph, concert tickets, domains, etc. These lead to high switching costs for users. For example, you can't bring your followers from Facebook to Twitter. And these also are very extractive to these users. For example, Ticketmaster charges like monopolistic prices because they own both the secondary and primary exchanges. And lastly, there's like closed APIs, which make it very difficult to interop. Additionally, if you look at Web3 in our permissionless database, the problem is that it's really detached from the real world. If you look at your social graph, stable coins, like these DeFi instruments, and even ETH, all of it runs in a parallel system. In fact, most of DeFi today is self-referential. And so the solution here is to bring the real world to Ethereum. And the question is how? We can break through these kind of walled gardens using cryptography and also maybe TEEs. So we can use ZK and MPC, these new technologies, to allow us to permissionlessly export data from these centralized data silos. Techniques such as ZK email and TLS notary, which also can help us redact any kind of private sensitive information prior to exporting. Check out some of the other talks on ZK email or TLS notary today if you want to learn more deeply. But yeah, now with these tools, we can kind of compose any kind of Web 2 action with Web 3 action, such as proving a fiat transfer using ZK email to swap for some stablecoins on-chain, or proving ticket transfer using TLS notary to swap for stablecoins, or swap domains for ETH, etc., or even put a social graph inside a TEE to do some DeFi stuff with. An example of this flow that is in production today is ZKP2P, the project I work on. The problem that it fixes some of the issues I mentioned earlier, such as the high fees. The construction for this is pretty simple, actually. A seller comes in, escrows some funds in a smart contract and provides a payment ID. Buyer comes in, pays the seller, and uses that proof to unlock the escrow contract. Kind of replaces Binance or any kind of centralized exchange with a smart contract, and replaces the manual process of unlocking the escrow with instant unlock upon satisfying a predicate. This construction extends beyond fiat. Simply replace the off-chain payment with a digital asset transfer and a proof of payment with a proof of asset transfer. Now you can kind of do P2P trading tickets, trading domains, trade social media handles, CSGO skins, gift cards, and much more. You can even further extend this construction if you trust TEEs as a credible third party. You can kind of encumber a Web 2 account, put it inside a TEE, and act as an escrow for the Web 2 asset. And both seller and buyer send requests through the TEE. Once the TEE owns both funds and the Web 2 asset, say tickets, then they can proceed to unlock funds to both parties. Yeah, now you kind of can see the Web 2 account is fully programmable. You can do some weird stuff like make the TEE run an AMM pricing model, for example. Yeah, in conclusion, design space is huge to do trust minimized marketplaces. The tech here is ready. Dev tooling will continue to only get better. And instead of only bring Ethereum to the real world, I think it's time to bring some of the real world onto Ethereum. Thank you, and that's it.
Thank you, Richard. Do we have any questions? Shy crowd today. Come on, guys. Graphic of the P2P marketplace. I don't even know if you have the ability to go back in slides.
Yeah.
Oh, sorry, is this better? Yeah, if you can't go back, that's okay. I was
Yeah.
just going to ask something about it, but it doesn't matter.
Yeah.
I don't think we can. Maybe you can just talk to it. Okay. Any particular use cases you're most excited about, like in terms of future of peer-to-peer marketplaces?
I think there's just a lot of ideas out there. Like you can put almost any internet data on chain and use it. Trade any kind of Web2 asset or even data, and anything that you think has value on the internet, you can kind of bring into on chain to do cool stuff with.
Yeah, love to see it. I mean, just like you said, Ticketmaster, I think a prime example of just like marketplaces that are absolutely using monopolistic pricing to just gouge consumers in what is becoming, a very much frictionless process to do straight peer-to-peer. I guess a question, have you seen any regulatory issues? How are you thinking about navigating that?
Yeah, I think there haven't been so far. I think P2P is a legally, I guess, gray area kind of thing. You are allowed to transact with like your peer. For example, Facebook Marketplace is like a huge P2P marketplace. And we're just basically enabling the coordination of that to be easier through on-chain means on Ethereum.
Totally. All right. Thank you, Richard. Appreciate it. Give it up.
Thanks.
Okay, welcome back. Next up, we got more talks on hallucinated servers. Very exciting new developments in the applied cryptography in the prog crypto space. And here to chat about it is Brian from 0x Park. Please give him a warm welcome. Brian.
And I'd like to thank the organizers for putting on this very exciting event here in Thailand. Anyway, I'm with 0x Park. We're a research foundation studying applications of all sorts of modern, new, exciting tools in cryptography. And, okay, there you go, 0x Park. So we're a research foundation studying applications of modern developments in cryptography. And today I just want to take you on a very quick tour of 4 of those cryptographic primitives that promise to have some really exciting applications, and tell you where these tools are as far as being available for development. So first off, this is just a giant tech tree of all sorts of different cryptographic primitives, things you can do with cryptography. So it starts out at the bottom. We have plain vanilla cryptography, things like encryption or digital signatures or public key cryptography, which have been around a long time. They're well established. We all know how to do them, and we use them in day-to-day life. And as you go up, you get more and more advanced tools. The arrows mean reductions. So for example, if you have FHE, then you can use that to get encryption. FHE is kind of strictly stronger than encryption. So as you go up the tower, you get stronger and stronger cryptographic tools that you can do more and more things with, that unlock functionalities you didn't have before. So I'm going to, for the rest of this talk, I'm going to focus on 4 of these primitives. ZK snarks. A snark stands for proof, so ZK snark stands for zero knowledge proof. Multi-party computation, fully homomorphic encryption, and then at the very top of the tower, program obfuscation. So with the time I have, I just want to give a quick introduction to these tools and say what you can do with them. So let's start with ZK snarks, also known as succinct zero-knowledge proofs. So mathematically, a zero-knowledge proof is a way to prove you have a solution to a system of equations. Right? F of x equals 0 kind of represents a system of equations. X could be, I don't know, 1,000 variables, or a bit string of length 1,000,000 or something like that. And then f is any sort of function you could apply to it. And so f of x equals 0 is just a system of many equations and many variables. And if we have some system of equations, then I can prove to you that I have a solution to that system of equations. Using some sort of algebra, I can prove it to you without revealing anything about x. And the proof can actually be much shorter than the system of equations. So I could have 1,000,000 equations and 1,000,000 variables, and I do some sort of cryptographic something, and I somehow encode my solution as just maybe a couple of kilobytes. Even though the solution itself was megabytes in size, my encrypted solution is a couple of kilobytes. And you take my encrypted solution, you can verify it and be convinced with cryptographic security that I have a real solution. But you can't learn anything about it. You can't learn anything about the values x. Unless I choose to reveal. I could reveal some part of x or all of x if I wanted to, and then you would learn what I revealed, but nothing else. So this is why it's called a zero-knowledge proof. I can prove I have a solution, but you don't learn anything about it. Now you might think, well, systems of equations, those are kind of, well, we only see them in algebra class. What good are those? But x could really, you should imagine x could be any kind of bit string, anything that can be an input to a computer program. And f is any function that you can write in code. So for example, if there's some public key somewhere, I can prove that I'm the owner of that key. I can prove to you that I know the private key corresponding to the public key without telling you the private key. Or for another example, if I have some sort of message that has a digital signature on it, maybe it's an email and it's been signed by the email server as part of some email protocol, then I can redact that message and reveal only the parts of the message I want. And yet you still get this guarantee that I'm showing you a legitimately signed message. These zero-knowledge proofs, we know how to do them. They're kind of widely used in practice. There's a cost overhead. Compared to just redacting a message is very cheap. If I want to prove to you that this is an honestly redacted message, well, that's a little bit more, computationally, a little bit more expensive. You can do a simple zero-knowledge proof on a mobile device. You can do a fairly substantial one on a laptop. So this is maybe the easiest, the simplest of the four technologies. So algebraically, I said zero-knowledge proofs are about solutions to equations. Conceptually, you get kind of a different picture. Conceptually, it's about data integrity or about verifiable computation. Maybe I did some computation for you and you want to know that I did it right without having to go through all the steps yourself. A zero-knowledge proof lets you check it more efficiently. Or maybe I have some cryptographically signed data, some attested data somehow. I apply some transformation to it, and I want to convince you that this transformed data is still legit. So I think of zero-knowledge proofs as being about integrity and trust. Okay. Let me move on to two related primitives, multi-party computation and fully homomorphic encryption. And maybe in the interest of time, I'll focus on the first of the two. I'll focus on MPC. The basic idea behind multi-party computation is imagine each of us has some secret, some number, some name, some I don't know what. And we want to compute something that's a function of all our secrets. So maybe we want to, we want to find out how many of our secret numbers are bigger than 100. Or how many people in this room have the same name. But nobody's willing to reveal their secret. We're not just going to reveal our secret numbers or share our names. So abstractly, you have some function that takes, how many people do we have in here? 30? 40? You have some function that takes 40 inputs and gives an output. And you want to learn the output to the function without anyone revealing anything about their inputs. Besides, of course, what you could learn from the output. So this is what multi-party computation lets you do. Multi-party computation also, it's been around a while. It's been used at least once in practice. It's a fun story, so I'll tell it. There was a Danish beet auction. The beet market in Denmark is, I think the word is a monopsony. You have a single buyer and a lot of sellers. You have a lot of small-time farmers, and then there's the one giant beet conglomerate that buys up everybody's beets and turns them into, what do you make out of beets? Beet juice? I don't know. Whatever it is they make. So you have the one buyer, and they want to run an auction to figure out what's the price that they're going to buy the beets at. But all the farmers are a little bit afraid of the one big buyer, because if the one big buyer finds out how strong my financial position is, well, that's really dangerous. So each farmer has their price, and they're not really comfortable having the sort of public auction where the people running the auction can learn their price. So they ran, maybe 15 years ago in Denmark, they ran this giant multi-party computation with all the beet farmer prices as inputs. to set the price of beets in Denmark. Anyway, that's the sort of thing you can do with MPC. It's like ZK, like zero knowledge proofs, it's doable in practice. It's definitely a lot more expensive than doing the computation the naive way, where we all kind of share our inputs or send them to a central server. But it's doable. There are software libraries that will let you do this. So what does multi-party computation buy you? It's a different kind of thing from a zero-knowledge proof. It's a sort of collaborative kind of a tool. It's something that lets you collaborate while still preserving privacy. You don't want to give up all your secrets. You only want to give up a little bit of your data to just enough to be able to do whatever it is you want to do, set the price of beets or find out how many people have the same name or whatever it is. And MPC lets you do that. While we're here, I want to describe the image of a hallucinated server that this talk is based on. So imagine you're a bunch of people, I don't know, you're a billion people, and you want to set up a social network. So one way you could do this is you could find a Zuck somewhere who could say, okay, I'm going to open a big company and run a big server in California, and everybody's going to send their data into my server, and then I'm going to do whatever it is Facebook does that's so useful to people. I don't know, recommend friends to people or tell people what their friends are doing or what they're interested in or whatever it is. In other words, everybody has their billion inputs to the server, which they kind of like to keep private. And the server takes everyone's billion inputs and does some sort of computation on them. I don't know what, something depending on who you tell it your friends are and what you tell it your interests are and whatever else. But the server runs some kind of computation, and then it gives you your output. Well, this sounds an awful lot like a multi-party computation. And so if you could do multi-party computation at this scale, then these billion people don't need a Zuck. All they need to do is the billion of them kind of write the code. Okay, someone still has to write the code. But they agree on the program they're going to run, the social network program, and they all run it as a multi-party protocol. There is no server. There is no one data broker that holds everyone's data and does the computation. So if you have MPC, this group of people can get together and hallucinate a server. They can kind of dream up a server just by using an MPC protocol that has the same functionality as a server. So that's why we call this a hallucinated server. Very quickly, fully homomorphic encryption is another tool. It's very different on the surface, but it gives you the same kind of affordances in the end. The idea behind fully homomorphic encryption, FHE, the idea behind FHE is I can encrypt some data and give it to you. And then you, even though you can't read it, you can operate on it. So imagine I have some X, my data is X, you have some function, some F. You can kind of operate your F on my encrypted data and give me back a thing that when I decrypt it, it's F of X. So here, I have X, you have the function F, and you never learn anything about what's inside the data. All you do is you blindly apply this F, and you hope when I get the answer back it means something to me, because it doesn't mean anything to you. But again, it's a collaborative computation sort of tool. The sorts of things you can do with FHE and the sorts of things you can do with MPC are broadly very similar. If you've seen a frog game, at Xerox PARC we put together some game involving frogs. That relies on some sort of combination of these two things, some multi-party, fully homomorphic encryption. FHE is somewhat slower than MPC. There are implementations out there. It just takes them a very, very long time to do anything at all. So probably you should imagine you could maybe add 2 integers in a fraction of a second, but anything more complicated than that with current technology is going to be a little sluggish. And again, if you've seen the frog game, you might have noticed. Now we're going to move on up the tree, beyond the realm of the practical, at least the practical with current technology, and into areas of active research. So at the very top, I promised you indistinguishability obfuscation, or I might call it program obfuscation. And what is this? This simply says I can take any program I like. Again, you should imagine F is some source code in your favorite programming language that computes some function. And I can obfuscate the code. So it doesn't change the functionality. The obfuscated code still does the same thing as the original program. But you can't learn anything about how it works just from reading the source code. You can feed inputs in, you can get outputs out. You have the source code so you can see what it's writing in memory and debug, right? You can see what it's doing. But you don't learn anything about my original implementation of F. So this seems kind of mysterious. What do you do with this? I'm missing a slide here. But the sort of thing you could do with program obfuscation is you could hide data inside of a program. For simple example, I could hide a private key to sign a message or decrypt a ciphertext or whatever it is. And so I could write a program that says, well, I'm going to read the message first. I'm going to take a message and I'm going to see if I would approve it. And if my program approves the message, then my program can sign it, issue a digital signature using my private signing key. And I can give you this program, and you can sign any messages as long as the program approves them using my private key. But what you can't do, because it's been obfuscated, is you can't learn my private signing key. Because that's the whole point of obfuscation. You don't learn anything about F other than its inputs and its outputs. So you feed in a bunch of good messages. You get a bunch of valid signatures. You try to feed in a bad message. Well, there's nothing you can do. If you had the original source code to F, of course, you could just read it and reverse engineer it and see, oh, look, there's the variable called private key, and well, now my signature is useless. But if I can obfuscate that, well, then I have this program that more or less acts as an autonomous agent on my behalf. I can send the program out into the world, and it can do anything for me, whatever I ask it to do. And I can trust that the data inside can't be breached. You can't learn my private key. You can't learn whatever else I have in this magical cryptographic orb. So that's the good news with program obfuscation. The bad news is, well, we don't quite know how to do it yet. There are obfuscation protocols out there that are proven secure that would run in, I don't know, millions or billions of years. There are proposals out there that are definitely faster that you can implement that will run and terminate in a real amount of time. But we don't really have any reason to believe they're secure, and we kind of suspect they might not be. They're protocols from a decade ago, and they're all broken now. So this is an active area of research. There's a lot of new cryptography that's come out in the past 10 or 20 years that makes us think that there's a lot of promise for obfuscation in the near future. But as of now, this is the pipe dream. This is the holy grail at the very top of our cryptographic primitive pyramid. Anyway, I'll stop there and open it up to questions.
All right, thank you, Brian. Looks like we have a question of, if computation is not a problem, what would the world look like with ZK, FHE, and MPC.
What would the world look like if we could just use these things and computation is not a problem and we can deploy them in practice? Well, it seems like it's a lot easier to manage data and computation. So when you had the internet gives you very strong communication. You can communicate with anyone, anywhere, very, very quickly in ways that we couldn't really imagine until it happened. So you have very reliable communication. With this technology, ZK, FHE, MPC, all this stuff, you'll be able to build programmable functionality on top of that communication. And it's hard even to imagine what you could do with that beyond these vague visions of maybe we could hallucinate some sort of server. Right? We could do things on a peer-to-peer level, do computations peer-to-peer without having to depend on a centralized server, a centralized service and the APIs it provides.
Right on. And yeah, you mentioned the frog game. If you folks haven't yet, highly encourage you to go check out the frog zone on the ground floor to see one of these implementations in action of actually using MPFHE to hallucinate a server and actually allow people to play a game where these programs are computing on this private state. Really incredible. I'm curious, yeah, like maybe on just the MPC and FHE side, what do you see as the current big challenges? Like, is it on the research side? Is it just engineering and optimization? Or where are you focused on?
Performance. So the problem is performance, and I think we need more research. It's the sort of place it looks like ZK, like zero knowledge proofs looked maybe 10 years ago. There's a lot of room for research to improve performance. I wouldn't be surprised at all if a few years of academic effort got us a 10-fold or a 1,000-fold improvement in performance that makes a lot of things more doable.
Exciting. And another question, would I/O be imaginable on Ethereum? And if so, yeah, what implications might that have?
What would you do with I/O? So how would you combine I/O and Ethereum? I guess you would take a program and obfuscate it and put it in a smart contract. And so now you have a smart contract that can act as your autonomous agent.
So potentially, like you mentioned, like storing a private key on a smart contract might enable some use cases that for developers out there who may have tried to build some applications realize, oh wait, I can't just put this in the public state because people might take my money. Seems like it enables some interesting use cases there, for sure. Cool. Well, yeah, Brian and the ZeroX Park team, like I mentioned, they'll be down at the Frog Zone. Encourage you to go check it out, get in on the Frog Crypto Mania, or talk to them and ask questions if you want to learn more. But thank you very much, Brian.
Thank you.
Cool. Okay, welcome back. We got our last talk before lunch. Another presentation on the applied cryptography track. We got Richard from Xerox Park, one of the people behind the frog crypto mania that's been happening this week. You're going to want to stick around to the end. I hear there's a nice little frog surprise. So get excited and stay tuned. Let's give it up for Richard.
Hello, thanks, Sam. As you said, there's going to be a bit of a surprise for y'all. I know it's getting close to lunch, towards hungry times, so we'll make sure it's worth the wait. Yeah, I'm Richard. I work at Xerox Park, and I'm here to talk about Zupass. But before I get into Zupass, I actually want to first talk about Ethereum. We are at an Ethereum conference, and one theme that we've seen popping up over the past, I think, few years, especially in few months, even more specifically, is how do we get to things that people can use, right? Not just interesting ideas in theory, but as Vitalik says in this blog post, this is a decade where we actually have to build things that are useful. And I think there's been a lot of really exciting directions in the stable coins, the prediction markets, DeFi in general, right? I think that kind of world has been really exciting to see things come to fruition. But there's this broader world of, the promise of Ethereum beyond just, more ways to use money, more ways to increase financial access. There's this vision of computing being a different sort of paradigm because of decentralized technology, because of cryptography. So I think that's where I want to focus on, and I want to approach specifically this problem from the usefulness lens. And I think one interesting thing about Devcon and Ethereum conferences is that conferences can serve oftentimes as ground zero for new technology breakthroughs. There are early glimpses of what's possible. You have a bunch of sort of really bought-in, excited people, caring a lot about coins or frog hats, right? And it's a chance to sort of show what you can really do in a short amount of time. And two examples that people might know of are, one is this 1968, this guy, unknown professor from Cornell, Doug Engelbart, introduced modern computing, the personal computer, the mouse, the spreadsheets. It was all hard-coded. There was no actual product, but it was a sort of vision for researchers at Xerox Park and for Bell Labs and these folks to sort of actually innovate and build the thing that we now know as probably the most important industry of the past 50 years. The one on the right is Twitter at South by Southwest in 2007. Just another example of how we've seen early glimpses of social media, and it's changed our lives for better and for worse. So I want to start with this prompt, which is, what did going to an Ethereum conference feel like 5 to 10 years ago? And I actually wasn't part of the Ethereum ecosystem 5 to 10 years ago, so I'm just kind of guessing, but let's play along. And let's target it from the technology perspective of the conference. So you're at a conference, there's a few things, features or products that are important, right? There's ticketing, you need to be able to get in. There's communications, I want to meet people. I want to sort of expand my network. I want to sort of hear what's going on. And I want to go to talks, right? And you can roughly map this out in a data way with, you have all these sorts of objects. For example, you have your tickets in this ticketing server. You have communications and messages in another. You have some other stuff going with talks. It's pretty standard sort of thing you do for any kind of web application. And one thing I want to explore, this is 5, 10 years ago. What does it feel like in 2023? I chose last year because this year's a little different. But it's basically the same picture. The one thing that's changed is, now we can buy tickets with Ethereum, right? And that's pretty amazing and powerful how that happened. But it feels like we could be doing a lot better, right? Not because we're trying to make the best conferences, but because conferences are where folks from the community should sort of see what's going on at the bleeding edge. So basically nothing has changed much. And what could it look like in the future, right? What could the reality of being part of the Ethereum community look like in the future? This is a bit more complicated of a diagram, but essentially, all those pieces of data, right, that are being held in servers oh, why aren't they being held by me, right? And not just for privacy reasons, but also for the fact that I can port them across different applications. Applications themselves could live as smart contracts, right? Be publicly auditable, be composable, all that good stuff. And I think here's my take, which is like, if we can't do this, if we can't actually just run the biggest and most important event on Ethereum in a few years, like something's really wrong, right? And I think that's sort of a red flag almost. And here's one exercise, which is like, what would it actually take to run Ethereum conferences on Ethereum, right? First off, what are the benefits? I think most people here are familiar. I won't sort of spend too much time, but you have all these sorts of like data ownership, composability, permissionlessness. Everything's verifiable, right? And this is powerful because you can have these sort of new behaviors that emerge that are only possible when you have very strong guarantees. Now, what's holding us back, right? Yeah, basically all state is public. That really sucks. You can't really have any sort of secrecy or privacy that you want sort of just because you want to build. Organizers don't want, or I don't want somebody else knowing my information, right? It's not sort of a ideological thing, it's a very practical thing. Most of the world's data is still on Web 2. It's not very portable yet. Building in Solidity is still really, really hard, right? Computation's expensive and high latency. I mean, rollups make this better. The resources in development have made the third point better, but I think it's still pretty tough to build an actual like high load application on Ethereum. Yeah, so I think at this point it's still too high a friction to go all in, but we don't have to go all in, right? I think there's this tendency to be like, oh, it has to be fully decentralized or private, or it has to be nothing. But I think there's ways to sort of like 80-20 this, right? And the question is like, how do we get to sort of 80% of the benefits? There's a lot of clicks. With only 20% of the cost of using this tech, right? And one thing that I'll note is that things like Zupass, among other really great applications in the past few years, have made this more possible, right? And through different types of, through certain data formats, but also through encouraging a certain type of application. So put simply, data is not stored directly in Ethereum. However, it's easily portable to Ethereum because it's cryptographic, right? And not only is it portable to Ethereum, but it's portable to basically anything, because you just need to be a person or a computer that speaks math, right? It's kind of the universal language. And just to kind of go through some vocabulary, my colleagues will probably inundate you guys with these phrases more later on, but a pod is essentially, you can think of it as a JSON that has some proof attached to it. It's a statement about the world. Zaps are these things we're calling, which are applications that operate over pods, and they connect to your Zupass, which is a store for pods, and it stores and also manipulates, and these are all stored locally. You might hear this thing called a GPC. It's basically, it stands for General Purpose Circuit. Essentially, it's a kind of a ZK FPGA where you can sort of configure a circuit or a proof through JSON rather than having to like write CIRCOM or learn functional programming. And you can make proofs that are really, really efficient, like 2 to 3 seconds on a mobile phone. Okay, so some examples. Pods, so your Devcon ticket, which I'm sure all of you used, maybe struggled with a bit, but and other sort of events in the Zuzulu ecosystem, which is where Zupass got its name from. For example, Edge City, ZooConnect, which was before DevConnect last year, your frogs, and other pods from applications like questions and answers, like Meerkat is one example, which will be used at the end of this talk, that QR code to the right there. In terms of Zaps, we have, there's just a lot of stuff on this page, but briefly, right, there's things that help with communication, like the Telegram. There's things that are just fun games in their own right, like Frog Crypto, and actually have their own extensions, right, like the necklaces, these guys, and apparently there's a game where you can juice a frog and put it on chain. Just hearing all kinds of stuff now. And then also faucets, right? So I think the Mekong faucet came out, and that's using Devcon gating. So all kinds of different things are highly, all kinds of really complicated logic is highly flexible because you're essentially just writing a TypeScript app that checks some cryptography rather than having to write a whole smart contract. And given these sort of like new technologies and capabilities, right? What does feeling Devcon go like? What does going to Devcon feel like? It feels a lot like, well, I have some application that stores my own data. It's issued by trusted services like Devcon, but I can now use that across a whole bunch of different zaps. I can get, and not just tickets, right? I can get my frogs, and those frogs are useful for all kinds of like extension apps, the juicing stuff. This another one where you can sort of like put your frog in a lab. There's like more gated chats, right? And I think this is just very, very fascinating and interesting of a way you can sort of engage with an event because you have this technology where everyone has software that can process pods, they can make proofs, and developers can build applications that interact with these. Okay, so here's where we get a bit more experimental, and if we project this with high uncertainty bars, because no one can know the future, what does this look like? What does this mean beyond just, okay, it's a cool, fun conference experience? Well, I think that if we sort of just literally take each of these boxes and do like the more serious version of it, right? Check-in is basically how customs or traveling across any sort of like high, high stakes reputation thing where you're going through and you're checking that you are who you say you are. That's essentially what's going on with ticketing, right? And it carries over to the high stakes things like I want to enter a country or I want to like do something that's highly restricted. Messages, every email has a DKIM signature and that can be portable on chain, or they can be portable within this sort of cryptographic environment. Voting, that's been said a lot before, so I won't go into it. Faucets, right? What's the sort of bigger version of a faucet or a bank? It's an actual bank, right? And then I think this direction of apps building on apps is reminiscent of two things. One is like in the early Facebook days, there would just be a ton of like Facebook games, right? I mean, same with Twitter. There was a Twitter API, and there's like all these kinds of like aggregators, or there'd be like, check my Instagram followers, do some sort of like, query over them. I mean, TikTok, there's like the remix behavior where someone can sort of like take a TikTok and like build on top of it, and you get sort of like recursive TikToks, like 6 down. And I think like these kinds of things are really fascinating. I think you see it in DeFi as well, right? But it extends far beyond like derivatives and financial applications. Okay, so this is all cool, but how do we actually get here, right? Because I think like we can all dream and sort of imagine, right? But I think what's important is like what needs to get done. And we have 3 main ideas right now and directions that are, I think, pretty concrete. So the first one is we just need to get better technology, right? There's been a lot that's changed. So Zupass was first launched in 2023. It's built in 6 weeks, which is crazy. There are like all kinds of crazy stories that happened from there. But basically it was built that assuming that, hey, we have what we have at March 2023, and so many things have changed, right? So pods was not even a thing until early this year. And now we have a lot of developments in recursion, which have made so many different kinds of things possible. You can basically make proofs of proofs of proofs in sort of arbitrarily long chains of proofs in under 2 seconds on a consumer laptop. And we have not adapted Zupass yet to this new paradigm. And that gives us the ability to also work with data that's not so nicely like ZK friendly. So like ZK email, ZKVMs, they take really long and they're just not very feasible on phones right now. But that's something we can actually just solve given how much things have progressed over the last year. Yeah, I think we want to continue to improve performance. We have, for example, we've done a lot of open source fixes and feature work with Snark.js and Semaphore, which are two of the libraries we depend on. And a lot of it is because both of these libraries have not really experienced the level of load that before something like Zupass emerged, right? Like, I'll give you one example, which is there's this memory leak issue in Snark.js that caused people's screens to freeze up, but it only happened when they tried to make really big proofs, and it was a really simple bug. We just sort of, it was allocating too many pages. But my point is, like, there's a lot of low-hanging fruit because a lot of this stuff has not been tested in production, even though these are sort of like the the classic libraries you use. And there's all kinds of like new updates too. There's delegated proving, which seems to be the direction of a lot of the future of client-side stuff. Essentially, where you blind it on the client and you send it to the server to make it succinct. There's new APIs like WebGPU, native proving, which has been exciting, and more of a reason to actually get a mobile app. Right, so things like MoPro and explorations of alternative kind of Zupass or pod clients. For example, there's one experiment we've been doing on Mac native, with a Mac native app, and that allows us to do a lot more like complicated proofs than you can on just your Zupass, which is ultimately bound by the web browser in your phone. Okay, yeah, we need to get more valuable data into this ecosystem as well, right? We can't, frogs are fun, conferences are fun, right? But it can't just sort of stay in our little bubble. We have to really we have to actually go out there and engage with real world data, right? And I think there's passports have been talked about, but there's all kinds of other data that's highly valuable, right? And I think this is where we're kicking off conversations with builders who are working on this sort of like import problem, right? How do you take data that's either cryptographic or not and import it into a format where it can be used in this way, right? TLS Notary and ZKEVM, I think, are the great examples because there's just so many emails and websites out there. But I think what we want to focus on is how can we sort of take these new imported data and find sort of a use case that makes sense, and then also let devs build further applications on top of this, right? How do we enable the frog crypto of something beyond Devcon or an Ethereum conference, right? That's still an open question that I think will be very interesting to solve. Yeah, I think that's where partnerships with universities, governments, financial service providers, I think this is still, it's starting to get to the point where this makes more sense, right? There's a lot of cool stuff you can do at universities, right? People want to make apps at the Stanfords and the sort of Berkeleys of the world, and they want to make social apps, dating apps, and this is sort of like a great way to get off the ground with a lot of these new technologies. We can sort of work with portability of social media, or Ethereum has been one, but also Farcaster, Blue Sky, X. There's all kinds of directions, and this is not a complete list by any means. Oh, wrong button. Cool. And then last is we want to empower, this is Devcon. We want to empower developers to build the most interesting apps and the most powerful ones. So, here's an example of how you can sort of insert a pod to somebody's Zupass in basically 5 lines of code. We try to make these things very simple. We try to make these things very, at the end of the day, we're pragmatic, and we want to ship a lot of things. So I think this has been a really, we spent some time basically in the past few months rushing together an SDK that, so that someone can actually come in and build a Zap without much guidance. We will have a workshop on Friday where we'll go over and just literally build it together. You can build frog battling, frog, dating, or whatever kind of app that comes to mind. Yeah, and crucially, I think no cryptography experience is required because a lot of what we're doing with these libraries is focusing on how can you just describe the behavior you want, and then we'll take care of the actual implementation. And yeah, there's some documentation, pod.org. It's 6 letters, easy to remember. And we have a Telegram group as well. We haven't shared it too much publicly because we're worried of spam, but I think everyone should join. Everyone should ask our developers with questions and help us help you guys figure out what to build. Yeah, some upcoming sessions from my colleagues, and then crucially tomorrow we're going to have a full day of programming. There's going to be some cool keynotes in the morning, and then workshops in the afternoon, right? So that workshop with building zaps with pods at 2:15. And as promised, here is a froggy surprise. I'll just let you guys figure out what's going on, and that's all.
All right. Thank you, Richard. Excited to see what zaps all you folks build out in the wild. Looks like we got a couple questions. When native mobile app?
Yeah, great question. I think we've probably said soon, like too many times. I think we're really excited for, how fast you can get with native proving. Like Rapid Snark and MoPro have just been, really exciting to see the progress. I think there's a few things. Most of it is honestly just, we're a small team and we, have to sort of. I think if we had a lot more people, if we had a very strong sort of like, mobile direction, that would be something we'd certainly do. I will say 2025 is a great time to, we have already explored a native Mac client. So I would be very surprised if there's no native app next year, but don't quote me on that.
Looks like a question around breaking down parts of the app. Parts of Zupass built on primitives like Snark.js on Semaphore versus what is driven directly by Zupass.
Yeah, it's a good question. So I'll separate Snark.js and Semaphore. So I'll talk about Semaphore first. Semaphore is, at least the latest version, the V4, is essentially a key pair, which is super useful for us. And essentially, a Semaphore identity is a Zupass identity. They're one-to-one. And it's what you use for signing pods. It's what you use for also if pods are soul-bound to you, right, or watermarked to you, we put your Semaphore public key in that pod to signify that. Snark.js is used for proving. It's mostly for, if you remember, GPCs. It is, I think, still the fastest web-based library that we've found to be reliable enough, although we're very open to sort of change it. It's crazy because it was built mainly for educational purposes, but now it's being used for huge use cases. Yeah, and a lot of the rest of Zupass functions similar to a traditional web app. I think the pods being stored locally rather than being stored in the server is a really big difference.
And looks like curiosity around, Zupass building this data wallet. Is there any plans for association with an Ethereum wallet, I'm guessing, and or ZK email like functionality or authentication?
Yeah, we're really excited about, we've been really excited about, I think, all of the sort of ZKX, movements, right? TLS Notary had put in this as well. And I think, we finally have the technology to actually do this. It's pretty crazy, but with these things we're terming pod 2, right? We essentially, anything that has a verification function, which is any cryptography really, can be put into Zupass. So I think this is something we're gonna, it's gonna happen, and now we finally have the resources to do it.
Love it. Got some more questions. Sounds like people should show up at the workshop tomorrow. But curious, integrating pods with traditional Web 2 stuff, what that might look like.
So one interesting thing that happens for Frog Crypto is that we created this new data format called a PWT. It's a pod web token. JWT is JSON web token. So pod is essentially a superset of JSON. It can also be serialized to other formats, right? But anyway, as an aside, just to point out that it's very easy. It's almost like asking, is JSON compatible? It's mostly a serialization format. with some opinionatedness around like how do you verify the data. But yeah, these are all like very easily possible because they're cryptographic sources of identity. At least JWTs. I think OAuth, and I'm not familiar with OIDC, but there are ways to import those over to cryptographic data types, for example, with notaries.
One last question I see. Hi, can you go back to the Frog QR code page again, please and thanks?
I mean, I don't think I can.
Unable to do it.
Unable to do that.
It was there, it was gone.
broken.
Those frogs are slippery.
Yes.
All right. Thank you very much, Richard. Yeah, I encourage you guys to go check out the workshops tomorrow to learn more. Let's give it up for Richard. I think that is for lunch. We're going to take a 1-hour break. We'll be back here at 1 p.m. with more programming. So enjoy lunch. See you guys soon.
All right, hello everyone. Good afternoon. Can I get everyone seated, please? So next, we are going to kick off this afternoon with a very interesting panel on multi-party FHE for multi-party privacy. And our panelists are, hopefully I can pronounce their names correctly, Edward, Gubsheep, Jeremiah, and Veronica. Let's welcome our panelists onto the stage.
All right. Let's go ahead and get started. Welcome, everybody. Hope folks are not too sleepy from lunch. Thanks for making it out here for the multi-party FHE for multiplayer privacy panel. To introduce things, I'm Gubsheep, and I will be our host of the panel for today. And I'm delighted to introduce our three panelists as well, three incredible cryptography engineers who have been working on various topics in programmable cryptography over the past several years. We have with us today Jamajaya, who is the founder of Gauss Labs and the creator of the Fantom Zone fully homomorphic encryption library. We have Edu, a researcher and engineer at PSE, who was one of the first contributors and developers on the ZKEVM project. That's the original ZKEVM project. And we also have with us Veronica, an open source developer who has worked on everything from consumer-facing crypto products at Coinbase to frontier cryptography prototyping alongside organizations like the EF and 0xPark. So the title of this panel is nominally about multi-party fully homomorphic encryption, but as with many things in this fast-moving world of programmable cryptography, and as you might have heard if you came to one of the other programmable cryptography panels earlier in this week, this term is largely a placeholder name for a set of concepts that we don't fully know yet how to describe or how to use or how to even think about yet necessarily in the clearest ways. But I want to start off by introducing this term itself because it's sort of been one of the best anchors we've had emerge in the past year for describing some of the things that have emerged from the recent world of research and development around these concepts. So maybe for starters, I'll direct the first question to Jay here. Can you tell us about MPFHE? So this isn't a term that, as I understand, this is not a term that actually is conventionally used in the academic world of FHE. And what do we mean when we say multi-party FHE? You know, what distinguishes that from fully homomorphic encryption? How do we sort of think about that prefix in this context?
Well, the way I would think about multi-party FHE is it's a way of doing multi-party computation using fully homomorphic encryption. And the advantage of this approach than taking the traditional ways of doing multi-party computation is, in this case, the computation is offloaded to the server. If you take a traditional approach to multi-party computation, let's just say secret sharing scheme or Yahoo's gobbling, you'd have to pay a bandwidth cost. It is not the compute that is bottleneck in that case, but you have to, upload things and send to the other party. The difference between multi-party FHE and the normal way people think of FHE, which is fully homomorphic encryption, is that in the single-party FHE, where it's a single-player game, a single person holds a secret key and then encrypts everything, sends it to the server. Server has some function that it usually wants to keep a private, let's just say a neural network. And the server would evaluate that neural network and send the output to the client back, and the client can decrypt it. But in contrast to this, in multi-party FHE, the secret key, which was just held by a single client in single-party FHE, is now split among multiple of them, so that individually no one can decrypt the output. Only when all of them come together, they can decrypt the output. And that's the difference between single-party FHE and multi-party FHE.
Cool. So multi-party FHE somehow exists in the intersection of the best of what we want out of multi-party computation as well as fully homomorphic encryption?
Yes, because it's sort of like trades of bandwidth cost that the client needs to pay in traditional MPC with compute. So you have higher compute, but we know how to solve higher compute instead of solving a higher bandwidth requirement problem.
Cool. So maybe one thing that I also want to dig into a bit is this idea of, so we have this contrast with MPC, which is that we can take the bandwidth costs down. In terms of the contrast with FHE, as I understand it, a lot of what's going on with trying to introduce this term, or when we think about related things like obfuscation, is to also catalyze a mental model shift in how we think about what FHE is good for. So I think FHE is actually a pretty new topic for all the panelists. By new, I mean on the time scale of kind of 1 to 2 years. But a lot of us have heard about FHE as this technology that has been, this wild DARPA project for a very long time. How did you guys think about FHE before you started embarking on the most recent research journey, and how has that mental model shifted now in the context of MPFHE?
Yeah, I think like when I first heard of FHE, it's like about 10 years ago in college, and then people say like, okay, the first time I heard about it, I think it's magical, because for most people, when you think about encryption, you think about hashing. You think about, okay, you put your input there, it's like you come out with like a string, and it's kind of garbage. And now you kind of like have a piece of string, garbage, and then you add to another piece of string and garbage. For some reason, it preserves like the addition. You can somehow decrypt it and then get a result. So for me, it's kind of like really magical. But around that time, people were telling me like, it's like 1,000,000 times to 1,000,000,000 times slower. And then, I just feel like it probably wouldn't be relevant for me. As a software engineer, I just moved on, never thought about this. Until like, we started experimenting on stuff this summer, like build on top of JS library, Fantom Zone. And then I thought, okay, this is something actually possible, and then you can use it for multi-party computation. So yeah, it's like a really magical experience for me.
Yeah, I think I also learned about FHE first around 8 or 10 years ago, just like Veronica. And it also felt quite magical, but I found the technical side of things more interesting. Because if you think about having encrypted data and being able to do arbitrary operations on top of that while preserving the data, sounds really awesome. But then on terms of applications of traditional FHE, I think I got less excited about that, because it's a lot about offloading computation from like a weak device. But in my opinion, like these devices are no longer weak. Like we get more power every year on our phones. So my first question is, why can't I just run the same computation on my phone? Or maybe not today, but in 1 year, maybe I think people are trying to run LLMs on phones right now. So to me, there was a paradigm shift with the introduction of multi-party, which is, it's not something that you can, it's not just offloading computation that you could already do it on your phone and then you do something to accelerate. Now it's computing on private data from multiple people, which is something that you could not do before. So that was pretty awesome.
Yeah, so to summarize, it kind of sounds like there's been 2 major updates in the thinking in the last couple of years. The first is more than just being this crazy theoretical technology. Someone can actually sit down and write an FHE library, write FHE circuits on top of that. It's no longer this pie-in-the-sky thing. And the second thing here sounds like our understanding of what FHE is even good for or useful for has shifted, with the introduction of this intersection with MPC and the idea that it's not about delegating computation, but actually about multiple people coming together to produce some joint output. So maybe, I'm curious if someone could give an example of both, maybe just to contrast what the world looked like when, I remember sometimes I would see a popular science article about FHE 10 years ago, and there'd be a certain flavor of application, which I agree with you, Edu, it just was not so exciting to me. But now the things that we're starting to see people prototype and build very early on these systems is qualitatively different. So I'm not sure if any of you have some examples here or can speak to that difference.
One really good example is live out there at the Frog Zone, where you have a global state in which each party has their own private state that no one knows. So you have a global state that sort of like composes of private states coming from multiple people, which is kind of interesting, which we did not like, which we cannot have with normal, well, I wouldn't say normal, but like things that we now consider normal, like zero-knowledge proofs, and so on and so forth. I suppose, do you guys have any other interesting use case?
Yeah, it's not a particular use case, but I think a lot of people have observed that smart contracts in Ethereum work with public data. And then I think many people learned about ZK and thought, can we use ZK to have private smart contracts? And the answer is most of the times no, because we need private shared state. So there are many applications where we want computation on private state, like, I don't know, Uniswap. Maybe there are particular solutions that can be built off ZK, but they need to be tailor-made for the particular use case. But multi-party FHE gives you a general framework to build these kinds of applications with shared private state.
Yes, so for me, MPFHE, it's like changed for end users, like I think it changed like my entire view about how I think about data. So like with MPFHE, like my default is like going to be, I want to share my data more. So just to give an example, so I normally when I meet like strangers, I feel like very awkward and very anxious. I don't know what to talk about. I just don't know like what to say to those people. I know some of you may not think so, but like a lot of us do. So one thing like in the past few days, like, you know, just going to those after parties, I'm just keep on thinking like, you know, what if I can just like upload all my data, my interests, books I read, like all my thoughts, my experiences, like on a server somewhere, and then like, you know, like everyone else also upload their information. And when I meet a stranger, like I meet Brian, and then it just pops up to say like, okay, you guys both interested in this, or like you guys have different opinions on this. So I'm like, okay, maybe I can talk about this, so I don't need to think about what to talk anymore. I think like in traditionally, like before like MPFHE, like if I want to do this, I mean, I have to write the code, of course, but I still have to convince people to upload all those information to my service. Like, how do I trust people to do that? Like, I probably need to start a company and like trying to build a brand and like maybe make myself like Facebook or Google, and then people start to upload their data. And then like, you know, like when I have those data, I might not want to have all those data because it's kind of like scary, like what if I leak people's data? And then I have to hire a bunch of engineers to like secure the data, and then, you know, I needed to have money, so maybe how do I make money like out of this? I might have to show people ads. So, you know, like a lot of things can go wrong like from there. But with multi-party FHE, I don't need to do like any of those things. I can simply like write my code, okay, and then like we can do this kind of matching or like a suggesting recommendation thing like peer-to-peer without going through all of those things. I think it's just going to like open a lot of like different use cases. Yeah.
So it sounds like one of the underlying themes here with what you all are excited about with MPFHE is this idea of multiple people coming together to jointly compute something, and without needing to rely on some other strategies. And you know, there's this first strategy of we can have someone build a company, build a business model, build a trusted brand around collecting everybody's data and doing those joint computations, and there's some problems with that. And then Edu, you mentioned something interesting as well, which was like, well, you know, we have Ethereum, we have smart contracts, we have ZK. Maybe a thought could be, can we combine these tools together to get what we want? And as you mentioned, this doesn't turn out to be enough. And what I want to do actually is, a lot of the folks in this room might be a little bit more familiar with ZK than FHE, and I know for all of us, we kind of came into this space as well through the ZK world as well. What is the right way to look at comparing ZK and FHE? What can they do? What can each of them do that the other cannot? And why is it the case that actually in the blockchain world, we've talked so much more and seen so much more progress in ZK over the last 5 years than in these other programmable encryption technologies?
I think one of the main interests from the blockchain industry in ZK has been focused on scaling, not on privacy. And there's a lot of economic incentives to solve the scaling problem, because you can have L2s that are pinned on Ethereum, and within these L2s, it's easy to extract, to monetize them because you get fees. But on the other hand, yeah, well, that's the answer I have why the blockchain space have focused mostly in ZK. And I think even in the ZK world, we have seen more scaling development than just privacy applications on ZK. That's my impression. So probably MPFHE gives you a different angle, and we still need to explore and convince people why this is nice.
I would say the programming model for multi-party FHE is still kind of unexplored. We were trying to build this Frog Zone game with Brian, with ZKEVM people, and we came across a lot of issues while doing that as well. You know, we set up 5 servers just for that game, by the way. We just set up 5 servers just for the game, by the way. So the programming model for multi-party FHE is still very unexplored. It's not as clear as ZK at the moment. The difference is that I can point at a few differences. For example, it's not all in multi-party FHE. I suppose the memory access model becomes problematic because the moment you sort of leak which part of the memory you're reading, it sort of like violates the law of privacy. Like you cannot do that. So you have to pay linear amount of time to actually retrieve anything from the memory. So that becomes a problem. What becomes better is that now you have, instead of just thinking in like single player term in ZK, where you have just one person generating witnesses on their devices and then just posting the proof somewhere, what needs to be done in multi-party FHE world is like you have to consider multiple people and they have a shared state and a private state within that shared state. And that is sort of a switch which took me some time to grasp over. I would also quickly answer the second question. I somewhat agree with Edu that there's a huge economic incentive to build use ZK for scaling, but I also think that blockchain world people are not that comfortable with, so usually the people that are using multi-party FHE or like threshold FHE in certain scenarios at the moment for blockchain, they have something called God servers. These are the servers that hold these secret shards that we usually put on in the clients. Blockchain people are not that much comfortable with it. And that is the tangible part of FHE. That is like what is possible at the moment. And what we need to do now is sort of like figure out a way around that problem, which is more like not tangible at the moment. Like people are not able to see a way around it, which inevitably leads to something called program obfuscation, which we can talk about later as well. So I think that it's not just about like there's a huge economic incentive. It's also because getting around this problem of God servers holding the secret shards is a challenge. It's more like a theoretical question at the moment than within the realms of like us right out of college being able to do all these things. So there's also a switch over there.
So maybe actually one thing I'll prompt here as well is it sounds like the reasons that you guys are mentioning are related to, on the one hand, there's the economic incentive for blockchains that drive ZK forwards, or at least ZK for scalability forwards. Not clear yet how far it drives ZK for privacy. And then on the other hand, there is ultimately this technological problem of can we make the idea of secret shards that need to be held by a bunch of people more palpable to different communities that could adopt this technology. But what that also kind of signals to me is there's a little bit of like almost like a social or a cultural aspect to that. What I'm curious about also is from a technological perspective or a theoretical perspective, is there an inherent reason why ZK needed to happen 3 to 5 years earlier than FHE? Or is it actually the case that we think it's more of a social, economic incentive, that sort of thing that's pulling this forward? In other words, could FHE, is there actually just a lot of low-hanging fruit that's waiting to be discovered, or is FHE inherently harder somehow?
I would say that with ZK, I think you need to solve a single piece, but with FHE, to be usable, you need to solve FHE, but verifiability, and figure out a way to spread among many users. So there are more pieces, and maybe it's harder to solve all these pieces together. And while we don't solve these pieces, we can have some examples or demos, but maybe not quite get there to this final solution that we envision.
I would say that in the more Web 2 world, FHE has received more attention than ZK, than our world where we sort of like inhabit. I'm not in a position to say whether ZK is harder than FHE or FHE is harder than ZK or so on and so forth, but I would say that it's more like a social thing as well. The cultural thing of us caring about this tool to make sure that we are delivering libraries and building tools so that people can use it easily, which is not often the case in the traditional world, like not the traditional, but like Web 2 world, whatever that is.
Did you have anything? I saw that you were picking up your mic a bit ago.
Oh yeah, so I think like, I'm not too sure about the theoretical, which is harder, but from like application developers' point of view, I feel like ZK, there's like less, it's more like a non-interactive. It's like, okay, you have like a approve a piece of something, and then you can give it to the verifier, and then for MPFAG, there's just a lot of like those kind of participants and the interaction happening. And as of now, like when we decrypt the, decrypt the output, there's still like aliveness. So that's like a lot harder to build like application around. So yeah, but one thing is quite interesting is like when I build like ZK applications, normally I would make the data, hiding the data by default. I would actually like just by default hide data. But with MPFAG, like I think like as an application developer, you kind of want the user to share as much as possible. So that's like another difference, yeah.
One more thing would be that I sort of, so there's only one way of doing FHE at the moment, if you know about it. Like there's just like lattices and ring learning with errors that you're familiar with, and you can only use that for FHE. There's somewhat hints that probably theoretically FHE is much harder than ZK, just a conjecture, no sort of like commitment to that. But I also think that it's more like a cultural issue where we are not coming with new ideas, and probably if we sort of like enforce ourselves, a lot of people are paying attention to this thing and find it useful, then probably we can come up with new ideas. Like the way we did for ZK, like for a long time we just had Grot 16, and then up come Plonk, and so on and so forth.
There's a lot of really great insights there. I guess one thing that actually I had not considered was the role of interactivity here. So interactivity played a huge role in actually making ZK snarks practical as well. The idea that the way a ZK snark or a general purpose ZKP used to work was you would have these two parties and they would perform some interactive protocol between themselves. We actually did have general purpose zero knowledge proofs that were interactive before ZK snarks came onto the scene. It seems like the really important thing that actually made this practical for developers is you have this one-shot nature where I can generate a proof, I can publish it publicly, or I can send it to you and you can verify it and we can get on with our application. So, it makes sense actually that the nature of interactivity here just makes it so much harder to reason about. You now need to do this coordination problem amongst all the different parties. I think that's a super good insight. I'm curious to double click into, Jay, some of the directions you were just gesturing at. From the theoretical perspective, what can we carry over from what we know from, I guess, the first branch or generation of programmable cryptography that we have really advanced. What carries over from ZK into FHE, or are we in a totally different world? How do we think about development in this space? Is anything even relevant, or is this like we need to go off and have some completely different kind of cryptography, think about some completely different kind of systems?
I would say that the programming models somewhat can be transported over. When first starting with FHE, I was having enough information about ZK did help me sort of understand a lot of things, but the primitives are entirely different. You're working with lattices, which are much simpler than elliptic curves. So that's a good point. There are less ways. I do not know, but like I think that there are less way to shoot yourself in the leg with lattices, because now we have standardized parameters and so on and so forth. There are more ways to shoot yourself in the leg with the elliptic curves, at least on the base primitive level. Lattices sort of like give you, they give you more API, probably because of which they give you, when I say API, sort of like, I think of hardness assumption as API giving me things to manipulate. I think lattices give you more structure in terms of like the API, which gives you FHE eventually. What else? One thing about elliptic curves is that the size of any ciphertext that you encrypt using, the normal cryptography that we know is like very small. Lattices blow up everything. Like the data that you sent over the communication is way bigger than the way you would do it, maybe if it's by some commitment or something like that. What else? Did I miss anything?
Yeah, one thing I'm curious about also is, when we sort of bottom out in terms of the ZK performance story, we bottom out in things like FFTs or fast Fourier transforms or MSMs, multiscalar multiplications. What do we bottom out, at least in the current generation of FHE schemes? Are any of those similar? Does any of our acceleration work, hardware work, ways of thinking about parallelization, do any of those carry over?
Yeah, they do, because all we are working with is polynomials. In FHE you have polynomials, in ZK you have polynomials, and you have to multiply these polynomials, which requires something called fast Fourier transforms, if you were to do them efficiently. And I suppose that really applies. Like all the work that is happening, at least on the GPU side for ZK, sort of ports over to, I would rather go ahead and conjecture that it's directly ports over to the FHE world, because all of them are working over friendly primes like Goldilocks, or all of them are probably not working with FFTs, but like probably Mercenary Prime or Goldilocks and so on and so forth. So I think that is completely relevant to the FHE world as well.
Cool. So that's a bit on the theoretical side. We're now, one of the big jumps in the last really half year is we've started to move from, if you want to engage with this kind of technology, you purely have to engage with it at the theoretical or at most cryptography library level. One of the big transitions, it seems, is that developers can now at least begin to engage with this. Maybe developers who have a high awareness of cryptography and some math background, but nonetheless, at least you don't yourself have to be a cryptographer to start building on top of and using these things. So Edu and Veronica, the both of you have been amongst the first developers, I'm guessing, in the world to really engage with MPFHE or FHE broadly and really take it seriously and think, how do we build stuff with this? Where are we at right now? Can you describe what the journey has been or what the experience has been? What does the tool stack look like? The both of you were also among the earliest developers in the applied ZK world as well. How does that contrast? Where are we in comparison? Is this like 2017? Is this 2022? Does that question even make sense? Tell us a little bit about the development experience today.
Yeah, I feel like it's similar to 2017. It's like in 2017, like I remember we have this Snark.js and Circum, which is like super awesome. Now I think like we have this Fantom Zone built by Jay. So I was able to experiment with it and build stuff during this summer. So like we built this like a chickens game, which is like a previous version of this frog game. So we have this like 4x4, 20x20 grid with like 4 chickens move around, and then chickens can lay eggs, which is like a 1 and 0. So I think like from that experience, we like how we build the game is like we can write the code, like maybe at that time we write in C++, and then we have like a compiler, compile it down to like binary circuits, like binary gates. That's like what a Fantom Zone is using. And then once we have that, we can use the Fantom Zone library to do that. I think like if you start writing the circuits, like at first it's like, yeah, so I remember like when I talk with Ideal and like how to think about this like you know a egg in a grid like a 0 and 1, and then I realized okay, like every time like you encrypt a 0 and 1, you sample like a different randomness. So like when you encrypt like 0 and 1, every time it's like the ciphertext is actually like different. So that is like a shift. And we also realized, okay, you cannot just access like a cell in the grid because the coordinate is like encrypted. So like in traditional programming, if you want to lay an egg, say cell like 2, 3, you just access 2, 3, flip the bit. But here you have to go through like the entire grid. So yeah, it's pretty interesting. But I think like on the high level, it's actually the experience is pretty similar to like the ZK development experience. Like we just experiment, like build a lot of demo code, build a lot of use cases, and then we realize, okay, here is the things that we need like researchers to do more to help us like optimize, and here is the things we needed to build like library framework as like ZeroXPark built like this pod and GPC library, so you can help developers to build a more useful application. So I think like in general like the experience feels pretty similar. Yeah.
Yeah, I would add that as far as I know, there's been FHE libraries for single party for a few years, but probably there's not been a lot of developers interested in building applications on top. Maybe it's because of the performance, maybe it's because just offloading computation was less exciting. And on the other hand, in the ZK space, we've had so many developers wanting to build applications and deploy them on chain and build proof of concepts. And I think this has helped a lot on the maturity of the tooling and making it more usable. So in that sense, for FHE tooling, I think we're not there yet. And then we have all this FHE previous tooling that was single party, but now we want to use it on the multi-party setting. So we can reuse the ideas of having circuits, but maybe we need a layer on top to define who is the owner of the data that is coming into the circuit. And I think there's been some exploration on this from the MPC side. So hopefully we can take all these ideas and build better tooling that is more usable and that makes the process of taking the library and building an application faster.
Yeah, I want to touch on a couple of things that the both of you raised. The first is this idea, Veronica, you mentioned that if I have some sort of, you guys tried to build a chicken game over the summer, right? Which is basically, there's a grid, the chickens can move around. If you're a chicken, you can lay an egg at a square, then you can keep moving around, and you can only see what's around your chicken. And you said this thing that was the being able to actually flip a bit at a certain coordinate is not as simple as accessing what's the value at 2, 3 in this two-dimensional array and flip the bit. Somehow you need to scan over every single coordinate and do a maybe flip in encryption over every single coordinate so that you're preserving the location that your chicken is actually interacting at. So one of the things that this makes me think about is this idea of thinking of FHE more in terms of programs rather than functions, where a program is something that might keep some persistent state, whereas a function is something that you run once, it has some inputs and it has some outputs. A program might have some memory, you execute some, imagine like a smart contract call, and then the memory changes, and then you execute another call, and then the memory changes, and you can read from it. So when we talk about something like this model of programming, without thinking about things in terms of the program and memory model, I guess we're just limited to Edu, like you were saying, these single-player applications, single-party FHE applications, where you're basically just running an extremely slow calculator, right? Like I can perform delegated computations, but a billion times more slow than I would be able to on my own machine. Is that kind of an accurate summary?
Yes.
So we've gone then from, I was able to observe some of your guys' experiments over the summer. Can you talk a bit about not just the development process, but the mental model shift in going from the first application were these kinds of calculators where we can add numbers together running a one-shot function, or Jay, I know you built a simple game, Bomberman. And then after that, we moved on to this chicken game, and now we've got the frog demo going on in the downstairs basement. What was the process of figuring out the programming model here like for all of you? What did you go into feeling uncertain about, and then what clarified as you started writing the circuits?
I would say that one of the challenges that if you imagine this server that is running FHE functions and has a private state, and then clients keep sending a request to run stuff on this private state, there is the question of how much does the server see? For instance, you can have a state and 4 methods, and the server knows which method you are calling to update the state, but you could also put these methods encrypted so there's only a single endpoint, and there's like a switch in the circuit that picks the method and then runs the computation, and there's also, like, if you try to balance both, you will find trade-offs between performance and privacy. So trying to reason about that is pretty hard.
For me, it was, so in FHE, turns out that you have to perform something called bootstrapping a lot. Like this is a bootstrap, this is a single operation that is the bottleneck, requires a lot of polynomial multiplications, and your entire function is like many of these bootstrapping operations. I observed myself to switch over from like, I just started appreciating parallelization a lot more after FHE than before, because what you can do is like you can take a program, but you can write a program in a way so that it's very parallelizable. And you can assume you have a server in the cloud that has, you know, thousands of cores, and you just put it over there and it executes in parallel, and the latency is like really low. So that is one thing that I'd like to mention is like in FHE you just start to appreciate the power of parallelization a lot more than otherwise.
Yeah, yeah, as I said, like, you know, access like memory, like it's hard. Another thing is hard is like, how do you think about how to represent states? Like that, like actually, you know, matters a lot, like in terms of the performance of the algorithm. So like think about how do you like bundle states together, and then so like, yeah, so basically that's like one part of the thing we have to think about. Another thing is like, I think it's just how do you think about your API, and like, because the thing is like, you can do like a bunch of computation, and at the end, like, if you want to actually see the result, you have to have like every party to decrypt it, and then so you can get the result. So that is one thing to really think about. And also like, you think about who gets the result, because the person who decrypted the last, like who get all the other people's decryption shares would see the result. So that is also another thing to think about when you design your program.
So we're getting back to this interactivity topic that we touched on earlier in this panel. It seems like this is a real thorn in our ability to build more scalable MPFHE applications. I mean, as far as I'm aware, all the demos that each of you has tried to run are involving at most 3 or 4 parties. How do we scale past that? How do we get to a world where the Twitter backend can be run as one huge multi-party computation, or MPFHE, or just general cryptographic computation? Is that something MPFHE can bring us, or?
Well, with MPFHE or any MPC protocol, you're stuck with this issue of someone holding the secrets. And that is hard to get around unless you have something new, which sort of led to the investigation of program obfuscation and indistinguishable obfuscation in the first place. Well, and can we get there? Yes, we can get there. We have like a few things to present. And I think if you were there for Barry's talk, he sort of introduced a bounty. We implemented a program obfuscation scheme and sort of we want people to break it because it's based on newer assumptions. So I think there's a path there. There's a path for building a Twitter backend based on the hallucinated server model that you've been mentioning. Yeah.
Can one of you describe maybe what program obfuscation gives us here? What problem does it solve that we're running into with MPFHE?
Maybe you can think of it as non-interactive MPFHE. So you have the program, you have the private state, and anyone can call this program and get the outputs without interaction from the other parties.
So in short, we don't have to do this multi-party decryption every single time I want to retrieve some result from my encrypted program.
Think of it as the obfuscated circuit now has this ideal secret key of FHE, which was first split among these different parties, embedded inside it. And now you feed your inputs, you feed your ciphertext, which is output of the FHE evaluation, to this obfuscated program, which holds the ideal secret key, and it decrypts it for you. It's just like a decryption oracle. And if you want to be more strict, I would say that it's a conditional decryption oracle because it first needs to verify whether the FHE was evaluated correctly or not. But that's a different question.
So yeah, maybe my final line of questioning here, I want to look a bit towards the future. So we've heard this topic obfuscation come up a couple of times at Devcon. And we've also heard a lot of really strong claims about obfuscation. Obfuscation removes the need for ZK. Obfuscation generalizes MPFHE. How much of the work on these technologies, you know, MPFHE, the schemes we're using in particular, the programming models around them, is actually going to be relevant in a world where we think obfuscation is actually the final boss of cryptography? Should we still be developing these particular MPFHE schemes? Like what role do these still play? Or is this something where this is a bridge technology, but what we really think is going to happen is at some point obfuscation is going to take over once it becomes practical enough and completely, you know, remove the need for any of these tools?
I would say that to answer that, like answering that question would take a while, honestly. But there's one way of achieving obfuscation that requires publicly verifiable proofs of FHE evaluation and FHE. So you require certain proof generation there, not zero knowledge exactly, but you require FHE over there. You require some sort of MPC protocol as well. But once you've built obfuscation, then it encompasses all these things. Yeah.
I would say a different point of view, which is that for performance reasons, we may want to stick with the fastest solution, so we may have hybrid solutions in the same sense that you can build a signature scheme with ZK, but we still use like traditional signature schemes. So maybe all the part that you can do with FHE, you will do it with FHE, and only the part that it needs I/O, you will be using I/O.
There's also a question of whether you can build program obfuscation for generic circuits, or can you only build program obfuscation for limited class of circuits? And we do not know a full answer to that yet.
All right. A final question I have is, what would all of you be most excited to see built next on top of MPFHE or any of these technologies that are creating this model, enabling this model of this trusted third party built inside cryptography, hallucinated server? Maybe folks here have heard a couple of different terms. What should we build next?
I would want like researchers and also like you know, cryptographers, like someone like Jay, to build like improve the library and actually try to make obfuscation a reality. If that happens, I think there's like so much things we can actually build on. For app developers, I think this is a time you can actually try like MPFHE. I would like to people to build more things like for multi-parties, like for people to connect, to coordinate, and to kind of negotiate things. So that's type of the things I want to see. Yeah.
I think someone should finally build the eigentrust. We have been trying this for like now almost 4 years now. And I think someone should finally build the eigentrust with multi-party FHE or obfuscation if it's practical in the near future.
And for those who don't know, eigentrust is basically proofs about social graphs. If we have a decentralized social graph, then we would like to be able to perform some operations on it.
Yeah.
I totally agree with these 2 points. I would like to add one which is less exciting, but it would be nice to lower the resources requirements of MPFHE so that it can run on lower-end hardware so more people can use it.
Awesome. Thanks, folks. So now we're going to go to audience questions. I believe that in a moment you'll be able to see. Oh, cool. Okay, here we go. So we've got this QR code on the screen. You can scan and make a ZK proof with your Zupass ticket to post a question to this feed, and we're going to start picking some of these questions to pose to our panelists here. So maybe I'll go approximately in order here. What would be a good framework to start with for someone interested in building on top of MPFHE? What is even the landscape?
Fantom Zone. That would be a library that already implements MPFHE protocols. And then you would need a compiler on top of that, unless you want to be writing Boolean circuits by hand, which is a fun option if you want to learn how it works, but not very practical. And there are some solutions for the compiler thing, but they are not very robust. And someone in PSE will probably be working on this.
Are there other tool stacks besides Fantom Zone that exist?
There exists Latigo, that is like a more lower level library. Again, gives you multi-party FHE for different schemes, not just the schemes that Fantom Zone implements. You can work with that. There is something called OpenFHE that also implements multi-party FHE. Again, very low level, not as high level as Fantom Zone, but like if you really want to, go into this wilderness and sort of explore FHE, then I would recommend these two libraries for sure.
Awesome. So the next question here is about TEEs. Have you considered the combination of TEEs and FHE to solve privacy issues you mentioned, and about how much the server knows? Maybe to add on to this, it sounds like what MPFHE almost resembles is like a mathematical TEE that also happens to be 1 billion times slower. So I'm curious for each of your takes on basically, why is it worth exploring this avenue? Why is it worth incurring such a high performance cost overhead? Is it because we believe that that cost is going to go down enormously, or is it because we believe that there's some fundamental reason why the direction of things like FHE and obfuscation versus the direction of things like TEs lead us to different capabilities?
I would say I find it harder to reason about TEs because I believe all TEs can be broken, and then it's a matter of how hard it is to break them, so you try to put a cost on breaking them. But this estimation, I don't know how good you can make it, because if someone finds a new flaw that reduces the cost, and you build a solution with that assumption, then you have a bad solution. So FHE gives you an alternative where, the performance is worse, but you have better guarantees on the security?
I would say that what I really want is like a box that is like this mathematical TE, and I can sort of like explore this box and confirm the guarantees that it provides. And I don't think we can do that with TE at the moment. The only feasible way of doing that at the moment is via relying on mathematical guarantees, which comes from cryptography, and one form of that is like fully homomorphic encryption.
Yeah, I think when I think about it, maybe MPFHE can also make you to be able to do things like peer-to-peer fashion. So you can have like a cryptographic shard of a program and then to run it that way rather than put everything inside a central box. So that might be useful in some use cases. Yeah.
One thing maybe I'll contrast this with, and I would love to get some takes on this, is, well, with a lot of the FHE prototypes that we've seen built in the recent months, the architecture for these things looks like you have multiple clients, and you also have a server that computation is delegated to that's responsible for actually performing the FHE over encrypted data. You know, there's some spectrum here between everybody is running the FHE locally on their local machines, to there's a delegated computation, to actually we're going to delegate the trust model to the TEE as well. How do you think about navigating that spectrum? Like, what is an appropriate place to land on? And of course, we might even take it further on the spectrum in the other direction, which says, well, maybe we don't even accept FHE because at the end of the day, some set of parties needs to hold a bunch of decryption key shares. So theoretically, some KVM people could collude to decrypt the entire state. We need program obfuscation instead. Where do you think about landing on the spectrum, and where do you essentially draw the line for what technology is actually useful for an application?
Yeah, I think there should be a world all those things exist, and depending on the special, like your use case, and then you choose one versus the other. You might think about like what of your security guarantee you want to achieve, like, and then also like the performance and like how is the when you have users, like how is the user flow going to look like? So yeah.
Yeah, I think, like, depending on the stakes of your problem, you may use TE in certain parts. You may also try to have hybrids. Like, maybe you have a model where you have a collusion assumption, but then you run this under TE. So now you need to break two security properties, which is that they collide and also, sorry, they collude, and also they break the TE. So I guess on the practical side of things, if you want to build a product, some people may find using TE is acceptable. But I think we as a, I don't know, as researchers, we should try to push more and try to work towards having practical MPFHE and practical MPC in general.
The problem with relying on just TEs, or even like this God server model of the multiple servers in the cloud, probably, you know, TE servers in the cloud holding the secret shards, is that the moment you try to build a big application, or the moment there's enough incentives, people will break it. Like the moment there's a way to break it, people will break it. Which sort of like forced me to push on this other direction where we should really aim for program obfuscation to become practical for any of these things to scale in terms of going global. It would be really hard to even scale multi-party FHE if you're not able to get around this problem.
One other thing that I want to ask about, and this is inspired by one of the questions on the screen, which is about ECDSA, the signature scheme Ethereum uses, is where do these technologies intersect with blockchain? I mean, after all, we are at Devcon, the annual or semi-annual Ethereum developer conference. And it also sounds like the way that we've been talking about MPFHE, obfuscation, hallucinated servers, and all these concepts is very similar to the idea of the world computer spiritually that Ethereum is gesturing towards. So are there any specific technical interfaces that any of you think about as this is the border between FHE and blockchain in the near future? Right now it might not be performant enough, but where are we going to see these things finally dock or converge, or how should we think about docking them?
Like at the, okay, if we just imagine that we have program obfuscation practical in future, then there's a huge chance that we can completely change the smart contract framework of Ethereum itself. This might be a big claim, but like, just take it for granted at the moment that we have program obfuscation. But we can completely replace that with IO. Or program obfuscation. We cannot do that at the moment with multi-party FHE because us as the community are not comfortable with these God servers holding the secret shots. Which is why I also think that we cannot dock at the moment. We would make future progresses to be able to be compatible with what blockchain people are comfortable with.
I mean, this kind of gets me back to some of the discussion we had about interactivity, right? So ZK snarks became a very good fit for blockchains once they became non-interactive. When we had general purpose interactive ZKPs, the liveness assumptions needed to interoperate with smart contracts were just too high. Is that a fundamental barrier to FHE and blockchains, or is that something where we can actually do some sort of hacks in the near term to find some useful convergence?
I can imagine some solutions where like a small party coordinates outside of the blockchain, and then they compute something with multi-party FHE and send it to the blockchain. For instance, I don't know, like FHE multi-6, something like that. I guess that would be. But when you want to go to the global state with no coordination, I think the only solution is going to be program obfuscation.
Awesome. All right. That is all the time that we have. Let's give a big round of applause to our panelists. And thank you to everybody for joining us this afternoon.
All right. Thank you to our amazing panelists. right, hi everyone. Welcome back. If you enjoyed the previous panel a lot, the good news is we have another talk from Gemma J on scalable multi-party FHE with Fantom Zone. Let's welcome Gemma J onto the stage.
Hello, welcome back. So today I would be talking about Fantom Zone, but before I sort of like dive deep into Fantom Zone and talk about the rest of the things, I would sort of walk you through the motivation behind Fantom Zone. So if you guys are familiar with globally mutually trusted third party, I would want to introduce you to this idea of globally mutually trusted third party. What is this globally mutually trusted third party? Well, it provides you 3 guarantees. The first thing that it says is that whatever information you send to this third party, it will always keep that private. It would not leak it to anyone. The second guarantee that it provides is that all the information that it has collected over time from different people, we have been sending this globally mutually trusted third party all our information, let's say for a year. All the information that's collected for all these years, it will always keep that private and would not allow anyone to poke inside its state, inside its memory. And the third guarantee that it provides, which makes this particular party very magical, is that it can compute any arbitrary function we want it to compute, as long as we provided enough authorization to be able to compute that function. And it will only output the necessary outputs. Usually, I sort of like refer to this mutually trusted third party as a mutually shared computer. And if you guys are familiar with something called the God protocol, this is the God protocol. This is a picture from Nick Szabo back in 1987. So, first observation to make is that if we really want these 3 guarantees if we really want this party to be globally mutually trusted, we want this party to be able to prove these 3 guarantees to any individual without requiring any additional interaction, which is why we require cryptography. We cannot just make it on certain legal arguments or something like that. We require cryptography for building this globally mutually trusted shared computer. And we started to build Fantom Zone to eventually build the God protocol. But to stick within the realms of practicality, we could only build an abridged version of it. So for the rest of the talk, I will be talking about what is Fantom Zone? Why it is an abridged version of this God protocol. And the second important thing that we're talking about is how can we push the frontiers to eventually build the God protocol? Okay, so Fantom Zone, the abridged version. The key idea in Fantom Zone is something called multi-party fully homomorphic encryption. And for me to describe you multi-party fully homomorphic encryption, I'll have to eventually describe you what is single-party fully homomorphic encryption. In single-party fully homomorphic encryption, you have a single client, this guy over here. They hold a secret. They keep the secret private to them. They can encrypt their information, which is A here, with the secret and produce an FEG ciphertext. And then they can send this FEG ciphertext to any server. And the server can evaluate any arbitrary function on their private input, which is A, and produce an output ciphertext. And then the client can receive the output ciphertext and decrypt it. So this is single-party FEG. Coming to multi-party FEG. Well, the key idea in multi-party FEG is that you split this secret, which is held private by a single client in single-party FEG, among many clients. So you have S0, S1, S2 as secret shards split among these 3 people over here. The first step in multi-party FEG is something called collective public key generation. So all these 3 parties come together and they generate the collective public key. And then all these 3 parties, using the collective public key, encrypt their private inputs and produce FEG ciphertext. And then they send their FEG ciphertext to the server. server executes some arbitrary function on the FHE ciphertext and produce an FHE output. The key thing to notice here is that all these parties would have to produce a decryption share to eventually decrypt the output ciphertext here. So they produce the decryption share using the secret shards, and then they send it to each other, and then only they're able to decrypt the output ciphertext. Because in this case, the secret was split among all these parties. So why is Fantom Zone an abridged version? Well, because Fantom Zone, assuming that in the future we're able to add publicly verifiable FHE to a Fantom Zone, can only guarantee the 3 guarantees that I talk about in the God protocol to only the holders of the secret shards. It cannot guarantee these 3 guarantees to everyone around the globe, which is why Fantom Zone is just an abridged version of it. Okay, so you might wonder, how do we build towards the God protocol? Like, how do we even do it? Well, what I would like to say at the moment is, I would have loved to say that, after a lot of research and a lot of 5 years of research, we have figured out the solution to build the God protocol. But no, there are no enlightening thoughts here. And there's one obvious answer to eventually building the God protocol, which is program obfuscation. What's program obfuscation? Well, to simply describe a program obfuscation, let's just assume that you have function f, right? What you can do with program obfuscation is you take this function f and perform some transformations on this function f and produce an obfuscated circuit. You can give this obfuscated circuit to someone else, and program obfuscation guarantees that the only thing that you can learn from that obfuscated circuit is the input to output map and nothing else. Now, you might be wondering, why is this useful? Because if the function is trivial, then you can easily learn it from the input to output map. Program obfuscation becomes very interesting when you sort of obfuscate a program that is a cryptographic function. For example, let's just say that I take a function that decrypts any ciphertext that is encrypted to my public key. Right? So I take a function, and this function has my secret key, and it decrypts any ciphertext that was encrypted to me using my public key. And I perform certain transformations using program obfuscation to this function and produce an obfuscated circuit. I give this obfuscated circuit to someone else. What they can do is that they can decrypt any ciphertext that was encrypted to me using this obfuscated circuit. But they can never, ever learn what the secret is inside that circuit. They can never learn my secret key. And these are the class of functions where program obfuscation becomes useful, and I'll tie it to building the God protocol later in the slides. Okay, so now assume that we can only build program obfuscation for some limited class of functions. Not for general class of functions, but limited class of functions. I'll tell you one way of building the God protocol using program obfuscation. Step 1, modify the FHE scheme that we're using before to become publicly verifiable. What do I mean by that? Well, a publicly verifiable FHE scheme does two things. It evaluates the FHE function, which a normal FHE scheme does. In addition to evaluating the function, it also produces a proof of correct evaluation, so that anyone can verify this proof with the output ciphertext and be assured that the server that sort of executed this FHE function executed it correctly, and which I usually refer to as proof pi of correct evaluation. Step 2. Replace the collective key generation operation that we did in the multi-party FHE with a trusted setup. In the trusted setup, you have arbitrary number of people here. They perform some MPC protocol to produce FHE keys. There are 2 types of FHE keys which are very important: public key and the bootstrapping key. Bootstrapping key is usually used for some sort of FHE operations that you can completely black box. The key thing here is that no one knows the ideal secret key, because we're doing a trusted setup in MPC to generate these 2 keys. The third step is modify the trusted setup to also output an obfuscated conditional decryption oracle. Okay, that's a mouthful. I'll sort of like go into it one level deeper. What is an obfuscated conditional decryptor? This particular conditional decryptor is an obfuscated program of the following functionality. What it does is that takes an output ciphertext and a proof of correct evaluation of FEG circuit. It verifies whether the proof is valid and decrypts the output ciphertext if and only if the proof is valid. And this sort of like tells you why did we assume in the first place that program obfuscation may be feasible only for like limited class of functions, because to build the GOT protocol, like to build the GOT protocol using the FEG route, we only need program obfuscation to be practical for this obfuscated conditional decryptor. So we modify the trusted setup to also output this obfuscated conditional decryptor, and that's it. And another thing to note is that this conditional decryptor also has the secret key, the ideal secret key that no one knows, embedded inside it. Okay, so the end-to-end flow is, you do MPC to generate three things: public key, bootstrapping key, and the obfuscated conditional decryptor, which I now realize is somewhat of a mouthful. I should have chosen some other term. Anyways, the second flow is, now anyone can encrypt their private inputs using the public key, that is the output of the MPC protocol. So you have multiple ciphertexts here. And then they can send it to the FEG server. FEG server evaluates the FEG function, outputs the encrypted output. In addition, it produces a proof because the FEG server is evaluating a publicly verifiable FEG scheme. And then we plugged in the proof as well as the output to the obfuscated conditional decryptor, and the conditional decryptor would only output would only decrypt the encrypted output if and only if the proof is valid. So this is one way of building the GOT protocol using publicly verifiable FEG and program obfuscation for obfuscated conditional decryptor. So there's one way, which I've just shown you, but we need new ideas to push the frontiers and to finally build the to finally build program obfuscation or indistinguishability obfuscation, if you're familiar with that. Here, I've showed you just one way. But if you're able to come up with new ideas, then probably we can make program obfuscation more practical for general circuits, not just for like limited class of functions that we used before. And probably we can directly build the GOT protocol from program obfuscation. Okay, so while I was exploring this field of program obfuscation and I/O, one key observation that I made, was that it's really hard to get efficient program obfuscation from standard assumptions, and we would inevitably require exotic assumptions. And I'll tell you what are standard assumptions, what are exotic assumptions. Well, a standard assumption is an assumption that has been there for a while. For example, D-log, discrete log problem. There also exists additional incentive for people to break these standard assumptions. And exotic assumptions are somewhat newer assumptions, like they have been only there for like 5 years, or not even 5 years, like 2 to 3 years. What we can do as a community to, realizing that we might inevitably need newer assumptions to build practical program obfuscation is we can start examining these newer assumptions, start breaking them, start testing them. Or we can build applications using this assumption so that we can incentivize people to break them and tell us whether they're broken or not. And then eventually, in like a few years, we would have candidate assumptions that are newer assumptions, but they have become then standard, so using which we can build practical program obfuscation. Okay. And taking a first step towards this, we are launching a bounty program to break one of the candidate assumptions, which is called program obfuscation via local mixing. The way I think about this particular assumption is that they're taking more computational complexity approach than taking like the traditional approach of using algebraic structures to build program obfuscation. The goal of the bounty is that we have provided you an obfuscated circuit with roughly like 240,000 gates, which was obfuscated from an original circuit with roughly 1,000 gates. And you have to find the original circuit. You can learn more about the bounty at offustopia.io. If you know what offustopia is, offustopia means that we're living in a world where obfuscation is practical, and the bounty amount is 10K. And this bounty is launched in collaboration with Ethereum Foundation and ZKEVM Spark. Okay, so before I break, and I think that I have a bunch of time, okay, before I break, I would want to make one conjecture. And the conjecture goes as follows. I think the God protocol is the convergence of cryptography. Probably building the God protocol would require certain sort of like FHE, that is just one route, but like publicly verifiable FHE and other things like MPC for trusted setup and so on and so forth. But once we've built the God protocol, I think it encompasses everything. It gives us everything that we have been like wanting for a while. It gives us witness encryption. It gives us zero-knowledge proofs via signatures. It gives us MPC, multi-party computation. It gives us FE, functional encryption, and all of these things that we've been demanding for a while. And this is also one of the major reasons that we should start investigating much more seriously how to get practical program obfuscation and finally build the God protocol. And that's it. Thank you.
All right, thank you for the talk. We do have some questions rolling in. Let's go through some of the questions. Let's start with the first one. Can we implement threshold ECDSA with Fantom Zone?
At the moment, yes, because you can express theoretically, yes, but it would be very impractical to implement ECDSA with Fantom Zone at the moment because ECDSA is like you're doing elliptical operations, which is a lot of operations. As far as I understand, threshold ECDSA is possible. It takes 2 days to generate one single signature.
All right, so next question. Can you tell us a little bit more about the definition of obfuscation as a virtual black box? That's the first question over here.
Isn't your definition of obfuscation as a virtual black box impossible? I am not posing obfuscation as a virtual black box. I did not mean to say obfuscation is a virtual black box. By the way, the impossibility result for virtual black box is only for like certain very restricted class of programs. It's not for like general class of programs. Eventually, you can aim for virtual black box with certain caveats. But again, saying that my definition of obfuscation is not virtual black box.
All right. And what can be done today with Fantom Zone?
At the moment, as I said, Fantom Zone is an abridged version of this God protocol. It does not even have publicly verifiable FHE scheme, so it does not give you all the 3 guarantees. The only guarantee that it gives you is that it will execute the function that you ask it to execute while private information can be coming from multiple people. It'll keep the information private, but you'll have to trust it for it. So you'll have to trust this particular server to always keep the information private and not send it to anyone else.
Perfect. And we do have one last question. Oh, cool. More questions rolling in. Can obfuscating programs undermine open source transparency and make it harder to verify the absence of malicious code?
I see. Make it harder to verify absence of malicious code. Well, that is assuming that the entire program is obfuscated. When I say obfuscation, we require obfuscation for certain parts of the program which can interact with a public program and a private program which is obfuscated. I understand that obfuscation can be used for many malicious purposes as well. Like, for example, like there are several reasons why people might be interested in obfuscation, but we can, as a community, make sure that there's interaction between the public interfaces and the private interfaces which are obfuscated.
All right. And why do you call the publicly verifiable FHE circuit obfuscated? Doesn't the require solidity verifier or something which is public?
No. I think once I give you obfuscated circuit, there are certain guarantees that you can learn from the obfuscated circuit itself, that it does not reveal anything, as long as you've done the obfuscation correctly.
All right. And do you have evidence that the conditional decryption functionality is possible using I/O?
Yes. There are theoretical results, and we're trying to make it practical as well.
All right. Can you give one example each on how I/O can replace ZK, MPC, FHE?
Okay, so for ZK, what you can do is like, you can embed a secret key inside this obfuscated circuit, the God protocol. And a zero-knowledge proof is just a signature from this God protocol. Whatever secret exists inside this particular server, or this God protocol, or this FHE circuit, obfuscated circuit, a signature by that thing becomes the zero-knowledge proofs. So you do not require zero-knowledge on the client side anymore. For MPC, again, it's a globally mutually trusted third party. All of us encrypt our private inputs with the public key corresponding to the secret key that lives inside this obfuscated circuit. And we send our private inputs to this. It decrypts that, performs some function, and produces the output. So that's one way of replacing MPC, and the same applies for FHE.
Cool. We can stay here for maybe another 10 seconds if there are any new questions rolling in. All right, cool. Let's give another round of applause to Gemma. All right. Hi, everyone. Welcome back. May I have everyone to get seated, please? Thank you. Next, we have a talk on multi-party homomorphic encryption from ring learning with errors from Jean-Philippe. A little housekeeping rule, there's going to be a QR code on the right side of the screen. Please scan the QR code if you have any live questions, so Jean-Philippe can address them at the end of his talk. Now, let's give a round of applause to Jean-Philippe onto the stage.
So hello everyone. Yes, so before we had a high-level introduction to multi-party FHE, and in this talk I will go more into the details how you, in practice, instantiate this kind of construction. So this talk will be like a bit more formal and technical than the previous one, but it should give you a good insight on how it's done in practice. So, what is MPC? Essentially, MPC is a functionality that you want to achieve, and you want to compute a public function or private over a set of inputs that can be some private or private, and get an output. Wait.
Yes, but my slides are not working. Your slide not blocking? Yeah. It's not land, right? No, the slide I made, you are missing the equations and a lot of it on it. It's wrong slide? Yes. It's not possible to give a talk with that. Yes. I have my laptop, yes.
So sorry guys, we're going to take maybe a 2-minute-ish time to figure out some technical difficulties, so bear with us. We'll be back very shortly.
Do you already send the slide, but it's not your slide, right? Online, yes. This is online but not connect, right?
Yeah. Okay. Download PDF.
I want to know his screen is connect to is already connect. Your file is already connected with at the back and monitor already. Okay, right. It's your microphone.
It's fine. Yeah. Yeah, there was an issue with the slides. It's fixed now. Okay, sorry. There was an issue with the slide, but it's fixed. Yeah, back to the slides. Now everything appears. Yes, so you want two things. You want output functionality, so you ensure that you get Y, and also input privacy. So you do not learn more than what you could learn from the inputs and the outputs. And we consider a set of n parties and up to n-1 adversaries, which are public and static, which means they follow the protocols and try to learn as much as possible. And in fact, you can instantiate MPC with FHE by adding an access structure on top of FHE. This is meaning that you restrict who is able to decrypt what. And this is done with a key generation protocol, like Jay introduced to you, where you secret share the key among the participants. You generate some public evaluation key and public keys. Then you have an evaluation phase. And finally, you interact again to decrypt. So I will introduce now the ring learning error problem, which is the base construction on which all these schemes are based. And so we work in a polynomial ring of degree n-1 modulo q, and we need free distribution. We need a uniform distribution over this ring, a small error distribution, and a ternary distribution, and that's it. And essentially, the ring learning error problem is the distribution is defined as a small secret polynomial times a public uniform polynomial plus some error. And you have two hard problems on this lattice, which is a search problem. Essentially, you need to either find E or S, or the distinguishing problem, which asks you to distinguish a valid ring learning error sample from a uniform distribution. And from this, you can build homomorphic encryption. And this works because all operations are affine operations of the secret keys, meaning that if you apply an operation on a ciphertext, then it outputs a ciphertext on which the same operation will apply on a secret key. And it essentially preserves the structure of the ciphertext. So before and after the evaluation, all you need to do is have a secret key and multiply back the two components of the ciphertext to recover your message. And because all of these are affine of a secret key, there is one more thing to introduce, which is gadget. So, sorry. To encrypt the ciphertext, you simply sample a ring learning error sample, and you add the message on top of it. But sometimes you also want to multiply with a message, and for this you need another type of ciphertext, which is called gadget ring learning error. Essentially, it's the same as before, except you decompose your message with a base, and what this allows you to do is to do multiplication where the noise is independent of the message. And since all operations are affines of a secret key, then the setup phase which generates the public encryption keys, is also a fan of the secret keys. So all the elements in blue, they are linear operation over the secret keys, as well as the decryption and re-encryption, which is simply changing the secret keys. So these are all linear equations. And yeah, there is one issue with the S-square, but we will deal with it after. And this is great because now you can instantiate your protocols as public aggregatable transcripts. So since everything is a fine function of a secret key, then everything is additive. So each party can sample its own secret key locally, and then you do some protocol with public transcript, which output a sum of all the transcripts which correspond to a new transcript that is encrypted under the collective secret key, which is unknown by anyone, but each one knows a part of the secret key. So this is great because with that, you can instantiate a one-time setup, and it has a low round complexity compared to traditional MPC. You have 2 rounds for the setup. One of the 2 rounds is because of this really an instruction key which has an S-square, which is not linear in S. Then the evaluation phase is completely non-interactive. This is why you have an overall low cost of communication. And you, again, need to interact for the decryption. And what this allows is completely delegated public share aggregation. And overall, it has a sublinear complexity and multi-party computation. So these kind of schemes are implemented in the Latigo library, and it enables N out of N and T out of N threshold schemes. So this is the library that provides all the state-of-the-art FHE schemes. And it's also widely used, for example, for the Adash Privacy and Security Workshop, where this series was used by the 2 first-place competitors. But simply implementing these protocols is not enough, because you run into a lot of issues when you try to deploy them in practice. So Latigo has the construction and deployment of the base protocol, but when you run them in practice, then you run into some security issue and a client issue. For example, you need to make sure you have a reusable setup and that everything can be parallelizable, that the share for the key, which can be quite large in practice, can be supported by the client, so you need to share the shares. You need to support a predefined HE circuit evaluation, and also you need to ensure that if a client drops, for example, during the setup or at the decryption, you have some robustness, but also that it's still secure, even if you have these kinds of unexpected events. And for this, Helium was developed by Christian Mouchet, and this solves all these issues. So Helium is built on top of Latigo, and it provides a framework to be able to do FHE-based MPC and deploy practical solutions. So we have seen that we have a 2-round setup. Basically, you need 1 round to generate a public key, and then 1 round to encrypt and generate the evaluation keys. But it would be great if we could have a 1-round setup, because this would enable many more applications. So essentially, why do we have a 2-round setup is because when we generate one of the public key, the reunion key, this key enables ciphertext compactness. So when you multiply 2 ciphertexts together, they do not grow in size. It depends on the public key, which itself depends on the previous protocol. So it would be great if we could reduce this to a single round. And the ideal framework would be that we have a set of predetermined parties. And each of these parties will send a single public aggregatable transcript to the server. And then the server can choose any subset of these parties, aggregates the path associated to these parties to generate the corresponding evaluation keys and ciphertext. He can run an arbitrary circuit. And then it only requires the collaboration of this subset of parties for the decryption. So back to the issue that prevents a 2-round protocol. A 1-round protocol. This is this rel interaction public key, which is an encryption of a square of a secret key. It's both important for ciphertext multiplication, but also for expanding some other kind of ciphertext which are used for the few bootstrappings, which is the scheme that is, for example, used as a backend in Fantom Zone. So if we look more at the structure of this key, then we see that it's a gadget RLB ciphertext of the encryption of the secret key times the sum of all the secret keys. So it would be great if we could have a one-round protocol that is able to produce this kind of key-dependent message for both RLB and GRW ciphertext. And, well, how can we achieve that? It's possible with some homomorphic operation. Basically, we generate from 2 RLW ciphertext and 1 GRW ciphertext, you can hopefully generate this kind of key-dependent message RLW ciphertext. And here, all the message, the ephemeral secret key U, the error, the secret, etc., they are all affine, so they are all additive, which means each party can generate locally, non-interactively, and at the end, you can aggregate everything and get this encryption of the message times a secret. And this is great because now you have a solution to have this one-round protocol. And so we are back to our diagram, and now we solved this was a previous instance where we have one round for the public key generation, one round for the encryption, and the realization key generation. And this solves and changes it to one round for the key setup and one round for the encryption. This is already great. But allocating one round just for encryption is fine if we want to have dynamic and flexible on the secret inputs, but if the input circuit is fixed, for example, if you have a starting state, like for a game like Frog Zone or bank account, maybe you want to have everything into one round. And this is easily solvable. Basically, the party that wants to encrypt the message encrypts it under its secret, and the all other parties that have to generate encryption on 0 under their own secret. And you can aggregate everything, and this is equivalent to encrypting under the secret, the public key of the ideal secret key. The only issue is that it requires ON communication per ciphertext per party, meaning that for each ciphertext that a party wants to generate, all the other parties also need to generate a corresponding encryption of 0. And yeah, at the end, you could have a full one-round non-interactive setup with encryption if you want. So these protocols are not in the base library, but they are in my fork of the library, Latigo. It's a fork of Latigo that has over 30,000 change. It has new functionality, protocols, etc., like these non-interactive protocols. And there are also the backend of Fantom Zone, which is a Rust-based MPC focus library, which can evaluate arbitrary functions over a set of private or public inputs. And it has a high-level abstraction, which is focused for ease of use developers. And yeah, if you did not know it, it's the backend of the game Fantom Zone, that is downstairs. And yeah, voila. Yes, the questions. Yeah, I have to disconnect for the...
So we do have some live questions. You can sit here. So here we have one on the screen. Is this a best method than ZK proofs?
I would say it doesn't solve the same problem. It tries to ensure privacy. ZK proofs do not provide privacy. So FHE and ZK proof are complementary. You would use a ZK proof to, for example, right now, the server, you have to trust him that he will evaluate the correct circuit. And so what you get is a ciphertext which looks like random noise. How can you be sure that it's not a malicious ciphertext, which when you decrypt it will leak some information? So you use ZK proof to have a proof that the server did evaluate the circuit it was asked to evaluate.
All right, we do have some extra time for QA, so let's wait for a few seconds to see if there are any other questions popping up. Oh, we have another one. What are the main differences between this library and the pre-existing ones, like Concrete?
Concrete primarily focus on TFHE, and the entire stack is built on this scheme. These libraries, they are more generic. They are, I would say, more low level. Also, they are not in the same language. So I would say first, if you want to use Rust, then use Concrete. But this Latigo, for example, provides support for the BGV, ZKEVM, which are schemes that enables vectorized arithmetic over complex number or finite fields. And TFHE is more like single-gate arithmetic.
Awesome. And can you give some concrete use cases where one-round protocol unlocks?
Yeah, so basically what it solves is liveness. Now you can just send your share and forget and go offline. You don't have to wait on the other parties to have some interaction to generate the setup and then the ciphertext.
All right. Can you share any insights or number on the performance versus other libraries or protocols?
So multi-party FHE, what is essentially solved is the setup. The evaluation phase is the same as single-party FHE. And the setup remains, in most of the case, negligible to the evaluation of the circuit. So there isn't like concrete difference in practice.
All right. Are there examples to use your forked Latigo with the features you mentioned in this presentation?
Yes, fork has a folder with examples, and there is an example that shows how to do a full one-round protocol for all the key that will be used in practice.
What resources would you recommend to learn about multi-party homomorphic encryption?
I would recommend to join the Discord of FHE.org. They have a lot of, it's a great community, and there are channels to learn and to discover, to ask questions, and there is always someone online, and they will point you toward the correct references if you have a specific questions.
All right. I guess the next question is also kind of related to the previous one. Are there any posts or publications where we can learn about these protocols?
Yeah, unfortunately, right now, no, it's only in the library, but we will submit something for the FHE.org conference, which will happen in March. The thing is that these are very simple and small protocols, even if they solve a problem that was not solved before. For question of time, we did not have the resource to produce something, but it will be there in a few months.
One last question. What are the challenges in this space we should look into?
Right now, I see two challenges that people face in practice. We have a lot of people that complain that the setup is heavy, like a few hundred megabytes to a few gigabytes, depending what you want to do. And depending on the circuit you want to run, the overhead can be quite large. So a lot of people say that FHE has 1 million to 1 billion time of overhead, but it's not really true. It depends really on the circuit you want to run. Some FHE circuits are as fast as plain text circuits, but they are very shallow. So it's use case basis. Personally, I look forward to having GPU or hardware acceleration for FHE. It will make things a lot more practical. But we had collaboration with people in the medical sector, and they said they did not care if it would take 3 weeks for the computation to finish because it took them 2 years to get the data, so it was nothing for them.
All right, so that's all the questions. Thank you guys so much for coming, and let's give another round of applause to Jean-Philippe. Thank you. So our next talk will begin at 3. I'll see you guys then. Hello, hello. Welcome back. Please have a seat for our next panel. Very excited for this one. The next panel will be on building consumer apps with ZK, MPC, and FHE. And our panelists are, we have Ayush from ZK Email, we have Aish from Tacheo, Andrew from Cursive, Richard from ZK P2P, and Ying Tong, independent researcher. So let's give another round of applause to our amazing panelists on the stage.
All right, thanks so much, Teresa, for introducing us, and welcome to the panel on consumer apps built with ZK, MPC, and FHE. I'm also super excited about this panel here. How I'm thinking of these projects is we have two of them that actually build primitives, so ZK Email and Taseo. They're building sort of libraries and tools. And then we have two of them who built on top of them. So we have ZK P2P that built on ZK Email, and then Cursive, which uses Taseo as well as MPFHE. So this is a really good representation across the stack, and I have lots of questions for you guys. So I want to first start with an intro. Can we get ZK Email, ZK P2P, Taseo, and Cursive in that order? Yeah.
Sweet. Yeah, I'm Ayush. I work a bunch on ZK Email. The idea is you make proofs of emails in your inbox or emails you've sent, and these can get proved on chain. We've thought a lot about what are both the interesting apps you can build and what is the best kind of dev tooling to do that. And on the side, I also like thinking about MPC, FHE, and things like that, so happy to also jump in there.
Cool. I'm Richard. I work on ZK P2P. We build P2P marketplaces that connect Web 2 assets and like digital goods with Web 3, like smart contracts. In particular, we have like a P2P like on-off ramp. So basically, you can send money from Venmo and use that to trade directly for USDC on chain, and that's powered by ZK Email. As the source of proving that you've sent that Venmo payment. Among other things, we've also launched a couple, I guess, different marketplaces for trading tickets and trading domains on the secondary marketplace.
Hello, my name is Ash. I'm from Taseo. We build tooling and networks to build and deploy MPC-based applications. In particular, CoSnarks, which is what Cursive are using, and you heard a lot about this week. It was the first week that it's live, so we're very excited. And my role there, I care a lot about privacy. So I think about how using these tools in the real world actually affects the lives of the people using them.
Cool. My name is Andrew. I work at Cursive, and Cursive is exploring different ways for cryptography to enable new forms of human connection. So certain things that we're exploring are like multi-party FHE, looking at CoSnarks with Taseo, and also like new MPC primitives that we're like super excited about as well.
Very cool. I want to start us off with a high-level question, because you guys are building in a paradigm that is very new and different from most consumer apps that we're used to. And I'm wondering what are some application design patterns that are unlocked by these cryptographic primitives. And I want to address this sort of like in like ascending order. So in my mind, like ZK is the like most basic primitive, followed by MPC, CoSnarks, followed by MPFHE. So let's go in that order. Like, what are some design patterns that are unlocked for you? And give us examples from some of your favorite apps. Let's start with ZK Email. Yeah.
Yeah, I guess we've seen two main ways people design applications that I think are different than everything we've seen before. One is around proof of received emails. So that's kind of the stuff that Richard and ZKPDP can contribute to. But it's very interesting now that it's very easy to make these proofs. People are kind of starting to compose them. So one example is you can prove you're part of a Slack workspace by using any Slack confirmation or invitation email, and then also prove you, for instance, took a flight on United and you ended up at Thailand. And now you can automatically build a system where everybody in your Slack workspace automatically gets reimbursed for their flight to Thailand. And it's kind of interesting because you're not just using one proof, you're combining all sorts of different proofs. And just because it's very easy to build each sort of proof, you can build these new applications that take multiple facets of your identity into account. And so that's one that I've been really excited by seeing. We've also seen on the side of using emails to send transactions, people kind of hot swapping almost emails and Ethereum accounts in their application. So for instance, multi-sig signers can just be an email instead of an Ethereum address. And it's kind of interesting seeing, okay, once that's really easy to do, then people start being able to expand their apps to all sorts of new kinds of users. So I think those are the two. And I think we've seen over the last few years the design evolve more into this being almost turnkey for developers instead of like ZKPDP, which had to slog through like months of the primitives of getting it up to speed. But we learned a ton from that. Yeah, I'm curious what your takes are, though.
Yeah, I think for us at ZKPDP, we're particularly focused and excited about the idea of bringing Web 2 data and using that like all across blockchains, especially. I think if you think about like Web 2, all the data currently exists in these like centralized data silos. Like you basically can't export them to use anywhere else. Think of like your Facebook or your Facebook friends. You can't just take that and use it on Twitter, for example, right? And some of these like ZK primitives allow you, and I guess also like MPC with like TLS Notary, allow you to kind of permissionlessly export these Web 2 like data from these like silos and use that anywhere you want. And we're particularly excited about like putting these on chain because of this like global like incredibly neutral settlement layer that you can do like really cool stuff and composable stuff with.
Who goes with co-snarks? You are using them. I can go general purpose MPC. Well,
you built them.
I think, I mean, with co-snarks and MPC, for co-snarks, I think one of the nicest examples is actually what you were doing, and this is essentially doing private proof delegation. So with zero-knowledge proofs, if you want to generate a proof where like the witness gets particularly big and you're doing it client-side and maybe your phone is not powerful enough or you don't have enough time to do it on your phone, you might want to outsource it. And so you see all these proof markets popping up that offer services that can generate your proofs for you. But if you have any notion of privacy at all, or if you care about the witness data and not leaking this in the clear to everybody, then you might want to do this in a privacy-preserving way. And I think this is where co-snarks enter the story. So doing, private proof, like proof delegation, but maintaining privacy in an MPC way, I think is the one real sort of awesome use case that co-snarks offer that wouldn't be possible otherwise. So like in yours now, you don't do proof generation on the phone, you outsource it to the network. And then I think for general purpose MPC, I think the thing, for me this is the most exciting part because there you start to now be able to collaborate on private data across multiple users. So I think ZK is great in the sense that it gives you like this sort of control over your data. But in a way, it restricts you because it's like, okay, I have control over my data, but now it's stuck and I can't share it with you. And sometimes I want this sort of flexibility. I don't want this all or nothing. And so if I have this flexibility to say, okay, I can share it with you and you and you, or I can share something about it with you and you and you, and we can compute over it together, then this is great. So for me, this is like the real kind of new thing that's opened up by using MPC in a ZK world, let's say.
Yeah, so I personally feel like ZK by itself is quite lame for the use cases that we're thinking about, which is social applications. Like, I feel like social is inherently like multiplayer. You want to get like a bunch of people involved, and the coolest applications there involve multiple people's private information. And for that, MPC is a perfect fit. So I would say for co-snarks, the thing that's more exciting to me personally, is the idea that you can actually generate proofs about a group's data. So it's like the other side of the coin. And I think in general, like MPC, FHE, all of these things, cool applications or design patterns are like, one thing that we're trying to explore is asking questions to your social graph, asking private questions specifically. So one setup here is that like Richard could like have his like private data uploaded in some like encrypted form or whatnot, and I can just like ask certain queries, or I can ask questions like, hey, like who here wants to join the hackathon with me? Like, does anyone in my social graph meet these criteria and wants to like be part of this group? And these queries would only be decrypted if they're actually satisfying that criteria. So I think like the MPC FHE angle feels a little more exciting for that.
Absolutely. I wanted to also, so this interesting theme sort of came up about making connections. So from Web 2 to Web 3, from one node to another in your social graph. And it's also kind of making connections between the primitives, like CoSNARKs is a good example, MPFHE is a good example. So one question that's always at the top of my mind is security and how security assumptions compose both across primitives. So so you are introducing new cryptographic assumptions. How do these compose? And also across applications. And in that case, it's more about threat modeling. So for example, if you're relying on, say, the Venmo's email format, and they change it, let's say, or yeah, you're relying on like some DKIM server, some registry. Like, how do the threat models compose? So I'm so curious as designers how you reason about that, first of all, and also how you communicate it to your users, how you educate your users about it.
All right, I'll go first. So I think because ZKP2P is building like a financial application, if you will, we're dealing with like movement of, I guess, stablecoins on chain. So there is real value tied to it. We do like treat security pretty seriously, both on the cryptographic side and on the application side. I think on the I guess overall, we see like security as kind of like how comfortable are we like securing like this dollar amount over this amount of hours, for example. And I guess like different primitives that we use, I think fall under different parts of that spectrum. For example, like email may not be, I guess, the most, I guess, like gated and secured, for example, whereas like behind like a gated like private API with 2FA and everything, yeah, the data might be more secure. So I think we do account for all of that in like how much we allow like the max transaction limit to be in some of these protocols. And I think, yeah, I think we're constantly monitoring and seeing as these technologies mature, we feel more confident on it securing higher dollar amounts.
Yeah, I can also address trust assumptions on the ZK email side. I guess we think about this in two ways. One is around when things update, so you say your email template updates or the DKIM registry updates, it's one, very easy to change that. So we have a very simple builder where you put in the new format or the new parsing and it automatically handles everything for you. And so one thing is, okay, when a template changes, the developer's ability to react should be extremely fast. And then number two is we kind of want to make sure the system is robust to any weird kinds of like bugs or malicious DKIM key updates. And so one way we think about this, for instance, with email-based account recovery, where it really matters, like the entire security of your account hinges on, you know, it really shouldn't hinge on will this recovery module get hacked. And so one thing we think about is like very intentional time locks and kill switches. So for instance, like many of these accounts will have, once all the emails say, hey, I should recover this account to this new address, a 1-week time lock starts that's non-negotiable on chain. And so even if either the email server got hacked or the DKIM key got somehow maliciously rotated, or even like, you know, the user's guardians acted against their own will, then at least the account owner has a week to repair that. And so I think non-negotiable time locks has also been quite compelling. And the final thing is giving users the ability to exit. So, for instance, for the DKIM keys, if a user doesn't trust, hey, these oracles they've set for the DKIM keys are going to always act correctly, we've made it so that users can say, look, I have to approve all DKIM key rotations that are applied to my account. And so now we kind of show, you know, maybe in the UX, hey, confirm your Guardian emails and the relevant keys. And the user just kind of does, say, some passkey authorization, and that'll automatically check, okay, I'm going to do the DNS check, did the DKIM keys match, okay, I'm going to rotate them on chain for this user specifically. So allowing users to have control over their own keys within an intuitive manner, I think is also quite important. So yeah, these are the 3 ways. Easy updates, having it so that there's non-negotiable time locks, and giving users control over their own keys or parts or oracles so that they don't have to trust it.
Yeah, sure. For MPC and FHE, security is generally a lot more difficult. Like, there's been so much money being put into ZK audits and all these rollups and everything that, like, people know how to audit circuits very well. And for MPC FHE, this is maybe becoming more of like a nascent thing. So we'll see how that progresses. I think there are certain things you can do to make MPC FHE more secure. One way to look at it is there's this notion of direct security versus delegated security in MPC. So delegated security is when you take your private data and you split it up and you give it to all the MPC parties and they run this computation, versus direct security is you are actually running this computation yourself. And you are one of the parties when you actually want to run compute over your own data. And that's like a simple way to say, oh, it's your own data, you should be a part of the computation. And I think that simplifies part of the equation or some of the threat assumptions. But I think for MPC, FHE as a whole, like, we're still trying to work this out.
Maybe I can add something on, like, I think you talked very nicely about the composability, but maybe I can try to say how this translates to users. And I think to end users in particular, like, now we start to hear that, like, oh, people do start to care about privacy and, like, okay, yeah, we do have stuff to hide. So people do start to feel something about privacy, but I think they really don't understand, like, the nuance or even the language around it. So, like, explaining to end users, like consumers that we're talking about now, is just hard. And, like, but even, like, for us now, we start to kind of onboard developers to use MPC tooling in the network. And it's like, even to developers, it's really hard to explain. And I think a lot of developers even have, like, a lot of confusion around the security assumptions. And, like, it's actually a little bit worrying. And so like, and as you said, like, there's no auditing and, like, there's little sort of support for security in MPC and FHE and this slightly more advanced primitives. So at least we talk a lot. I mean, like, all of us talk a lot to each other about, like, okay, are we right in thinking this? And, like, with you, I was talking about private proof delegation, and I was saying, like, okay, just outsource everything. And you were like, okay, no, we're happy to outsource some stuff maybe, but, like, if there's, like, a whistleblower or something that's, you know, particularly sensitive, or, you know, then no, like, everything needs to be done client side. So I think having conversations amongst each other to, like, raise the general bar of education, like, either amongst consumers and the developers and, like, the researchers and everyone, yeah, generally just raising the level of education, I think, is good. And that's what we do, and try to, yeah, inform each other.
Yeah, I love that. I think a lot of, since we're building at a very early stage, a lot of it is about talking to each other and communicating well, communicating, like, in an intuitive way to users. So to that end, I want to sort of find out, like, some practical insights that you've gained from your experiences deploying these apps in the wild. So by practical, I mean, like, insights that you could not have gained from, like, just writing a white paper, just implementing it in a hackathon. For example, UX features, like I used making it clear to the users that they can control the set of DKIM keys they trust. So, like, UX prompts, how these cue behaviors in users. I'm interested in that. And I'm also interested in sort of how we compensate for the UX hit. So a lot of these apps, they involve heavy computations, right? for example, making a ZK proof. For example, having to be online for a long time for the MPC or FHE. Well, not for FHE, but yeah. So having to wait for a long time, be online for a long time, like these are UX hits that we have to take. How have you been dealing with those? So that's on the UX side. And then I'm also interested, like on the infra side, like actually what are the infra requirements? Like what difficulties have you run into? Yeah. Let's do the UX stuff first. Like what interesting user behaviors have you observed? What sort of UX prompts, UX patterns have you found useful? And how do you compensate for like the UX hit, the performance hit in these apps?
Okay, so for ZK P2P, we have two flows of interacting with these like cryptographic primitives that we use. The first one is obviously using ZK email. I think the main thing about using ZK email is trying to get that email in your inbox to start the proof generation process. And that's been a difficult thing to resolve. Basically, the manual way is you have to open like the raw email, copy it, and then paste it into the UI, and then click a button to run the proof generation process. So we basically built like a OAuth. We got a Gmail API OAuth flow that will basically OAuth into your inbox and read the email, but keeping it completely local and client side to kick off that proof generation process. So that has helped with UX a little bit, but it's obviously like a workaround kind of thing in trying to smooth out UX things. And also, after extracting that email, the next step is obviously generating that proof. Venmo email circuits are like massive. They probably will take like 8 minutes to do client side, but like 20 seconds to do on the server. So we pass it all through the server. And so far, I guess all of our users are fine with that. I think they're okay with that, leaking that level of privacy.
Do they know that they're sending the plain text email?
We disclose everything to the user that we are doing that. And then I guess the second flow I was going to talk about is we also use like TLS Notary, which I guess for that flow, you basically need to have the users like credentials in order to generate that like MPC proof. So in order to get that, you basically need to install or create a browser extension to scrape those that request and response in order to pass it to the MPC proof. And of course, all of this is done local and client side. But yeah, I think the reason for that is that's kind of non-negotiable. Like us storing cookies on a server, running cookies through a server and their credentials is like a complete no-go, whereas email is a little bit more okay in terms of privacy. But yeah, that's also a kind of UX hurdle we had to deal with, like trying to get users to install a browser extension and going through that flow.
Yeah, maybe one thing ZK email learned a lot from ZK P2P is that, it's always important to have the clear user flow. So actually, after you guys added the Google OAuth flow and realized people are actually using this, we added it to all of the existing ZK email apps too, where it's like you can, because we noticed, hey, as long as there is a way for users to do the easy path, and as long as that means we have to offer a way for the self-hosted or fully private path. And so it's kind of, as long as that path exists, it's kind of fine to have an option for easy users who don't care to just use the kind of simple sign in with Google, select the email, move on path, as long as it's possible for the people who really care about privacy to get that privacy they want. Either they manually upload the email, they select do it client side, they're willing to take the UX hit in exchange for privacy, or, and this is one of the advantages of having a totally open source organization is that all of our repos are open. Like you can go, if you don't trust ZK P2P's front end, or you don't trust ZK email's front end, go to their GitHub repo, clone it locally, run it, and if you really, really care about privacy, there's always ways to get around the ease of use turnkeys that we've put into the UI. But For me, it's kind of like we've learned, okay, as long as there is the easiest possible path and a way for someone who cares about privacy to do the private path, we feel like that's been like a good enough mix of things, even if people in general don't necessarily always do the private path. So that's one UX pattern we've noticed has been really nice. Yeah.
Yeah, bunch of thoughts here, I guess. First one is about privacy, and like, I feel like one of the main appeals of building consumer apps with programmable cryptography is the privacy you get, right? Is the choice and the consent that you have, and that is like one of the major reasons why these technologies are so powerful. But I feel like if you go down the street and you just like talk to people, I think what I've noticed is people just don't even understand privacy from your peers versus privacy from the server. Like this simple concept of like, hey, they look at your Venmo history, and if you look at it, you can have like Venmo or whatever payments app you use, like you can have transactions only visible to your friends, only visible to yourself. Like people think when you set your transactions to be only visible to yourself, like that is privacy, right? That is like just privacy in general, that's what that means. But it's like a completely different concept when all this cryptography offers privacy from the server, which is really what we're aiming for, right? Like we don't trust server to get hacked or to be malicious or all this stuff. And I feel like this is really like a critical question we need to solve in like communication and design of how do you actually convey this to users. So here's one idea I can propose, which is like from Rachel at Cursive and also Tomo from the EF. Like they're both wonderful designers, and they have this idea, which they can talk more about, of like, hey, we should have some sort of like standard UI kit for like communicating to users. Like when you see this interface, it means it's actually private from the server. Like this looks totally different, it feels totally different, it is different, and that's actually connected to the technology, right? Because right now there really is no difference and people don't understand that. So I feel like having something like that where when the user actually uses the app, that would maybe change their perception of things a little bit.
You mean like a incognito mode or something?
Yeah, something like that. Like incognito mode, like it feels different because it's like dark.
Yeah.
Right? It's like, or I think of like the TLS like green lock icon. Like at the very least having some visual component where it's like, oh, it's not like a standard or something, but it's basically this norm you assume that if we have this green lock icon, then your connection is like more secure in some ways, and we're just gonna all like uphold each other to this promise. Because at the end of the day, like this is all up to like people building apps to just agree on and to like call out the people who don't follow this and to all work together to communicate.
I think that's a super nice point, and like if you look at cryptographic papers or whatever, when they like draw the protocols and the primitives, like they do have a sort of like it's hashed box, like there's lines in the box when things are secret shared, or it's a clear box when it's in plain text, or it's black when whatever. So it does exist, and I think this is nice. But one other point that I wanted to mention was a bit still on the design side, and also from Rachel, I guess, or from Cursive, is like that you really play with the ideas that, you know, like the concepts that these programmable crypto primitives give, and you sort of, you play with them in your own minds and sort of somehow translate this. I don't know about design or how you do it, but like you somehow translate this to the user. So like downstairs in the museum, there's these art pieces where there's the QR code that you can scan and input an emotion, and like it explains like, hey, we're going to send a hash of this and like prove that you know the pre-image. And like this is so cool. Like even just showing people the language and showing people like just mentioning it, just saying, okay, this is what's going on here, I think makes people aware, and like it's like, okay, cool, I'm doing some crypto.
Yeah, and so I was just getting lunch with Gordon, who's like the artist behind that piece. Like basically like we were talking about ZK cryptography for a while, for a few hours, and like he made this wonderful art piece explaining how you can keep your emotions private, blah, blah, blah. But I feel like what came out of that conversation is that the most important thing for all of us who are building apps in programmable cryptography is communication. Like we cannot just be technologists. Like if we want to actually build apps that people use, like we need to communicate and we need to talk to people and like explain, hey, this is what privacy means, this is why you should want it, this is what decentralization means, or whatever. Like communication is arguably like more than half the job. You can't just build the technology, build the primitives, and just like throw it out there and hope something good's gonna happen.
But it's not even just regular communication. It's like you make it look cool and fun and entertaining. And like if I'm using an app, okay, unless it's like a super serious thing that I want actual privacy, like real privacy for, fine. But if I'm just like using an app, I'm probably doing it for some sort of entertainment or like some fun or to like engage with my friends or whatever. Like, and then having it like look cool and feel like a shiny, cool app, then it's great. And I think this is something that you do well. Like, it feels cool. I want to be part of it. So yeah, I think.
Yeah, like that's what's cool about Cursive is like they make it like joyful, social, and like it's sort of turning that privacy as like isolation and darkness kind of metaphor on its head. So that was really cool. I think, yeah, all these UX insights, there's no way to get them without deploying in the wild, without being in production. I guess I'm also interested in sort of on the back end, like on the infrastructure side. So I guess I have two sort of questions about infrastructure. First of all, is it expensive to run these apps? So it's a leading question because I know it is. I want to know how expensive and then like basically what improvements do you see in store? What improvements are you excited about? My second question is sort of a spicier one, and it's about decentralization. So for example, WorldCoin. They're secret sharing their iris codes using Taseo to 3 servers. So to me, 3 is a small number. How do we, I'm wondering like, another example is TLS Notary. So they rely on a set of trusted notaries to be the other party in the 2PC. And how big is this set? So yeah, it's kind of an infrastructure question, but it's also kind of a decentralization question, like underlying these primitives, like what implementations and what infrastructure are we actually using? And yeah, what are your thoughts on how this will develop?
Should I start? We laughed when you brought this up, and I wanted to explain why we laughed. And I don't know if I should say it like in front of a room because we haven't discussed this at all with the teams. But like, so like this week was the first time we deployed, let's say, co-snarks in like prod, like properly. So like this week it's like fresh out of the oven and it's like messy. It's been a bit messy.
It's all our fault. They didn't do
no,
anything
it's
wrong.
not like
totally
it's no
our
one.
fault.
So like, so the situation is this: like we have established a network. So Tatseo is running a bunch of nodes, Cursive are running a bunch of nodes, and PSE are running a bunch of nodes. And they all do computation. They do a multi-party computation between them and produce a co-snark. And so some of the things you might learn when you go into prod that you wouldn't learn in a hackathon. Like, as you said about like auditing and security, like being immature for MPC and FHE and the more advanced things, yeah, like infrastructure and support there is super not in place yet. So like yesterday we had a bit of an incident where 2 of the nodes of one of the parties died and they had 1 node left. And so this
is our party.
But like, okay, there was some sleep involved because they stayed up all night to finish the thing to actually get it done for Devcon. So it's a good reason. But yeah, like just the nodes died and they just needed to be rebooted, and that's it. But there was no like alarm or notifications or like anything set up. You know, this kind of like support that just keeps things online, or like small stupid things that are like the absolute like complete like essential things in any sort of advanced tech, not even advanced, but like used tech. Like the most basic things are not there, and we focus on just getting things working. But like yeah, this sort of support to keep it going, it's just not there. But and in terms of cost, I also don't know if I should talk about this without knowing exactly, but like I think for us setting this up, I think, is it for each party? I think it's about $7 per day for like seriously beefy machines. So
yeah,
not too bad.
Yeah, I don't have much on numbers that I know of concretely, but I think in terms of like what you said, like this is not something that we would have learned this quickly if we didn't deploy it, right? Like this, we were using CoSnarks for like the leaderboard, for like handing out merch downstairs. Like if you tap like 40 people, you generate a proof of it, and like you can get a shirt, the shirt that I'm wearing, which is super sick. But like we learned of this incident like literally 30 seconds in because people's leaderboards like weren't updating and they couldn't get their shirts. And like they were so mad. They were like, oh, where's my shirt? I want my shirt. Like my leaderboard isn't updating. So I feel like having that feedback loop instantaneously is like super useful. And we learned this lesson and like we fixed it overnight and like now we learned something new.
Maybe I can add one good point and then I'll be quiet. But like the good point is that we had we generated many more CoSnarks than we expected. So like the load was much higher than we expected. And the reason it went down was like, yeah, like it was not because of, let's say, so much load. But like we're handling much more throughput than we expected we could in like pretty good times. So that's the good outcome that we wouldn't have also expected without going into prod. And like a lot of it is because of the response of people at the conference actually. Like people are super curious and cool to try it out. So that's something we wouldn't learn.
Yeah, that's a good problem, like higher than expected throughput. And that's a good like alert system. Angry users demanding shirts. Those are like the joys of deploying in the wild and having real users. So I do think I'm supposed to open to questions from the audience, but I don't see any questions, do you? You don't really?
I think questions after that time.
Oh, okay, so we have 9 minutes left and then we'll open to questions. Great, because I'm really not done here. Yeah, I think the second part of my question was, like, what do you see in the future? Like, future improvements that you're looking forward to? I, in particular, want to ask about mobile interfaces and whether, yeah, that's a priority for you guys. What challenges do you see, like, sort of what blockers do you have right now, and what challenges do you see in future, or what needs to happen to make like a joyful mobile experience for the users?
Maybe one thing we've thought about on the infrastructure side and on the mobile side is because proofs cost a couple cents on a server and will cost a couple more cents if you do CoSnarks, there is quite a pressure to push things to the client side because then it's free. The user handles the computation for you. And so one interesting thing is that if ZK proofs get really big and if people are doing, you know, not just hundreds of proofs a day, but thousands or hundreds of thousands of proofs a day, then there's a really big pressure economically to create client-side proving. And I think it's quite cool because client-side proving is kind of the holy grail of where ZK privacy comes in. You don't actually leak privacy to anybody else. And so I think it's actually potentially a good thing that we can incentivize this research. And so far there's only like, you know, maybe 2 or 3 organizations I can think of that are really invested in, okay, really we should get client-side proving today because you kind of like, you value in crypto often accrues to the points of centralization. And by saying we're going to do client-side proving, you're removing that point of centralization of we run the prover, we make the money. And so it's not currently economically advantageous for infrastructure providers to do client-side proving. But when applications are like, we don't want to pay, you know, hundreds of dollars a month or thousands of dollars a month to you, then all of a sudden applications are now incentivized to use somebody who is providing that client-side proving. And so, yeah, that's one thing that I'm excited about in the future, infrastructure-wise, and also for mobile proving. We've seen some teams like MoPro, like Ligatron, like teams in PSE, like Noir, really be like, how can we get this client-side proving done? And yeah, we're excited to see more of that. There's a lot of tech that has been underutilized, like WebGPU, SIMD acceleration, things you can get on mobile devices that you need for these email proofs because people, most of the time, are just going to scan a QR code, sign into their email on mobile, and make a proof. And you want to make that flow as fast as possible.
Yeah, I think for us, we echo a lot of the same things you said about client-side proving for our ZK stack. I guess for us, since we also use TLS Notary and the MPC side, we're especially also really interested in building like a mobile-based flow to enable some of our marketplaces. And the bottleneck there is, I guess, it's also memory, where like mobile has just much lower memory than on, I guess, browser. But yeah, also like bandwidth and internet connection matters a lot in MPC. And when you're on your phone, you're typically like out. So you may not have access to like high-speed internet, for example, to like finish generating these MPC proofs. And as a result, like the connection drops, and which is a terrible user experience for some people. But I think there are quite a lot of like improvements like coming soon on the MPC front, on the TLS notary front, which yeah, cuts the bandwidth requirement by like, I don't know, like a huge like factor. And yeah, we're pretty excited to adopt that and yeah, support mobile as a next step.
Yeah, I think like mobile is super interesting to us just because it has such a wide toolkit for social apps. Like things like Bluetooth, NFC, like web Bluetooth, web NFC, like they just suck. I don't know, they just don't work. Or like not supported by a lot of browsers. I think Apple has a lot of security restrictions on some things there. And it just sort of widens the toolkit of things that you can build in the social context. So I think like mobile to me is super important, and it also is just like a much more buttery experience than a web app. But then you have the question of like, how do you get people to download a mobile app? I don't know. Yeah.
There's these things called app clips now. You don't need to download a mobile app.
Tell me about app clips.
Yeah, it's yeah. So there's basically these app clips and instant apps on the Android store where like Google and Apple offer ways for you to like try out the app without actually downloading, going through the app store. So you basically scan a QR code, it loads some like temporary like a binary on your phone, and you get to interact with some limited features of the application without needing to go through the app store.
Maybe like one point that kind of touches on another question you wanted is like something that I'm excited about is something that I think both of you mentioned a little bit, is about the different models of MPC. So like the one where the user is actually part of the computation, or when yeah, it's a different, like you delegate fully everything to the network. And so like in some cases it can be that, you know, as long as one party is honest, that, you know, the whole thing can remain secure. And so if I'm involved in this protocol and I know for sure that I'm honest, then I can say that this is a good, like that this protocol is secure and there's no collusion happening. We're like quite, I think, not there yet at all for that, but like I would love to see this happening. This would be super cool.
Oh, absolutely. That's like one of the interesting thing about co-snarks as well, is because of the security guarantee from the snark side, you can relax requirements on the MPC side. And so, yeah, all these sort of interesting like paradigms emerge when you're like confronted with these use cases where, and they can, like these use cases become interesting in applications, like maybe in academia, they were not interesting theoretically. But yeah, like in practice, you realize, okay, like this is like an opportunity to like get some performance gains. Yeah, so that's a really cool point. I guess with my remaining 2.5 minutes, I want to find out what you're excited about. So yeah, what applications have you seen that are like, wow, far out there? Or what applications can you imagine? What applications would be like holy grail for you? And this can involve like, this can be extensions of what you're working on now, or it can even involve like far out primitives that you're looking at, like witness encryption or something. Yeah, I'd like to hear what's in store for the next few months and years.
I personally really want to see more digital signatures and more ZK proofs of those signatures. I mean, emails is just one example, but if you can get, for instance, the signed website standards to be more adopted, you can get any website front end now approved on chain. And you can already do this for some things like Forbes in Italy, but it would be great if more websites did this. I'm also excited about PUFs, like physical unclonable functions, being the root for new open source DEEs. I think like open source TEs is kind of a holy grail and gives us the ability to do a lot of this private computation without having to rely on Intel getting hacked every 2 years. What else? I'm excited about witness encryption. I think more research around new kinds of privacy modes, and maybe I'll even let Andrew talk more about that. And yeah, I'm also excited about more far out things like making certain versions of I/O a little bit faster, or making having MPC FHE be faster. Things like we've seen like Apple's Wall-E, they just released like a ML and FHE kind of application, and I think seeing more of that, more enterprises get into these privacy protocols, make them faster. Yeah.
So for me, I guess, yeah, like making things faster, like harder, better, faster, stronger is always the goal. But I think I would love to see more like what you are doing actually, and I think there's not so much incentive to actually play with these tools. And I think the gain from playing with these tools and like onboarding users and educating them is huge, but somehow people don't do it enough. And so like there are apps like yours, like Tonk, they're building these, like salon basically where Speakeasy, yeah, exactly, where you can meet your friends, like, and have this private environment where you can, yeah, like come in if you can prove some stuff, and like, yeah, this sort of transitive trust idea, like all this kind of cool stuff. Like this for me would be great. I'd love to see this actually happening more and more.
Yeah, I'm super excited about new applications of MPC. So specifically this concept called digital pheromones. And the idea here is that like real pheromones are these biochemical signals that you send around to find people you're compatible with. And what if we could build the same thing with MPC, but related to digital data, digital information? So you have these signals that you send around, and because everything is private, everything is safe, just like your normal pheromones are, you just get to see like where your compatibility is. You get to see who you match with, who you might be in a group with, who you might be able to do stuff with, and it just happens naturally. And so one way we can actually implement this is through a new scheme we came up with called Trinity. And Trinity is called Trinity because it's a combination of 3 schemes, specifically KZG witness encryption, garbled circuits, and Plonk. So the rough setup here is that you have your own private data and you just upload a KZG commitment of this into the cloud or wherever, and like people can just start asking you questions. People can start making private queries based on this data, right? And essentially like you only need to respond to these queries if you actually meet those criteria. Like these commitments are like pheromones from your data. They're like hiding commitments to your data. And you can just like naturally have other people around you ask questions and say, hey, like, am I compatible with this person? Like, am I able to do something with this person? And you can just discover that. And it's only possible because MPC enables this privacy and safety.
Yeah, I think I'm really excited about like more practical applications that like use these schemes that are like being like more and more robust and secure over, I guess, the next year. I think a lot of protocols, I think ZKEVM went through an audit, and a lot of these other like protocols such as TLSN will be, I guess, in the next year or two. And I think as these protocols become faster and easier to use, I think we'll see more and more practical applications like ours, and yeah, like stuff that you can do with Web 2 data come online. And yeah, I think I'm just really excited to see like combination using schemes, these different schemes in combination with each other in production.
Yeah, very cool. So I think now we're supposed to open to audience questions. I still don't see them. Oh, there they are. So we'll start with the most upvoted, which is, yeah, what's the path forward for mobile? Do we need a new browser? Who will fund it? I guess like we already addressed sort of outsourcing heavy computations from mobile, whereas this question is, I'm interpreting it more of like sort of the current standards of mobile. Like you mentioned, there's applets now, but there's lots of sort of restrictions on mobile apps that make it hard to say directly interface into like TLS notary, let's say. So like how do we deal with these standards that are incompatible with the primitives we need. How do we deal with them? Do we like start from scratch with a new browser? What do you guys think?
For mobile specifically, like, I feel like we just need more people building mobile apps and just experimenting. Like, that's basically it. Like, there's how many apps exist today on the App Store that are like mobile apps with programmable cryptography running client side? Like, I don't know. We don't have one. So I feel like we just need to learn the lessons there, pretty much.
Yeah, I agree with that. I think we need, more dev tooling, more developers building these kind of programmable crypto mobile apps. I think in particular, like, there's a lot of pain we experienced trying to do this the main requirements being able to extract like the credentials through like a web view, like privately, and keep it local. And Apple just doesn't give you, or React Native or any of the mobile frameworks they don't give you that tooling right now. So you have to be pretty hacky when you're developing.
I think on the mobile browser side, one thing we really want is there's this kind of vectorization called SIMD, and you can only access 64-bit registers in mobile right now, but if we could access the full 256-bit registers, you could do ZK proofs a lot faster. Similarly, WebGPU exists on most laptops, but doesn't have very good support on mobile. So I think in the short term, if browsers can ship those, that would be super awesome. And then, but I do think the large browsers will have that eventually in mobile within the next year or two, and that'll help accelerate a lot of these client-side proofs.
Cool. Okay, what are you going to have privacy by default, the hard path, not just privacy by complicated UI and default no privacy and limited security? I don't know how to parse this. Do you guys get the question? I guess it's kind of responding to something Ayush said about, it's okay to present an easy path as long as we make available the fully private, hard path of completely self-hosted proving. Question mark?
Maybe one thing I can clarify on that is I think it is possible to have decent UI for things that are private. Like, for instance, dragging and dropping the email on like a computer is not that bad. Like, it's still an option in the UI, and it's definitely harder than signing in with Google, but it's not like you have to download something and git clone and run locally. Like, you can still give option to do that in the UI, and we try to do that where we can. And so I do think, it's a fair point that forcing people to self-host is maybe not the best way to offer privacy, but I do think you can have buttons in the UI that, hey, this will take a little bit longer, this might require an extra action, but it'll be private.
How far are we from ZK-based transitive trust graphs of 10K plus users in dApps?
Good question. I'm looking at you. I would say, and I probably shouldn't say, but I would probably say it's closer than we think. I mean, it's a hard problem, and especially if you want to do this fully privately, like suppose you want to do like a full trust graph in MPC, you need to do like essentially a full search because almost everything is connected. So it's super inefficient, and it's not so good now. But I would imagine that the speed at which things are improving now, I would say not too far away.
Yeah, I think technically it's possible. For me, it's like how to design this protocol-wise. It's like, how do you do this the right way where this is fair for people? There's a lot of tricky, moral product questions that are to be answered here.
Mm-hmm. I was also thinking just now that FHE is one example where you cannot offload and don't want to offload to client side. You fully want the server to absorb the cost. So I guess, and the trade-offs, oh, sorry for gesturing. This is just my opinion. The trade-off is just individual users doing less work, and that could maybe allow you to scale to 10K plus users. But yeah, like you said, it's a big design space. All right. How do you solve the issue of querying large databases efficiently in MPC? all queries are linear in the database size? No.
Maybe one quick thing is like Apple Wally, like their new FHE system solves this by one, like bucketing. So you say, look, we're going to make square root of n buckets, and we're going to send it to the right bucket. But then you leak a little bit of information, which is which bucket did the query go to. So they send square root of n queries. And then it's like, well, you know, which query is the right query? You don't know, and the user throws away all but one of the queries. So I thought that was a kind of clever way to, you know, leak a little bit of privacy, but then undo that leakage and have it be a bit more efficient.
Oh, okay. So it's like linear over square root n buckets?
And you can keep kind of recursively doing the square root of n.
I see.
Yeah.
How about, I know WorldCoin does have this, they do a database search per new iris code.
So yeah, we do actually search over the full database for this. And like it is quite optimized and it's quite efficient, but like it's heavily specialized, optimized protocol so far. But I mean, there is work definitely on like lookup tables, and you know, like there are ways. I mean, people are looking into this and coming up with like clever tricks like this. But yeah, so far it's people are looking into it, but it is still an issue.
We need more PIR research. PIR is really cool. Private information retrieval.
Isn't PIR also like linear work on the server side though?
Yeah. Right now, I think you just like encrypt the whole database. Yeah.
But not for the user. Yeah. Cool. So I think we are over time now. And I really love this panel. Thank you so much to the panelists. Thank you.
Thank you also
All right,
for
thank you
making it
guys.
nice.
I actually had to sit in the audience because I wanted to enjoy this full panel. So thank you guys so much. Our next talk will resume at 4. Thank you. welcome back. Next, we have a talk on little things we've learned about FHE. Let's welcome CC on the stage. Also, there will be a QR code on the right side of the slide, so feel free to scan the QR code if you have any live questions for our speaker. So now, let's give a round of applause to CC on the stage.
Hello. Thank you, Teresa. Hi, welcome here. So I'm CC Liang from PSC. We're talking about FHE today. So here's my selected resume to fit my narrative. First, in August and July this year, I'm very honored to work with 0xPark, Lab, and PSC folks on the FHE project called Fantom Zone. And before that, in the past 3 years, I've been working on ZKEVM projects with Kimi there and with many people. And more before that, I was working on different various ZK applications in PSC. So I think in summary, what I have seen is a rise of computational primitives on cryptography. So what does that mean? We discovered a bunch of computation Legos. These Legos starts with gates like this. You can add numbers together, or you can multiply numbers together. And we call these gates arithmetic gates. And if you're coming from a programming world, you've probably seen this AND gates, OR gates, XOR gates, and NOT gates. And you can fit bits inside it and do operation with it. These are called Boolean gates. So these are kind of abstract models. Once you get this, you get the whole computation you need. You can serve user with different kind of application logic. How does that go? So first you have gates, and then if you combine these gates together, you get circuits. And then if you build language and compilers on top of them, and you feed developers some coffees and teas, and they'll build amazing applications and to happy users. So I think that's what happened in the ZK past. In the ZK, we kind of have some arithmetic gates that allows you to perform computations on secret values. And now, FHE, we are getting new sets of Legos, and they unlocked new sets of capabilities. And this is what we'll dive into today. So before that, let's do some recap on ZK calculation. So when we talk about computations, we usually start with calculations, and then we build more abstractions, and then we can do computations on actual application logic. So here is a circuit that looks like a Sudoku board. They have some pre-filled values, 7 and 3. You can fill in some initial value, 5, and then you multiply together, you get 35. You plus 3, you get 38. You can witness some private value 2, and then you get the result 40. And then you can send the input and output to the verifier, and without sending all the computation trace in the middle. And in this way, you get privacy for your private value. You also get the computation compression for people call this succinctness. And if we accept some more abstractions, developers are very good at turning your application needs into the computation of bits and bytes. So we can do some high-level logic like this. For example, you have ID 123 that is reside in the ID registry. This computation result tells us this is a valid ID. As this dog, you can insert some secret value in this secret field of ID. This ID has some certain attributes. And then the whole thing is combined together. This shows you know the secret. So you are the owner. This dog is the owner of ID 123. And then furthermore, this ID 123 has an age field, says 19. So that this dog is 19 years old. But the dog wants to tell people it's 19 years old. The dog wants to tell it's greater than 18 years old with just one additional computation step. So that works well for if your user is just one dog. But now, like, if you want to build applications that interact with multiple users, like this dog and cat, and they want to decide what to have for dinner, either khao soi or pad thai. But like their opinions are very sensitive, so secret they need some cryptography that can protect you from state actor attackers. So they kind of, let's imagine we don't have any cryptography and we host this computation on the trusted third party, like the horse below. And then the dog sends their vote 1, and the preference for pad thai 0. And the cat sends their vote 1 and the vote for pad thai. Then we perform some computations. We want to add the votes together and to get the final preference for the dinner. But then, like you see, like this requires the interaction of the dog's secret and the cat's secret, and then it's not achievable by the ZK gate. So that's where FHE comes to help. So FHE stands for, it's a short for 3 words, but I'm not going to torture you with that nerdy details. I was going to redefine FHE as just one word, and it's a computation over encrypted data. As people say, like the ticker is FHE. And so what does mean like computation over encrypted data? So you basically get these 2 new Legos, and then you can have encrypted data from player 1, encrypted data from player 2, and then you add them together, you get the computation result. And so when I heard like the encrypted computation over encrypted data first time, I didn't realize how powerful it is or like the significant it is. But if you see here, it kind of builds a boundaries between 2 players, and then you let their secret to interact with each other, and you get a computation result. So now, like with FHE, you can do the dinner voting properly. So the dog sends the encrypted preference, cat sends their encrypted preference, and then you use the new FHE gate and to add them together to get the encrypted computation result. And then you have to decrypt it to get the actual result. So I think Vitalik has a saying like all the technology we have is kind of a simulated trusted third party. And I think we, like from this example, we're kind of seeing this phenomena, like this horse on the bottom is kind of like a trusted third party. And when we're using FHE and without it, like the application logic looks similar, but like it's kind of wrapping on another layer of security. And for the user, from the perspective of user, all they see is the same. They input some value on their browser, and then they got some values from their browser, but like there are difference behind the scene, and there are different security and trust assumption behind the scene. So why are we not already using FHE now? We kind of already, like, so in the basement, you have Frog Zone from ZeroXPark. I highly recommend you to play it. But there are three main problems of FHE right now. First is the computation is costly. Let's say you want to send 1 bit of plain text from this dog to the server. You have to encrypt it, and in this encrypted message is a data itself, so it has some size. And how big is this data? So this data takes 6 bytes. It's kind of it's amortized, and it's kind of 100 times of the plain text. And it grows linearly. It means if you have 100 bits, you multiply 16 bytes by 100. This is already very good, but the terrible part is the computation part. You need a server of 192 vCPU. It burns 10 USD per hour, so I highly recommend you to play the frog games on the basement to feel that like $10 per hour like feeling. So the second problem is the verifiability. You're getting this computation result, but is this computation result coming from the correct computation step or the incorrect computation step? To be honest, like you cannot really tell. Like it needs extra work. You either wrap another ZK proof on top of it. You either do some like message check or something to either guarantee kind of integrity. It's a problem people are actively solving, but it's still a problem. So the problem number 3 is the decryption problem. So after all the computations, we're getting the encrypted computation output. But how do you decrypt this? How do you remove that elephant from the fridge? So you need someone to decrypt the message. But you can, give the decryption key to a centralized party. But this is like you are not doing FHE at all. But the concern is like if someone has the ability to decrypt the output, can they also decrypt other users' input? And this, this makes the whole like FHE a security theater. So the other way to solve this is you use some threshold decryption scheme. So every encrypted output, you need all the party to derive a decrypted decryption key share, and together they have to collect all the decryption key together to actually see the output. So if the dog did not give its decryption key to their input, the other people were not able to decrypt the dog's input. But the problem here is the cat. If the cat ghosted, then nobody can actually decrypt this output, and then this secret will be secret forever. So let's give a quick recap. The message is simple. In ZK, we kind of have computations on top of your own secret. And for FHE, we can engage with other secrets. So you can build applications for multiple people, and that opens a lot of doors to many new applications. So I expect like you will heard like the word FHE in the like near years. There will be more talks, more in the next Devcon. Like This is a kind of trending topic. And lastly, I want to direct you to play the frog crypto kind of basement to feel like how early days of FHE feel like. Also, if you're coming from a developer background, here are some repos you should check. The first two are from Gauss Lab. It's a library for multi-party FHE. Pay attention to the branch because like the latest code is living on some branch. And if you want you deploy your frog zone yourself, check the last link. You can deploy frog zone, and you know it's early days, things break, so expect some hiccup from the code. And yeah, that's all I have for you. Thank you so much.
All right, thank you, CC. We actually have a lot of time for QA, so feel free to submit questions. Let's go from the first one on the screen. What are the best use cases you've seen for FHE so far?
That's a very good question. So for me personally, like definitely not for others, like I'm more from like economic background, and I'm very interested in like auctions and votings. These are very, you know, like old FFG applications. They are very ancient, but I feel like if we can do proper voting and proper auctions, that would be cool. But people, like, I think what makes people exciting in the future is if you can build some private state, you can build a, let's say, P2P network. You have a private state, and then you have some state transition function. You can continuously update the states, and then you have some, you can build a, like, kind of private blockchain and private application to many, but like I cannot say anything concrete at this moment because I don't know.
And we have another one. Which optimizations do you see possible to solve performance issue?
So this is what I heard from our colleagues, Pierre. He said like the last, so the latest performance update was already in like 2016, and there hasn't been new papers for that performance improvement. So we might be looking for some like a new generation of bootstrapping technique to improve their performance.
When should you use ZK, FHE, or MPC?
So my you know over simplistic understanding of this is if your application involves just one party, then use ZK. If you have two parties, use MPC. If you have more than three parties, try FHE.
Cool. Yeah, let's wait a few more seconds because we do have more time for QA. What do you think of TEs as a solutions for shared private state computation as a performance solution over FHE?
Good question. I don't know yet. I haven't dived into this topic, and so I haven't developed opinions on this.
All right, perfect.
Okay.
All right, let's give it another 10, 15 seconds to see if I have any more.
Maybe a question for you, like who here have heard FHE before? Oh, okay, almost everyone, okay. Who here have heard indistinguishable obfuscation before? Okay, oh, nice.
All right, cool. Thank you, Cece, for your amazing talk.
Okay.
Our next talk will be in 10 minutes, so see you guys. Hi everyone, let's get ready for our next talk on non-native arithmetic via CRT codes by Liam Egan. There will be a QR code on the right side of the screen, so please scan the QR code if you have any questions for Liam. Now let's welcome Liam on the stage.
Hi, I'm Liam. Yep, thanks for coming to my talk. In writing the talk, I found that I think it probably makes sense to mostly go over sort of what non-native arithmetic is and sort of build up to the question, because this is sort of an idea I've been casually thinking about for a while, and I don't have like you know, definitive answer to yet. So, yeah. Do I push the button, or how does that? Is this working? The clicker? Oh, wait, it is working. Okay. Okay, so for people who don't know, what is like the context for all of this? So non-native arithmetic is something that comes up in SNARKs, which are succinct, non-interactive arguments of knowledge. You may have heard of like zero knowledge proofs, and this is the same kind of thing. So in a SNARK, some party, the prover, wants to convince the verifier that they know some witness. And they want to do this by generating a proof without interacting with the verifier, so non-interactively, and the proof should be small. And if it's zero knowledge, it keeps the witness secret. Yeah, and sorry for the formatting. I did the slides in Beamer and had to import them to Google Slides, so it might be a little weird. But yeah, so the way that we usually write this is there's some C, which is like a circuit that has some public input X and some private input W, and the protocol allows the prover to convince the verifier that they know W by sending a proof. So, for example, right, you could have some like chain state X, which is public, some transaction W that is private, and you want to prove that you know W for a given chain state. And so not all transactions will be valid, and so that's what C checks. Yeah, so the kind of important takeaway for our topic today is that C is defined typically over a field. So a field is like a place where we can do arithmetic, addition, multiplication, etc. And that field will be defined modulo some prime P. The field is sometimes sort of like a free parameter, depending on the proof system. You can pick the field freely, and sometimes it's not. So if you're using like a Stark, you can sort of, in principle, use any field. There's some caveats, but for like an elliptic curve-based proof system, it's usually fixed as part of the curve, which, again, depending on the particulars, is something you probably can't control. So the question that motivates non-native arithmetic is, what happens if we want to prove a statement about some arithmetic that lies in a different field than the one that we're defining our relation over? So, right, suppose you want to verify a signature that is defined over some other curve externally to your proof system, right? You want to verify a Bitcoin transaction or something inside of BN254. And in that case, both of your fields will be fixed, and you can't, change them, and they're different. So you have to simulate one field inside of the other. And so we need to emulate or simulate the non-native field inside of the field that our relation is defined over. So just like as a simple example of why this doesn't work, right? Suppose we wanted to check that like 4 times 5 mod 7. You can check that I think all the arithmetic there is right, and 4 times 5 is 6 mod 7. But then if our proof system is defined mod 5, then directly carrying out the computation will yield the wrong result. So they're fundamentally different spaces for doing arithmetic, and so you need to simulate the one inside of the other. So what can we do? The situation is not hopeless. Like in principle, right, this is a solvable problem because you can simulate or you can encode any NP relation into an arithmetic circuit over any field. You can encode it into binary digits and check that the digits are binary and encode the bitwise operations. And so this is just sort of like an existence proof. But this is, very slow, and we would prefer to do things more efficiently than this. And intuitively, you'd kind of expect it to be possible to do something better because fields are similar, right? They wrap around, but for small values, they behave kind of like the integers. You're just adding numbers, and if you don't exceed the modulus, then maybe we can exploit that somehow. That's what we're going to try and do. So the first observation is to check modular arithmetic. We just have to check integer arithmetic because if you want to check something mod R, this is the same thing as just checking some integer relation for a quotient. And in some cases, this is actually sort of enough by itself. So depending on the relative sizes of the fields, it might be possible to do this. Like if you check that A, B, C, and Q are all small, you can just check this relation, as written here, directly in the larger field. And the reason this works is because it will never wrap around the larger field. So if all the sizes of everything are small or provably small, then if it's equal to 0 mod P, it has to hold mod R. You can convince yourself of this, I think. It's not that strange, right? Because if something has magnitude less than P and it holds mod P, that means it's 0 mod P. And since it has magnitude less than P, the only thing that's 0 mod P with magnitude less than P is 0. And so this works sort of like up to square root of the size of the field, basically. And that's coming from the fact that we're checking a multiplication. If you were checking a degree 3 thing, then you'd want like cube root or something like that. But what if our, field's not small, or our modulus is not small, right? Maybe it's even bigger than the prime that we're working over. Then you can't expect your encodings of the small values in the larger fields to behave well. And in fact, it might not be possible at all. If your elements are larger than the field that you're carrying out you're encoding your relation into, you can't even commit to a big value in a single field element. So this technique, I think originally, or at least I first heard about it from Aztec, but there's this ancient theorem, the Chinese remainder theorem, that allows us to work around this problem. And so what that says is if you want to work in a big modulus, it's sufficient to work in 2 smaller moduli that divide the larger one, or that multiply to give the larger one, if they're co-prime. It's sort of like both sides of that are rings, right? So you can take a value, and instead of working mod AB, you work mod A, and you work mod B. And these 2 rings are isomorphic. And so people call it a residue number system. And you can represent a large number, mod AB, by representing it, by encoding all of its residues, mod different small primes that divide AB. Here I've written it with 2, but you can sort of recursively apply this equivalence to include arbitrary numbers of coprime divisors. And so remember, we were working mod P, and we had some R, and our R might be too big. But now we can pick whatever modulus we want, right? We can pick a bunch of small primes, so it's always large enough to recover the value that we're operating over. And so long as everything kind of remains small, that Q is supposed to be a product. But, so long as everything remains small, this works. And like before, how we didn't want to wrap around P, here we don't want to wrap around M. But here M is a free parameter. It's not fixed by the proof system. Okay, so now like a slight digression to explain the idea. Reed-Solomon codes are an error-correcting code scheme that is ubiquitous in snarks. If you've heard of Starks or Fry, this is essential to how they work. And the basic idea is we have some message that we treat as a vector of dimension k, and we encode it as a polynomial, as the coefficients of a polynomial. And then that polynomial we evaluate at more points. So remember, a polynomial of degree k, or k minus 1, is determined by k points. And by evaluating it at more points, you're adding redundant information. And so, like in the original conception of Reed-Solomon codes, this was to deal with the fact that some of the information might be corrupted. So you only need, even if some of the data is maliciously altered, you can still recover the original message. Certainly given all of the points you can recover. So given a polynomial, and we evaluating it at some set of endpoints, this is equivalent to reducing the polynomial mod this kind of degree 1 ideal, x minus ri. And so this insight allows us to generalize Reed-Solomon codes to other domains, ideal domains. And for example, algebraic geometry codes, which replace polynomials and evaluations with functions of some curve and divisors, can be cast in this language as well. And this is also how we're going to introduce CRT codes here CRT is still Chinese remainder theorem. So the idea of a CRT code is rather than encoding our message as a polynomial, we encode it as an integer. And then, rather than evaluating the polynomial at multiple points, we take the integer, mod a bunch of small primes. And so you can think of these mod small primes as analogous to evaluating a polynomial at a point. It's not exactly the same, right? Because the ring you get from reducing mod different primes is not the same. But the ring you get from evaluating at a point is always the same. But it's not really important for our purposes. Yeah, so if you have enough primes so that the product of all the primes exceeds like the bound of your original sort of space of integers that you're encoding into, then even if some of the primes are wrong, in the same way that with a Reed-Solomon code you can correct errors, with a CRT code you can also correct errors. And this encoding is the same as a residue number system. So you're taking an integer, you're reducing it mod a bunch of small primes, you're keeping the residues, and you can just work with those. And for those who are familiar, there's a lot of similarities here with how you know, Stark's work and other kinds of algebraic proof type stuff. Okay, so this slide I just screenshotted because it was horribly mangled by the formatting. So the sketch of the protocol is, suppose we want to verify some non-native arithmetic. So we have some system of polynomial equations, the f in different x's, which are integers. And the f's have degree d, and all the integers are bounded. So in the original version of this, right, we'd be checking arithmetic mod some other prime, and you can encode that as an integer relation. And so the primes are fixed in advance, and you have some m, which is larger than the kind of maximum value achievable by f. As written, it's a little wrong because you probably want to account for the additions, but you know, it's something like that. And then you encode your integers, mod all the small primes, as we described, and also provide quotients for the evaluations of these functions. I guess as written, those should all be 0. So maybe there's a slight confusion there. But yeah, so you prove your encoding of all of the integers is sort of within its appropriate range. And then you choose a random subset of the primes to test the relations over. And for simplicity, assuming the primes are all like roughly the same size, then you can calculate the success probability of a dishonest prover pretty straightforwardly. You know, it's just the probability of having like some code word, right, some set of residues that does not correspond to a small integer, or that's like wrong in some position, and then yeah. Anyway. Yeah, so it's similar to how Starks work. Okay. Yeah, okay. So this is the interesting stuff. As described in the previous protocol, we're testing each encoding of x as close to a small integer directly. You're just taking your set of residues and checking that it is close to a small integer, or an integer within the right bound. This used to be how like Frye-based proofs did things, but it turns out that there's a much more efficient batched proximity test. So the proximity test here is you're testing the closeness of the set of residues to its space of correct messages. And what people do now with Starks is take a random linear combination of encoded columns or encoded integers and test that the random linear combination is close to a code word. So instead of testing each one independently, you can just take a random linear combination and test that one thing. So the question is, can we do the same thing here with CRT codes? So I think so, but it's very different, right? Because in the Reed-Solomon setting, you have polynomials, and you're working over a field, and you're taking a random linear combination over the field. Here, we have a set of integers, and we're taking a random linear combination of these integers, but there's no obvious base field in the same way that there would be for polynomials to take a random linear combination over. So instead, we would pick a random integer linear combination to take of the integers. And this has a lot of interesting issues. So for example, this is not sensitive to encodings of small rational numbers. If you encoded like 1/2, then there's like a 1 in 2 chance that a random linear combination will cause the 1/2 to go away. And you might think, well, we could pick primes to multiply by, but that doesn't really work. So it is in some sense fundamentally different, but I think that it's possible to do this. The question is just like how good is it, and if those things can be worked around. So for example, for working mod R, this is kind of fine, because small rationals are also valid sort of to reduce mod R for large R, but there's lots of details to be worked out. So yeah, just some overview of the things I haven't talked about in this talk. So I mentioned a little bit that CRT codes, the notion of distance is a little bit subtle, especially if the primes are not all like the same size. They can't sometimes always be, I mean, right, like every prime is of a different size, so you have to account for that. It's not like a fundamental problem, it's just a little more complicated. As well, I mentioned this decoding to rationals rather than integers, which in some applications is fine. It might not always be fine, so have to work that out as well. And then another thing I haven't talked about, but that could actually be worth considering in practice, is all of this generalizes from integers to number fields. And in number fields, you have a sort of different situation where the first point, you actually can have primes that are like of the same size, right? If you have some prime over rationals or the integers that splits over a number field, then that might yield like a more convenient thing to work over. And in some cases, this sort of works. And then you have to ask, like, how do you define the size of things and so on, but just more technicalities, I think. And then one other interesting thing worth considering is, so we moved to the integers, and we were no longer able to take random linear combinations over an extension of the base field. But what happens if we work over Starks with polynomials, and instead of taking a random linear combination over the base field, we took a random linear combination of columns by random polynomials, not over an extension field. In this way, it's sort of analogous to taking an integer linear combination of integers, and it has a lot of the same problems, but it would allow us to avoid ever working with extension fields, potentially. So I think that would be an interesting direction to explore if this work ends up making sense. And that is all I have. Thank you.
All right. Thank you so much, Liam. We do have a question here. Could you repeat how you calculate which primes are small enough to use for creating a CRT encoding?
So I guess there's two ways to, or I'm not sure what the question is referring to, but for encoding into like a residue number system, the primes can be any primes. You usually choose them to be small because working mod small primes is much more efficient. This question could also be talking about the example that I gave where you can simulate arithmetic mod a square root sized number in a larger field. And that is just coming from the fact that the relation that you're calculating over can't exceed the field you're operating in. So you fix some field that you're actually working over, and then if your field that you're simulating is small enough, then everything kind of just works out as long as everything remains smaller than the characteristic of the larger field.
All right, perfect. We do have a little bit of time for questions, so let's give it another 10 seconds to see if we have any questions. What is the size of the coefficients in the RLC, such as that security is still 128?
It's a great question. I'm not sure. I think, I mean, you can sort of work out that they need to at least be drawn from a space of size 2 to the 128, but I don't know how much loss you get from the protocol itself. So I would say at least 2 to the 128 sized space.
All right, perfect. Thank you so much for the
Thank
amazing
you.
talk, Liam. So we will resume at 5 for our next talk. Welcome back, everyone. I am personally very excited for our next talk. We have Jens Groth, the inventor of Groth 16, to give us a talk on the verifiability vision. Let's give a warm round of applause to Jens on the stage.
Thank you. Hi, everyone. Yeah, so I'm going to talk about the verifiability vision. So the idea is that we want to verify the full digital world. And I think it's something that resonates with many of you, right? This is also what we hope for in the blockchain world, that we can create sort of like very trustworthy data that people can rely on. So this slide here is sort of like the very short summary of what is the verifiability vision. Alessandro Chiesa and Aaron Troma in 2010 introduced the notion of proof-carrying data. So the idea is that you have data, and data comes with a proof of correctness. And whenever you compute a new piece of data, you sort of like take verified data, check their proofs of correctness, and then you know that you're relying on verifiable data. You can now compute your new piece of data, and you can create a proof that this computation is correct, right? And that proof would both show that you computed correctly, but it will also show that, well, all the previous data, the inputs you had, were also provably correct, right? So you have this recursive composition of proofs that means that the whole graph of data that you're computing is verifiable. Okay, so what are examples of things that we would want to claim about data, right? So imagine you're reading your online news site, right? You may see an image, and it would be nice to know that this is actually a correct image, not some fake information. And nowadays, there are some cameras that sign the data, so like what are the GPS coordinates, what is the time, and so forth, right? So as an witness to this being a correct image, you may imagine that using the raw data from this camera and the GPS coordinates and the signature and so forth, right? And then the proof might demonstrate that, you know, this 100 kilobyte image that you're looking at is actually derived from a much bigger set of raw data with these kind of meta information associated with it. Other examples, if you are building online voting systems, you may encrypt votes for privacy, right? But then, you know, these systems can get messed up if somebody submits an invalid vote. So there you may have proofs that the encrypted vote is valid. And here it's actually important to have confidentiality, right? That you don't want to leak anybody's vote. You just want to make sure that they're actually casting a valid vote. So like the poster child example that we use for zero-knowledge proofs is that identification purpose, right, where a customer wants to prove they're over 18 years old, and people are now sort of like actively going out and getting data from, say, passport chips or something like that, so you have some raw material to work with to give these kind of proofs. And in the blockchain world, there's a lot of applications, right? So for instance, you may want to prove something about a smart contract execution. Okay, so let me sort of like generalize that a little, right? So cryptographers, they then think about this as a class of statements, okay? And talk about proof system for these class of statements. And there we have typically a setup that we expect to be publicly available to all parties. Sometimes there's some trust assumption in that, so there may, for instance, be a ceremony in which you could create that. But if that is once that is done, then it's there and available to everybody. And then you specify a proof algorithm, a verify algorithm. The proof algorithm would take the prover key, the statement you want to prove, and potentially a witness, if there's such a thing, to this statement being true, and produce a proof. And the verifier, conversely, would take the verification key, the statement, and the proof, right? And then either accept or reject. And this was invented back in the 80s, where the definition was that it should be complete. So if it's a true statement, then the prover has a witness, it should be possible to create a proof. And conversely, if it's a false statement, then it should be infeasible to create a proof. And then the twist in the story back then was that, well, it turns out the proofs can actually convey that, well, this is a true statement without conveying any other information, right, which is very surprising. So the zero-knowledge property is that, well, the proof reveals nothing about the witness. It just gives you one bit of information, namely that the statement is true. So it's this kind of proofs that we would want to give for the data that we want to verify. What I want to talk about today are what I see as challenges for proof-carrying data to really take off. So like 4 aspects of that I want to talk about: the versatility and ease of use of these proofs, the cost that comes with them to create them, composability, right? Because the idea of proof-carrying data is that you actually compose proofs. You would have like inputs, and they have some proofs, and you want then to compute new data and give proofs for those, and so you have to have some composability of the proofs. And then I'll talk a bit about the trust anchors. How do we link these proofs to real-world data? Okay, so this is like a bit of a history of like, how did people go about sort of like ease of use for developers in the olden days. And this is an old picture of me. I did my PhD work working on voting systems where you needed to create proofs of valid votes. And back in the day, the way you construct a proof system is that you hire a cryptographer and then they construct a special purpose proof system for you. And then in the recent years, there's been a lot of exploration of building tools that make it easier to construct proof. So something we could dub as sort of like the ASIC approach is that you have a program, you want to prove that inputs to that program yield a certain output. Well, let's compile the program into a proof system that can handle that. And more recently, there's a lot of teams now working on ZKEVMs, where this is sort of like giving you a more traditional experience of proving something. So the idea is that you take a program, you compile it down to something that the VM can execute, and then the VM takes this executable file, the program P, some inputs, and produces an output, and together with that, a proof that the computation was correct. So let's dig a little more into what does that look like? So ZKEVM takes as input a program. At Nexus, we're using RISC-V as the target programming language, but there are also many teams building ZKEVM, so you could also find this for WASM or special purposes languages like Cairo and so forth. Then the program can take an input X. They may also take a witness W, and it will produce an output Y, and then a proof pi that this output is correct. And there will be a matching verify algorithm that then looks at the program and the inputs X and the output Y and the proof and decides whether it accepts this proof as being correct. And the whole goal for all these teams that are building ZKEVMs is to give a very easy developer experience, right? So the way it will look like for a developer is something like this. You can just use a command line and you can prove or verify these computations. So I think we're getting somewhere with sort of like the ease of use from a developer perspective. The next thing, the next barrier, I think, is the cost. So let's sort of like dig into where we are right now. And I think the whole community has settled that the type of proof that you want is a snark. Okay, and what is a snark? Well, it's one of these proof systems where we want the proof to be succinct. Okay, so the succinctness property is that the proof is really small. okay? And we're talking about, in the best cases, something like a couple of hundred bytes, okay? And the interesting thing is that it can be a couple of hundred bytes regardless of how complex the statement is, right? So imagine you have a program, it does like lots and lots of operations, but you still just get a very small proof and something that's very easy to verify. We want the proof to be non-interactive. And to give a little bit of context, because that's not present on the slide here, so in the olden days when people were thinking about zero-knowledge proof, they were thinking about proofs where you had an interaction, where the verifier was interrogating the prover. But the nice thing, if it can be non-interactive, where the prover just produces the proof and then it's done, is that now you can take these proofs and you can copy them and you can distribute them, right? So if you see a proof for some claim, then you can just make a copy and you can send it to somebody else and they will be convinced as well. And then we want it to be an argument of knowledge, which is sort of like a technical way of saying that the only way you can construct a proof is if you were also able to construct a witness. So in other words, you ensure that it is a true statement. Okay. So when we have succinct proofs, right, then we have these very small proofs, and the verification time is really small as well. It's independent of the program execution time. It's also independent. The verifier does not take this auxiliary witness as input, right? And that's super cool, right? Because it means verification can be much cheaper than doing the computation itself. And I think this is like a key message here, right? That verification is cheap, okay? And that's what sort of like makes the verifiability vision possible, right? In some sense, all these data that come around with proofs, right? The proofs are for free, right? So it's sort of like from a user perspective, okay, I can get a piece of data and blindly trust it. Or I can, at exactly the same cost, almost, get the data and a proof that it's correct, right? Which one do I prefer? Well, if it's for free, I would want it to be verifiable. Okay, so where are we today? Proof size is really small. It can be as low as a couple of hundred bytes. The verification time is really low as well. It can be as small as just essentially reading the statement. What is the bottleneck nowadays is the proving time, and that's horrendous, right? So the overhead of like, you know, the cost to prove something versus you just compute it directly it's like many orders of magnitude. There's a lot of work going on to improve that, right? And if you sort of like look across time, right? Like back in the 80s when zero-knowledge proofs were invented, people didn't even think about like the efficiency of the prover. It could have infinite time to prove something. And people have become more and more careful. And I think now we're sort of like, you know, the way you measure it is you would talk about like, you know, how many cycles does it take to prove a cycle? So trying to compare apples to apples. And in the future, I mean, there's a lot of companies working on hardware acceleration and so forth, right? At some point, we may sort of like go to using physics terminology to measure something like, you know, how much energy do you spend per proved cycle, for instance. So we are at sort of like an interesting phase right now where we have these proofs that while they're efficient to verify and they're efficient to copy and transmit, they're really expensive to create, right? And the question is, who's willing to pay for that? Okay, and it's very nice, I think, zero-knowledge proofs have been fortunate to meet the blockchain space because there are actually a lot of applications where we're willing to pay for that in the blockchain space, right? And that could be because it unlocks a unique capability. It could also just be because there's so much replication going on when you're verifying computation, right? So think about thousands of validator nodes that have to redo the exact same computation to verify that it's okay on a blockchain, right? Well, instead of doing that, why don't we just send a proof along that's very easy to verify that, hey, this is a correct next block. And also, the cost of storage is something that can be prohibitive on a blockchain, right? So instead of storing a lot of data and so forth, now maybe we can just have a proof that says, oh, there is some data that would result in this end state. So one of those examples, right, are ZK rollups, right, where it used to be that you do on-chain execution, so you have this kind of like low throughput, expensive operation whenever you're processing transactions. And now we're talking about, well, why don't we do all of that off-chain, right? And we just compute what is the delta, what is the change that would happen to the smart contract from all of these transactions, and then create a proof that that's the case. And then we just give the change and the proof to the smart contract and it can update the balance. Okay, so the next thing I want to talk about is composability. So how do these things glue together? And here, it's really the succinctness property, why we like snarks, right? Because they ensure that these recursive proofs of proofs of proofs and proofs that you have when you do proof-carrying data and you're computing new data based on verifiable inputs, that they stay small, right? Because all of these proofs are small, and whenever, regardless of how many inputs and so forth you have when you're computing a new piece of data, you can still compute a small succinct proof for that being a correct operation. So the nice thing about snarks is that they compose well, right? They're succinct, so there's no size explosion in the proofs. They're non-interactive, so you can sort of like give them as inputs and be used in further computation. And the soundness of them is, well, cryptographically speaking, close to 100%. So also there's no degradation. It's not like you are getting sort of 9% and then you have another 10% loss in the next step and so forth, right? You're staying close to 100% soundness. And this is unlike other types of evidence you could give, right? So for instance, if you want to do direct recomputation to verify something, well, then you would have to send all the data along, right? So there would be no succinctness anymore. Right? If you wanted to do some interactive techniques, so like interactive proofs or spot checking or something like that, well, there's some interaction. You can't do recursion. You can't give that as an input to the next step. And for economic security techniques, which I think is a really cool idea, right? But it becomes difficult to manage this kind of economic security and track that over a long path of statements. One thing that's interesting about this proof cost, then when we use it in proof-carrying data, is that we can amortize the cost over many verifications. Right? So if you have a proof that you've created at some step, and then you're building on that, and you're building on that, and building on that, somehow you're accruing value of verification value in all these subsequent steps, right, that are relying on that proof. And I think this is sort of like a really sort of like nice thing, right? But it also points to sort of like maybe there's a threshold effect, that the more data we put into a proof-carrying data system, right, the more we can amortize the cost of creating a proof over many steps. Okay, so the last part I want to talk about are trust anchors and trust management. And in blockchain, we have the oracle problem, right? How can we get data into a blockchain? And the same thing happens with these proof-carrying data, right? Sometimes there are data that comes from outside, and we just have to trust them. Okay, and how do we incorporate those? And that's what I refer to as trust anchors, right? So there's a question of how do we incorporate that data? So maybe it's a camera that signs a raw image, Ethereum that finalizes block, and you have some sort of like threshold signature, multi-signature on it, or something like that, right? And this is an adoption barrier. So there are not many places in the world today where we get these trust anchors for free. People have to go around hunt for it. But the exciting thing, people are going around and hunting for it and trying to strip, data from passports and using that for identification protocols and so forth. It does lead to point to a problem as well, though, right? Which is proof management. What happens if a trust anchor fails? Okay, now you create a lot of data on top of that. You have proofs, right? And maybe you've lost, so like, what was the origin of that? So what if it turns out that, well, somebody who signed something, they're actually malicious and they signed some fake input? So I think there are lots of these kind of management issues that we still have to resolve with zero knowledge proofs and proof carrying data. And I think that's sort of like going to be something people are not thinking too much about now, but I think in the years to come, that's going to be an issue that is increasing in importance. Okay, so I want to wrap up. I've sort of like talked about some of the barriers I see and sort of like where we're going, and I'm hopeful that we're going to get there. So what is the end result? What does success look like? I think in the blockchain space, we're talking about the proof singularity. So think about taking all the computation and taking that off-chain and doing it where it's cheap, outside the chain, and really using sort of like the L1 chain as a verification settlement layer, right? Because that's what the blockchain is good at. It's good at verifying stuff. And more broadly, I hope we will sort of like be able to go sort of like beyond the blockchain space, or maybe we can hope for the blockchain space becoming sort of like all-encompassing. It's something that's very widespread in use. And they are what the vision I'm hoping for is sort of like a digital world where we have this web of verifiable data, right? And since verification is cheap, right, hopefully people would want most of their data to come with proofs of correctness, right? And we will have a much more trustworthy world. And with that, thank you for your attention.
All right, thank you, Jens. We're actually running a short on time, but we can take some questions. Type theorists have thought a lot about composition of proofs. How can type theory help with composability of cryptographic proofs?
Okay, yeah. I'm not entirely sure, okay, so, but I think, I guess I suppose it's been from a somewhat different angle that type theorists have been thinking about this, I guess in terms of like, so one thing that you're using type theory for is sort of like static analysis, like so will a program execute correctly, will it process the data correctly? And that is an orthogonal thing to what we are trying to do with these kind of proofs, which is more like, has it executed correctly? So in some sense, I think that is sort of like a complementary thing, and I think one should do both, right? So you should use sort of like formula verification in type theory to make sure that whatever you're doing is correct. And maybe for proof carrying data, there's also a question of like, how does one computation carry on from the next one, and does that make sense? And then you would want the proofs to make sure that, well, once you know that that is sort of like the correct structure of data and computation, then that has actually been executed correctly.
What are the advantages of elliptic curve-based proofs versus small field proofs?
Yeah, so I think elliptic curve proofs are, I think in some ways easier to reason about. You can have some very nice homomorphic commitment schemes like Peterson commitments. The disadvantage is that you're working with larger fields, and that can be a costlier operation. So if I had to conjecture, I think the world is moving toward using small fields rather than elliptic curves, just for performance reasons, and then potentially also for post-quantum security.
All right, and a lot of people want to see this answered. Should we be prioritizing post-quantum proof systems?
Yeah. So I think it's not as urgent for proof systems as it is for, say, encryption schemes, because the proof systems, if there's zero knowledge proof, they're succinct, they don't actually carry the data around, right? So it's more a question of like, how long time do you want the verification to hold, and nobody could break the soundness. But for anything you verify here today, right, then since, as far as we know, no quantum computers exist, that should be good enough. I do think that the world is probably moving towards post-quantum security anyway, just because of like, they seem to be pretty efficient techniques anyway for creating proofs.
What proving system does Nexus use?
Yeah, so we have several proof systems. So we have a ZKEVM. We've re-implemented the NOVA family of folding schemes from the ground up. So that's NOVA and Supernova and Hypernova we have in the ZKEVM. But we also have an implementation of JOLT in the ZKEVM.
All right, given the time constraint, I think we can only take one more. What's an application of this verifiable layer you would be excited for that isn't currently possible?
Yeah, so I'm very concerned about deepfakes and in general, so like the news that you get and the fake information you get, and misinformation, which is very deliberate misinformation that we're facing. So I would love to have a system by which you had much stronger guarantees whenever you were reading an article or piece of news that, you know, that there's sort of like a path back to the original sources that provided that information. I've sort of like tried myself, talking to journalists being misquoted, not maliciously. It's even worse if it's malicious. So if there's some sort of like way of saying, you know, in an article, guaranteeing, well, that the original person who they talked to agree that this is a correct interpretation and so forth, I think we could already eliminate a lot of misinformation. And I think this zero-knowledge proofs can be part of that. I also think that there are other components involved in getting to that solution.
All right, so unfortunately, our time is up, but thank you so much for the amazing talk, gents. welcome back, everyone. Can I just get everyone seated, please? So our next talk is on decentralizing consensus, and we have another legend that's going to be on stage. He is the co-founder of Ethereum and the founder of Consensus. So let's give it for Joe Lubin on the stage.
Hey everyone, thanks for coming. There we go. So this talk will have a different tone given the recent political shift in the United States than if it was written a month ago. Though I've lived in the US for years, I'm a proud Canadian. I would describe myself as politically centrist and neutral. If there was a progressive, rigorous, open decentralization party, I would be an NFT carrying member. For years in the US, companies in our industry have been living in fear, feeling unable to engage in certain activities that should be natural for a Web3 company, like issuing utility tokens, for instance. We're operating in a climate characterized by regulatory uncertainty. By regulatory uncertainty, by gaslighting and carpet bombing of our industry with inquiries that felt like inquisitions, Wells notices, and lawsuits from the SEC. The industry asked for rulemaking and engaged in good faith, but a strategy of regulation by enforcement action replaced the approach any lawful or constructive regulator would take, because the goal was to slow, kill, or co-opt our industry in the US. This was the case for three reasons. The progressive wing of the Democratic Party believes a large, strong central government should have granular control over the population. Two, central large financial institutions preferred to keep winning a rigged game rather than compete on the level playing field of decentralized finance. And three, the US controls as much of the world as possible via intermediaries, especially financial intermediaries. And Ethereum represents the most powerful, unstoppable disintermediation technology on the planet. There's been concern about a second American Revolution. There's indeed going to be another revolution. It will be a bloodless and probably bipartisan revolution that sheds the regulatory cruft and reformats America according to the principles under which she was founded. Liberty and justice for all, distrust for overreaching centralized authority, and a healthy reverence for self-determination and decentralization. Paraphrasing William Gibson, the world of decentralization is already here. It is just unevenly distributed. While it is finally looking like America is getting on track, decentralization has already been blossoming in many places where it is needed or where opportunity presents. Decentralized protocols flourish in places like Argentina, where industrious people need ways to route around the damage wrought by centralized government, or in Asia or in the Middle East, where the population is hungry for opportunity and agile in how it responds. We have an opening now to reformat the world bottom up, the whole world. The massive shift that America is about to drive, including an embrace of our technology, will become an imperative for the world's countries to follow. Something like the American experiment or the American project that began with the American Revolution and was soon followed by the French Revolution in the 18th century will soon take hold in various parts of the world. This age of enlightenment led to the development of the Western liberal democratic philosophy in many nations. This philosophy is characterized by many ideals that have been corrupted over the past few decades. Rationality, reason, and progress, individual liberty and rights, empiricism and scientific method, limited and democratic governance, pluralism and tolerance, and genuinely free markets. Our global decentralization project, the natural evolution of the American project, will bring new kinds of sovereignty to the people and communities of the planet. And it will grow viral, crossing different kinds of borders, because once you see decentralization at work, you can't unsee it. Our tech ecosystem and socio-political movement must always be about progression towards rigorous decentralization in the deep foundational infrastructure of the world. With rigorous decentralization, we get all of the characteristics of Western liberal democratic philosophy, and more. Specifically, we get open source, transparency and credible neutrality. We get permissionless participation and innovation. We get a world computer with a verifiable computation stack and software supply chain. Web3 will be the world computer on which all the world's systems will eventually be re-architected bottom up on the sounder foundations of decentralized trust and decentralized finance. With rigorous decentralization, we get censorship resistance and non-repudiable transactions and attestations. With censorship resistance, we get instant on-chain news alerts, disclosures of political business and social events, and unfettered journalism. Shout out to multiple concurrent proposers distributed globally. With robust real-time information, dissemination, and journalism, we get an informed public. And an informed public is an engaged public. With an informed and engaged public, we get healthy local, regional, and global participation in governance. Broad participation in open governance at all levels makes it hard for exploiters to capture and control the important systems of the world. With good governance globally, we get a healthy, rapidly evolving society. Waves of decentralization are cyclical. See the ancient Greeks and then the Romans and the recent American elections. But the secular decentralization trend has been underway for centuries as monarchies have ceded power to nation states, which have ceded power to joint stock corporations, first national, then multinational. And technology has increasingly empowered communities and individuals. The trend is to make sovereignty more and more granular. A simple definition of the network state. A network state is an online digital-first collective of independent actors. It can be humans, groups, or AIs, who are aligned with respect to exploring and addressing one or more issues. Network states can be realized as DAOs, social graphs, online discussion forums, or a combination of tools. Network states benefit from new Web3 primitives like decentralized ID constructs, verifiable credentials, attestations, governance tools, etc. Network states have the ability to create their own magic internet tokens for different purposes: utility, loyalty, governance, money, equity, memes, etc. People who are aligned with the mission of the network state might be inclined to do work in exchange for compensation in the form of some of these tokens. Others might also find the tokens of value for different reasons. Network states that choose to work together may swap tokens to establish greater alignment. A network state can bootstrap itself following various strategies. Bitcoin, Ethereum, and Solana can be considered a certain class of network state. Layer 2 networks can also be considered a class of network state. To protect decentralization, we need rigorous, incessant, ritualized vigilance. Thomas Jefferson wrote, "The tree of liberty must be refreshed from time to time with the blood of patriots and tyrants." We too will have to tend to the long-term health of the tree of decentralized liberty. Not with blood, but with attention paid and shrill commentary on crypto Twitter and other discourse platforms, and with attention and gas paid to systems that are constantly monitoring the threats to decentralization. Sovereignty refers to the supreme authority or ultimate power that a state, institution, or individual holds over a specific territory or group of people. Sovereignty has several dimensions: domestic sovereignty, the state's control over its population and territory; international legal sovereignty, international recognition of all states' independence and authority and no interference into the internal affairs of a sovereign. Sovereignty can be limited by constitutions, international agreements, or internal divisions of power. One can imagine a Web3 plus AI. One can imagine as Web3 plus AI enables new modes of living in overlapping network states, that we have the opportunity to define new kinds of sovereignty. And just as nation states define their forms of sovereignty, we've started to define new forms online and on-chain. One for individuals, online self-sovereignty in various forms via IDs, and other identity constructs, combined with reputational primitives like attestations, verifiable credentials, webs of trust, and rating systems in which the raters have skin in the game when they vouch for something. Two, for communities, online sovereignty embodied in DAOs, social graphs, and other mechanisms. These are network states that will take very different forms. They will operate as sovereigns in online domains, setting rules for their participants that are of, by, and for their people. Sovereign individuals are already becoming members or netizens of network states. Some of those network states will eventually have arrangements with one or more nation states. Some of those network states, enabling temporary or permanent rights to be resident there. The state of Wyoming, for instance, allows DAOs to register as limited liability companies. This is a small step, but we can think of it as cracking the door open, and that will lead to establishing relationships between network states and more traditional polities. Many nation states are facing catastrophic demographic challenges. They need more people to take care of the boomers and keep the economies from collapsing. Some nation states provide passports to citizens of other nations in exchange for investments in the country, and some nation states actively recruit for talented immigrants. Canada has targeted recruiting 485,000 immigrants to become permanent residents in 2024. We will soon live in a world in which legislators and regulators consider themselves in the service of the citizenry, as they do in Switzerland, and compete for companies and people to choose residence there. The internet begat Web 1, which begat Web 2, which begat Web 3, the re-decentralized web. The internet started out decentralized. It was a bunch of protocols running on nodes distributed around the US, then the world on wires provided by telecom companies. The internet was loosely governed by the IETF, a decentralized organization. Web 1 also started out decentralized. It was a bunch of open protocols and specifications running on top of the internet protocols. Web 2 picked up steam in the late 90s and early aughts as it became clear that there were billions of dollars to be made as some sectors of the economy were moving online and brand new sectors were being invented. Web 2 companies had exciting new primitives at their disposal in the form of protocols and open specifications, and some new ones were created. But the dominant mode of operation of Web 2 companies was closed source systems, and if you were fortunate enough to grow your product into a platform, the standard strategy was to invite companies and users onto your platform so that they can get a leg up in offering their products. But when the platform felt it necessary to grow revenues further, it became opportune to rug pull those projects to capture their revenues. The Web 2 platform strategy became to build as broad and deep a moat as possible to stifle competition. Moats, not bridges. Web 2 represents the centralization of the web. Eventually, Web 2 on steroids became big tech. Big tech built itself into a weapon of mass manipulation, available to any actor who would pay. And big tech learned how to use AI and behavioral psychology to addict its users to its product. One result is that discourse on the planet is now hopelessly polarized and dysfunctional. Big tech has fomented, as a negative externality of its business processes, the shredding of the social fabric of much of the world. And now big tech, on even stronger steroids, is poised to convert its control of AI, talent, plus vast amounts of data and computation into building the most powerful tool in history for the centralized control of humanity. Fortunately, the pendulum is swinging back hard now towards decentralization and Web 3, the re-decentralization of the World Wide Web. Consensus was formed to continue the vision and mission of the Ethereum project, and just like Ethereum, we're dedicated to progressive, prudent decentralization of everything we do. Prudent because it must be done with care to ensure that we always focus first on the safety of and benefits to our users. And also that we never destroy value in evolving a project towards rigorous decentralization. We decentralize to build better, more valuable systems. MetaMask, for instance, is progressively decentralizing itself. The MetaMask Snaps plugin architecture allows users to add functionality to their MetaMask. Individual snaps are features created by third-party developers that MetaMask users can install directly into their MetaMask. And the MetaMask team has been leaning into account abstraction for a while. When the account abstraction dust settles, somewhat at least, we expect to expand MetaMask's scope and capabilities with components embedded in applications and enable you to add superpowers to your MetaMask or to any project via Dan Finley's delegation toolkit and framework. Continuing the pattern of progressing the vision and mission of the Ethereum project, Consensus Software announced yesterday that we're externalizing our Linea ZKEVM rollup technology and network into its own ecosystem. Linea is accelerating on the progressive path to rigorous decentralization and token-based community governance. Linea's evolution will be maximally Ethereum aligned. DIN, the Decentralized Infrastructure Network. Blockchains are complicated databases. Infura enables developers' products to read from and write to various blockchains with ease. But in a Web3 world of potentially millions of blockchains, Infura can't integrate them all on its own. So Infura has been progressively decentralizing itself into DIN, the Decentralized Infrastructure Network. A robust multi-chain RPC provider. DIN is already operational with 50+ partner providers offering connectivity to various networks and is already handling 100 million requests daily. And DIN is about to evolve into an eigenlayer AVS. Infura will become a premier specialized provider on the DIN network. Infura is openly sharing its optimizations, distribution to customers, and revenue opportunities with other providers in order to evolve the ecosystem. Bridges, not moats, can't be evil. DIN, Linea, and MetaMask Snaps enable permissionless innovation and onboarding to our infrastructure. We will not be the gatekeepers as our systems become more rigorously decentralized. It will not be possible for us to deplatform projects. Bridges, not moats, can't be evil. There are many other projects that are on our product development pipeline that runs from ideation through development, through product market fit, and into protocolization, externalization, and tokenization. We expect many of these to have powerful synergies in both functionality and benefit to the user. Standing up a proto-network state. The initial consensus company, Consensus Mesh, began as a tiny multinational startup because we had to look globally to find people who had a clue about what we were doing. Becoming a large multinational corporation is not cool. Becoming a global network state is cool. In order to operate most effectively in Web3, we build bridges, not silos. So we're working towards making Consensus Software Inc. more permeable or porous. For example, we've had policies for a while that enable our members to spend more time, spend some of their work time on projects outside of Consensus, like DAOs. Consensus is embarking on a new phase in its evolution. Consensus Software Inc., several of its projects and other projects in the extended Consensus ecosystem and beyond will soon set up shop on what we're calling the Consensus Network State. Network states are about alignment, transparency, broad governance, and collective benefit. We will progressively iterate in those directions. The capital city or DAO of the Consensus Network State will be resident on Linea Mainnet, the first island composed of Linea digital real estate. While Consensus will operate throughout Web3, we will consider Linea Mainnet our home network on which we build cores of our critical infrastructure. We will continuously look to build synergies among our products via explicit on-chain agreements. And we will look to create synergies among our products and your products via explicit on-chain agreements. Our friends at Sobol, Sobol.io, are in the early stages of building an on-chain agreements framework that we will use to form agreements between projects that specify in explicit and measurable terms what should be done by each party and what compensation, yes, token compensation, is due based on levels of performance. Performance can be measured in the usage of our products and protocols, or in providing liquidity, or in bringing your project onto Linea, or attaining levels of performance in your project in terms of users, transaction volume, TVL, etc. We will be employing a new yet ancient meta, work to earn. If a person or project adds value to the Linea ecosystem and/or the consensus network state, they will be compensated in tokens based on on-chain explicit agreements. Many of you out there are already self-sovereign on-chain, but we're all in the early stages of discovering what self-sovereignty means. We will be living more of our lives on-chain as our finances, identities, communications, art, and entertainment are increasingly mediated by open networks and decentralized protocols. The new relationships and communities that form will be the basis of new overlapping network states in which we will all participate. Today, we're launching solves.xyz, a project inviting everyone to declare their personal sovereignty as another small step towards the decentralized future. You can go to solves.xyz to attest to the kinds of sovereignty that matter most to you and write your support for the emerging world of network states and our liberation through them permanently on Linea. We have bigger plans coming soon. This is the beginning of a partnership with the community to build a network we all want to be part of. When we hear WWW in the decentralized future, we should think about a win-win-win world computer. Humanity has flourished via communication and coordination capabilities that give us massive advantages over other species. Coordination requires trust. Satoshi invented decentralized trust, possibly the most profound invention in human history. Decentralized trust platforms are now broadly available to builders and users based on blockchain and smart contract-based credible commitments. Web3 primitives plus AI automation are about to enable humanity to distrust each other much less and collaboratively build towards a post-scarcity abundance mindset that will enable us to evolve a massively positive sum world. So what does leadership look like in the decentralized future? Self-sovereigns in the decentralized future will be the CEOs of themselves, and they will collaborate with other CEOs using credible commitments on Ethereum. They will have clouds of AI allies amplifying their capabilities, and they will create complex delegations of on-chain powers with those AIs and with other collaborator CEOs. So what will leadership in a Web3 world look like? Well, that's up to you. Thank you.
All right. All right, thank you guys so much. And Joe, we do have some questions. Let's go from the first one. What can we do in 2025 in terms of tooling to boost the creation of network states?
Well, there are lots of primitives out there, and we're exploring them. So network states right now are more like proto-network states where the primitives are available, but a few systems are using them. As I said, you can call Ethereum a network state. You can call the Avara set of projects a network state. So it's happening, and we need to keep kicking the tires on our tools and start living in them.
How can we make the ecosystem safer to allow real adoption in a decentralized world?
Say it again?
The very first question.
Ecosystem safer.
Yes.
We have to keep building and security auditing. It's tough building Web3 on live monetary rails with the entire world watching. So it is a complicated prospect, but we need to get better and better in terms of security.
Here's another one. We can actually take the second one if you prefer. how can we more urgently shift the ecosystem towards reputational orgs where influence is determined by contributions to a project according to its values?
Consensus has built a reputation system, an attestation system. We're working on identity systems or aggregating identity systems. So we're trying to figure out exactly that. So whether it's reputation for MetaMask snaps or reputation for your activities in a project or a network state, it's pretty much the same system. So it'll get a lot of exercise.
What makes a network a state?
Well, a network state is a group of actors that are aligned to a specific purpose. It has capabilities. It could be anonymous people. It could be identified people. It could be could have the ability to create tokens for different purposes. Has the ability to set its values, to set its goals, and to achieve its goals.
And we have one on the ecosystem fund. Would there be identity and reputation systems to align not just financially, but personally and professionally?
The forthcoming Linear Ecosystem Fund or Consensus Network State Ecosystem Fund will have forms of decentralized ID, forms of reputation systems, but it should also be possible to operate as an anon. You may unlock fewer opportunities. You might get compensated less because there might be more risk in working with you. But I do believe that as reputation systems grow richer, we should get much more comfortable doing risky things with anons because you'll be able to calculate your risk.
We have enough time for one more question. How's network state different from DAOs?
A DAO is very much like a network state in its superficial definition. If you ask Balaji Srinivasan, who's been promoting the idea of network states, there's an element of formation which is initially on-chain, but then he likes the idea that it will reestablish itself or establish itself in physical context, perhaps in archipelagos all around the world. And so in his definition, a network state could be composed of a DAO and other constructs. It could be social graphs. It could be discourse platforms. But there will also be some sort of physical touch point.
All right, so our time is actually up.
Thanks,
Let's give a round of applause to Joe, everyone. Thank you. Hello, can I get everyone seated, please? So our next speaker, Walden, will give us a talk on how Hardhat 3 will ensure precise simulation for L2s using EDR. Let's give a round of applause to Walden.
Welcome, everyone, and thank you for staying until the end of the day. I am Wodan, a developer at the Nomic Foundation, and today I'll be talking about how Hardhat 3 will ensure precise simulation for L2s using EDR. There's a lot to unpack there, but first I wanted to comment on the Nomic Foundation. Maybe not everyone's familiar with it, but you're probably familiar with our work. We are a nonprofit dedicated to Ethereum developers, you guys. And our most well-known product is likely Hardhat and the Hardhat VS Code extension. That's us. So an overview of what I'll be discussing today is I'll start off with a quick introduction to what EDR is. Then I'll go into variability between L2s. I'll look at some problems that currently exist when developers are developing for L2s using L1 tooling. Then I'll do a technical deep dive into how EDR actually simulates L2s accurately. This will also be interesting for any of you L2 developers out there, as I'll talk about the extensibility points that EDR will expose in the future. And finally, I'll touch upon a demo that shows how L2s work in Hardhat 3. This will be interesting for all of you Hardhat users, as it will show how the technical complexity of all of this variability is boiled down to a simple and straightforward user experience. So what is EDR? EDR, or Ethereum Development Runtime in Full, is a reusable EVM development runtime library for tooling. It is a set of building blocks for blockchain simulation, and in particular, it allows you to observe EVM and Solidity execution. So as such, we are targeting smart contract development, the simulation, testing, and debugging thereof, and we're not targeting to be an execution layer node. If you're curious to learn more about EDR, earlier this year we had an EDR launch announcement when we integrated into Hardhat 2, and there's more information about other features, performance improvements that brought to Hardhat, and future roadmap for EDR as well. So what variability exists between L2s and L1? For the sake of this presentation and also for the implementation of EDR, we're assuming L2s that are EVM equivalent. This means that they have to comply with the EVM specification or the Ethereum white paper, if you will. When we can depend on rollups, any of the L2 transactions can have their own custom types. This means that when we're dealing with custom L2 transactions, that there is logic that's different, which is executed within the EVM. The way that we're dealing with rewards, the way we're dealing with fees can be different, and even the output that's returned can be different. For example, halt reasons when an exceptional halt occurs. When we go into a transaction and we look at the bytecode, the opcodes might also be different. It could be that an L2 doesn't support all of the opcodes of L1 or vice versa, but it can even be that the same opcode has a different type of behavior in the L2. For example, the block number opcode, how would we simulate this on an L2? Do we give a prediction of the L1 block that we expect to be included in, or do we return an L2 block number? Within the EVM, another thing that's different are precompiles. The set that's available in different L2s differs, as well as them being different from L1. Another thing that is different are hard forks. Every L2 will have a different set of breaking changes for which they'll have their own hard forks. And something that we need to track as well is so-called hard fork activations. Those are the block numbers or timestamps at which a particular hard fork becomes activated. And these will, for example, be needed when you do an ETH call at a particular block number. If we're forking a blockchain and we want to run a historic block, we need to know what hard fork should be activated at this point. When we then roll up everything into a L2 block, we also need to, at the protocol level, take into consideration fee calculation, and we need to incorporate custom transaction receipts. When we are deploying our own chain for specific L2s, we need to consider their own pre-deployed contracts. These are incorporated in the Genesis state and mean that you can access these contracts at a predefined address. These differ per L2. And then finally, if we go up one more layer, you have RPCs, the RPC, which might have additional fields for methods. It could be that a method returns fields but with a different behavior, and it can even be that one of those methods has entirely different logic altogether. All of these types of variability need to be incorporated, and keeping track of them is a huge pain, so a big shout out to EVM diff and the L2 documentation that was very instrumental when we were implementing the OP stack for EDR. So we have an idea now of what variability exists, but what problems might occur. Here are some examples. So when we start off at the execution layer, when we're dealing with unknown transaction types from an L1 perspective, we're not sure how to actually execute them. It could be that they throw an error, or it could be that they do execute, but because the opcodes have different behavior, the result is different. And as such, the L2 execution will be incorrect within your L1 tooling. When we're then trying to mine a full block, we also run into issues. The RLP encoding for these unknown transactions is unknown, which would result in an incorrect try route. And it could be that the header has different header fields, which would also result in an incorrect block hash. Then when we look at the gas calculation, these end up being incorrect as well. Let's have a look at the way that L2 transaction costs are structured. So on the left side, you'll see something that's very familiar. We have our execution gas cost consisting of a gas price multiplied by gas used. This is the same as on L1, except that L2 gas prices will be lower. But we have something new, which is the L1 data fee. This is the cost we have to pay for the rollup, or the part that our transaction is within that rollup. This is the L1 gas price multiplied by the L1 gas used, multiplied by the number of bytes of transaction data. Usually this is compressed to reduce the amount of memory usage, but we somehow need to convey this cost to the user. L2s do this differently. It could be that they try and convert this factor of gas price multiplied by gas used to an L2 gas usage, or it could be that they somehow try to change this to the L2 gas price. Each L2 will have their own strategy for doing this. Then when we're looking at debugging, for example, using debug trace transaction, what we're trying to do is we replay some block on the chain until we reach the transaction that we want to debug. And it could be that up until that point we find some unknown transaction, and we could treat them as an EIP 155 transaction or a legacy transaction, and try to execute based on a best effort, but this might result in errors. So instead we could choose to skip it. But this might have a negative side effect that if that transaction affected the state that our contract is also accessing, that we are getting a different result than we would on a test or mainnet. All of these examples that I gave have something in common. We're trying to build L2 smart contracts using L1 tools and hoping that it just works. It could be that the tests are passing, but there are still subtle execution differences that give us a false sense of security. And this leaves room for security vulnerability once we deploy. So how does EDR circumvent this and accurately simulate L2s? So here we have an overview of the different building blocks that I mentioned, outlined in black. In orange, we have entry points from and into Hardhat, and in purple, we have REVM, which is the EVM dependency that we use. Everything outlined in green is parts that we previously had supported for L1 Ethereum, but now we need to convert to be able to be multi-chain and also support different L2s. I've numbered it in two sections as they both have different requirements, and we'll delve into those respectively now. So the part outlined in one was all Rust code. So we need to look at extensibility from a Rust perspective. For this, we had several requirements. We wanted compile time polymorphism. This would allow users of our crates, or packages if you will, to be able to use these interfaces or traits during compile time to generalize their types and functions. We also wanted to generate type errors at compile time. This would force L2 developers to resolve any issues with their typing, as opposed to the error bubbling up to Hardhat users at runtime. Finally, we also wanted to ensure that our type definitions were reusable from a base chain to a L2 chain. For example, if we have an EIP2930 transaction, this is used in OP stack as well. So being able to reuse those types lightens the burden for L2 developers. The solution we used are the Rust traits and generics. Traits are a form of interface that can be used both at runtime and at compile time to constrain generics. And generics are just a way to generalize function definitions and type definitions across a type. For each of these traits or interfaces, we associated types with them that we consider to be a chain specification. Think of a transaction type, a block type, etc. And there are some constants which are used within the protocol. We distribute individual chains using Rust crates for reusability. So if we look at the overview again here, and we start at the top right, we have a remote network client which does RPC calls to a provider like Infura or Alchemy. Here we introduced an RPC spec trait that would define the RPC transaction or an RPC receipt, etc. Then when we go to REVM, here we introduce something called EVM wiring. We propose changes to REVM, and with the graceful help of Dragan Rakita, the maintainer, we were able to incorporate these large changes into REVM, which means that now within REVM you can also run and extend different chain types. Here you would define a runnable transaction, a block within which it's executed, the hard fork, halt reasons, etc. Then we go up one level to something we call the executor. The executor is a wrapper around the EVM, which receives a signed transaction, passes it in, and while it's executing, we gather additional data which we use for runtime observability. So things like traces for a stack trace, etc., that we expose to the end user. Here we introduce a type runtime spec. And then when we're incorporating all of these transactions into a block, within our block builder, we need to consider parameterizations for the protocol level, such as the base fee calculation. This has specific constants that need to be incorporated, which differ between L1 and L2. And here we introduced a ETH header constants interface to define those. Then all of this logic is tied together within the node or provider. And here we introduced a provider spec with things such as a pooled transaction. For example, for blob transactions, we also keep track of additional blob data, etc. And these are stored within the mempool. Then finally, we reach the RPC interface that's exposed to Hardhat. Here what we do is we use a tool called NAPI, which can be used for generating TypeScript bindings from Rust code. And this allows us to basically from Hardhat, which is TypeScript, call our Rust functions. And here we introduced a sync NAPI spec. Sync basically means we're trying to call our Rust code from a threaded environment, and this ensures that the access to that data is correct. And we also do a conversion from compile types to runtime polymorphic types, which we'll have a look at next. All in all, this encompasses 6 different traits or interfaces, and these are all the things that an L2 developer would have to implement in order for all of the building blocks that we have within EDR to be supported for their chain, and in addition, for their chain to be usable within Hardhat 3 in the future. So when we look at the part that was outlined on the left, we're dealing with TypeScript, so the requirements for extensibility are slightly different. We're dealing with runtime polymorphism. We're trying to minimize memory usage and load times. The goal here is that we shouldn't have to load all the possible L2 chains, only the ones that the user of Hardhat in that particular configuration wants to use. And we want to avoid centralization of chain types. We don't want a repository where you have to add your specific chain type to an enum. Instead, we want you to just be able to plug and play your own chain types independently. For this, we created an NAPI wrapper around dynamic trait objects. Dynamic trait objects are basically virtual objects where you can access a specific instance of an object through an interface. And to distinguish chain types, we use a string identifier. And then finally, for distribution, we're using NPM packages. Here we have an overview of what that looks like on the TypeScript side. We have if we go from right to left, we have a provider interface that receives a generic JSON RPC request and returns a generic JSON RPC response. We have two different implementations, one for L1, one for Optimism. These would basically parse the input, make it a typed request for their respective backends, handle it, and then again convert the response to a generic string, which is returned to the user. In order to be able to construct these, we're just using a factory pattern. So if we move one column to the left, we have a provider factory, which would receive a generic configuration, again using strings, and we have two implementations that would parse those configurations and make them typed and construct a respective provider depending on L1 or Optimism. If we then move one column further to the left, we have something called a context. This is maintained from the start until the shutdown of your application and contains a registry of provider factories, which is a mapping of the string identifier to the instance of the provider factory. If we look at a usage example, you start your application and would register any of the requested providers based on a configuration, and you store them in the registry. Then when a Hardhat user would actually request to create a provider, let's say Optimism, we do a lookup in the registry, find the Optimism provider factory, pass on the config, and ask it to create an instance of the Optimism provider, which is returned to the user. This is the way that we have designed extensibility. For the Hardhat beta, we'll be releasing with the OP stack and L1 support. In the future, we'll also be releasing all of these APIs, and it would allow you guys to extend it for your own L2. Now let's have a look at what this actually looks like in Hardhat 3. That got a little bit complicated on a technical level, but from a user side, it's actually quite straightforward to use. So here we see an example of a Hardhat 3 user config. At line 7, we have two networks defined, EDR L1 Sepolia and EDR Ops Sepolia. They both have the EDR type for the backend simulation. The first one has a chain type for L1, whereas the second one has a chain type for Optimism. This is communicating to EDR which typing system to use. And when we switch to Hardhat script, we see on line 3, we're requesting the Hardhat network manager to connect to the previously configured Ops Sepolia, and we specified that for its types it needs to use Optimism. This is informing the TypeScript type system that the estimate L1 gas function needs to be available, which would only exist for Optimism and not for L1, and we make a call to it through the public client, and then we send an L2 transaction to transfer one way, and we wait for the transaction received to be included in a block. So when we execute this, we're estimating L1 gas, gets 1600, and then we see that our transaction that was sent is included in a block. If we then go back and we switch the network we are connecting to EDR L1 Sepolia and used L1 typing, we see that we're getting a type error for estimate L1 gas, as this is not available for L1 networks. And the Veeam object knows this. So this is a sneak peek at some of the features that will be available with multi-chain and the kind of simple user experience that you get as a Hardhat user. If you want to learn more, we've had several other talks already at Devcon. We had a talk about the future vision of Nomic Foundation and the products that we're developing. We also had a talk which was a preview for Hardhat 3. And tomorrow we'll have a talk by the Slang team. Slang is a compiler as an API for developer tools. And this is basically useful for writing your own linters, doing formatters, etc. So if you're curious about that, go have a look at them tomorrow. Thank you.
All right, so we do have some extra time for QA. Feel free to scan the QR code if you have more questions for Walden. In the meantime, let's take this one. ARP has pre-deployed contracts that do not exist as EVM code on chain. Instead, it's Go code embedded into Geth. Any efforts to handle this?
So the way that we could theoretically handle that is instead of having it as Go code, we could include this in the Genesis state that is deployed when you're using an Arbitrum L2 chain.
All right, so let's wait for a few more seconds. We have another one here.
When Hardhat at 3. I think we don't have a announcement date yet, so stay tuned. We have an internal alpha going at the moment, but the beta will be sometime at the start of next year, but there's no definitive date yet.
How does EDR compare to Foundry's Anvil?
The Hardhat simulation, or the simulation component of it, and the RPC that's exposed is comparable, like identical in that sense to Anvil. The performance is also very comparable. We have a slightly different way of maintaining our state. And as a result of that, if you're very often switching between different states, so going and doing if calls and jumping back and forth between a previous state, making some modifications and jumping back, in those use cases we're often faster. But from a use case perspective, they're the same. The only difference that we might have is we haven't released our crates yet, which I think Foundry or Anvil has. But in the future, we'll be releasing a first version of EDR as well as crates on.
All right, perfect. Let's remain on the stage for a little while to see if I have more questions.
All right. If you have any questions, you can also meet me afterwards, and our CTO is also here who can answer any questions about Hardhat 3.
All right, that would be great. Thank you guys so much, and let's give a round of applause to Wodan. Thank you. Just to give everyone a heads up, tomorrow we can reconvene here at 9:45 for our first talk. All right, thank you guys so much for coming.